Hello, welcome to a tutorial about CoppeliaSim, or formerly known as VREP. This is an introduction video in which I will explain how VREP works, a brief introduction about it. Okay, I'm Leopoldo Armesto, I'm a senior lecturer at the Universitat Politécnica de Valencia, and these videos correspond to a set of videos in which I will introduce this software, and they are part of the robotic courses I teach in the university. So the aim of the video, in this particular video, is to introduce CoppeliaSim, or as I said before, formerly known as VREP. It's a robotic simulator. Actually, it's a very good simulator that can simulate any type of robot, and it has a lot of tools that makes simulations a lot easier. So the idea is to briefly show some of the capabilities, and for a first-time user, then I will just show how the user interface works, and also mostly how to move the camera to display different objects in my scene, how to pan, rotate and zoom, also how to add objects to my scene. And I will explain about the model browser and the scene hierarchy, and also I will briefly show how to see different simulation pages in order to have different views, and briefly explain about the physics engine library, which is one of the key components of the software. In order to follow this course, I assume that you have some previous knowledge, particularly in programming, because later on we will see some videos about programming a robot, and in the free educational version of CoppeliaSim uses a language which is called Lua. It's, let's say, not so popular language, not least as many other or popular languages like Python, but is easy and quite flexible. So this is the free version, the educational version of this software. And also I assume that you have some basic concepts about robotic system. If there's the need of explaining something in particular, I will do that along the videos, okay, so don't worry about that. And if you have some knowledge about 3D simulation softwares, basically to understand geometries, 3D shapes, and how these simulation softwares works in order to run dynamic properties of them and so on, this is usually quite recommended. But yeah, we will see all details. Okay, so let's let's move to the software, and this is CoppeliaSim, and this is the default scene as we can see. And here we can see obviously some menus and some icons here on the top that will be commonly used for us, and also some icons here on the left that we will use for different purposes. Okay, so we will see some of them. Okay, so first thing is these three icons here will allow us to modify the way we interact with the view here. So the first one, which is selected by default, is the pan. So I can pan my view, so I can shift it if I click, or I can rotate my view. Okay, this is also I can do a zoom out or zoom in. Okay, and here we can add, for instance, let's say for the first time we will add a cuboid. By default, let's create a default cuboid here in the middle of the scene. And as you can see here, what I have right now, it's a cuboid, and I can focus on it just by clicking on this icon here. Okay, so I fit my view to be closer to that object, that particular object. Okay, so now let's see what we have here on the left. We have a model browser and we have a scene. The model browser is basically a library with folders in which we have a lot of components that will be used by default, or they will be used in our simulations, and by default we will have this view here in which we have this one selected. And as you can see, we have a folder with robots and non-mobile robots, basically are ARM robots. And we have a lot of existing models with robots provided by manufacturers or users. So let's say we want to create or add a new model to our scene. So we just simply need to drag it there, and we can fit the view. So there's our new object, and as you can see here in the scene, we have the cuboid, which is not visible right now because it's small and it's hidden by the robot arm, and we have the robot arm. We also have a quite huge variety of mobile robots. As you can see here, you can play with them. All of them are mostly ready to use, so yeah, you can try to investigate how to use them. And also we have other objects that we can use, for instance, to decorate our scenario. Okay, and this is, for instance, a plant. Or we can use another one, which will be a person there. Okay, and we can have even other things like, for instance, walls of different heights. This is convenient if we work with mobile robots, moving on environment, a maze, something like that. Okay, and all these objects, as you can see here, have been added into the scene. The scene represents basically the list of objects that will be used in our simulation. And as you can see, by default there are some objects already created for you, but all the objects I have created have been appeared here in the scene. And the most important thing about the scenes or the objects, and we will see that into detail, is that they can have different, or there's a hierarchy on the objects on the scene. So if you click here on the plus sign, you deploy or expand the full hierarchy, and you have different objects. You can see here, yeah. And for instance, in this case, what we have, this is the root node, or the root object, which is the parent, and it has one single child, in that case, another object, and it has another child, and it has another child, and this one has 3 childs, and this one has additional childs, and so on. So there's like a tree having a lot of objects, and the important thing here is that a parent can affect how the child behaves. Okay, so for now that's enough, and let's also see how, for instance, this cuboid here, which is hidden right now by the robot, we can modify the position of the objects by clicking here, and we have this translation a dialog in which we can modify the X and Y position. So if we just right click right somewhere on the scene, we will see that we can move the object. Okay, we can also do it along, for instance, a specific direction like Z. Okay, and we can also rotate the objects. For instance, we can select the robot and rotate it, as you can see here, depending on the axis we select. And then we can also set the properties for our simulation, and in particular this is using the bullet library, which is what I recommend by default. So I don't recommend to modify these things unless you know what you're doing. But as a simulations engine, what it's in charge of moving all the objects on our scene and trying to detect all the collisions and react against each of the objects. Okay, so we will see that in detail later. Okay, so for instance, if we run the simulation, we have here the play button, and we have the person that was moving around the scenario. Okay, we can pause it and we can stop it. Okay, and finally what we can do is to change the view of my scene. So if I select this, I have this normal view, but I can have also a top view here, which might be useful for some purposes. Okay, and yeah, okay, so let's return back. Okay, so in this presentation I have briefly introduced how to use VREP and some of the capabilities. Thank you very much. Hello, in this video I will explain the properties of objects in the robot simulator CoppeliaSim or VREP. I am Leopoldo Armesto and this video is part of a tutorial about the use of CoppeliaSim for robotic courses that I normally teach at the Polytechnic University of Valencia. The aims of the presentation are basically to describe the main properties of objects in CoppeliaSim, understand the differences between a respondable and non-respondable objects, as well as between dynamic and static objects, to show some of the basic properties of shape and appearance of an object and understand visibility layers of objects, and also to understand special properties of an object that will affect the way in which the simulation is performed. So objects can be dynamic or static. A dynamic object is affected by forces such as gravity, collisions between objects, and other restrictions such as joint, as we will see. On the contrary, a static object can modify its position or orientation only if we modify it manually or if we do it by code, by programming. Okay, but they do not depend on these forces. Okay, so they basically allow us to implement purely kinematic simulations, which are more easy to understand. So, in addition to these, objects can also be reactive. Reactive is a property which is known in this simulator is known as respondable, and basically it implies that a reactive object can react against another object, also another reactive object, if there's a collision. So here I will explain the object interaction map. So if you want to get further information, you have to follow the link I show you below. So, so let's say that for dynamic properties we have four possible cases. So an object could be a static object or dynamic, but could be also at the same time respondable or non-respondable. And depending on the properties of these objects, they interact different on each of the cases. So for instance, when we have two static objects that are non-respondable, the objects won't move, they will be static, so they won't move at all, and since they are not collision at all, or even if they get into collision, they do not react because they are non-respondable. So also we have the case in which the objects, both of objects are static, but one of them is respondable. In this case, because of the objects are static, they don't move, so they don't react. And there's another or a third case in which one of the objects is dynamic. In this case, the dynamic object will move, let's say with the gravity falling down, okay? And if that object is non-respondable, means that whenever it enters into a collision with another object, it will not react. So if it's falling, for instance, imagine that you have a dynamic object but not reactive, just on top of another object, then once it's falling down and passes through, it will pass through the other object because it does not react. It does not generate a reaction force. And the case in which both objects will actually physically interact will be the case in which, for instance, the objects are respondable. It could happen, for instance, one of them is dynamic, the other one is static, but basically if the dynamic object is falling down and both of them are respondable, then they will react based on the principles of the third Newton's laws, action and reaction. And also objects have special properties, and these properties are very important in order to control the way we execute our simulation. Specifically, the most relevant properties are the collidable property, which means that if we activate this property, then an object with this property active will enter into a list of objects that can collide, which means that it will be used in order to detect possible collisions with other objects, but it does not imply that they will react. They are basically used for other calculation purposes like path planning in order to compute collision-free paths. Okay, so these algorithms or these modules will try to find or know which objects are collidable and which are not collidable, and only the collidable objects will be considered for their computation. Also, a detectable object will be detected by proximity sensors. So if we activate this property, means that proximity sensors such as ultrasonic, laser or infrared can detect the object and will provide a distance of that object to the robot or to the sensor indeed. Okay, so another property will be the renderable property, which means that these objects can be seen by vision sensors. So if you activate this property, then you have a camera in which you can do some processing, and only these the objects with this property active will be actually rendered on that camera and then can be detected. And finally, the measurable property will be used for the minimum distance calculation module, which is useful in or convenient in certain cases, specifically to avoid collisions too. So also objects have some shape properties, especially related with the geometry, and we can modify, for instance, the scale of an object, so we can scale it and make it bigger or smaller, and also we can adjust the color and even to provide a texture to an object to modify its appearance. And finally, what we can do in the properties of an object is to control the visibility layers. The software has 16 visibility layers that allow us to show or hide objects during the simulation. So the first 8 layers are usually used to show, let's say, nice objects, which are usually more complex objects such as meshes or convex objects, and they are usually used by the graphic engine, which is in charge of displaying them in our simulation. And the following 8 layers are usually used to show simple objects, and they are part of our simulation, mostly affecting our physics engine. Usually we can here include pure objects or maybe convex objects too, and also joints. So these objects are usually hidden on our simulation, and this can be controlled using a global mask. So the global mask by default uses the first 8 layers, as you can see here, active, but we can invert that and we can see the objects that are on the other layers, so we can see what's behind the simulation. Okay, so we will see all these properties on the next video. Thank you very much. Hello, this video is a continuation of a video describing the object properties and the simulation of CoppeliaSim or BREP. And in this video I will show you actually how to change or where to locate these properties and how to modify them. Okay, so first let's study what we have here, what I have prepared for you here. We have a scene with 8 objects. They have different dynamic properties. We will see them. And you can see that one of them is on top of the other one. We can see easily that if we change the view here, and you can see that in this top view, we can see that the colored objects are on top of the gray ones. Okay, so if we return to this view, okay, so as you can see in our example, we have different objects here in the scene, and we can first change the name of the objects by modify them. For instance, if we double click on the text of the object and we modified that, then we modify the name of the object. This is important, particularly when we will start using the coding or the scripting part of the software. Okay, and also each of the objects has always an icon here. We will see that on a different video, the icon type. But if we double click here on this icon, what we can see is the send object properties. It's a dialog in which we can modify the properties of the selected object. So right now we have this object selected, and as you can see here we have two different tabs, one related with the shape and the other one related with the common properties. Let's start with the common properties first. So if we go here, we have a set of properties here that we can select and modify. The first ones are related with the camera visibility layers. As I explained before, the software allows to select individually on each object where you want to be visible. And by default, if you access to this dialog here right on the left side, you will see the visibility layers that are actually active here. By default, the first 8 layers are active. So indeed, all these objects have the first layer. As you can see here, this is the first layer, the second one, and this is the 8th one, this is the 9th one, and so on. Okay, so all layers here that are active, if this is active and this is active, then the object will be visible. So if this activates that one, the object is not visible anymore. Okay, indeed, we don't see it here. Okay, and it gets the gray color here, but so it's still on the scene, but we can see it. So if we want to see the object again, we have to activate that. And if we deactivate this global check, then all layers that have this layer active will be hidden. So as you can see, all of them are hidden. Okay, and what we can do, for instance, is if we select or we active the second layer for this object and we deactivate the first global layer, only this object is active. Okay, so as I said, by default, this is the standard behavior to see, let's say, the NAS objects, and we can invert and see what's behind the simulation. And usually here we will select the object, we will view the objects that are affecting usually to the dynamic simulation. Okay, so this corresponds to the visibility layers, and also here we have in the common tag we have the special properties of an object. Particularly we have the collidable, the measurable, detectable, and renderable. These objects can be set individually for each object, so we can set them, or we should set them only if we are going to use the object for that purpose. For instance, if we want, imagine that this object is a wall or something, we want to be the object detected by a proximity sensor, then we should check this property of this object. And also, if we want that object to be considered as part of the motion planning algorithms to generate a collision-free path, then we should activate that property. And if we want to see this object with a vision sensor, then we should activate this property here too. Okay, so I'm just simply undoing the changes. Okay, so now let's move to the shape properties. First thing is, here we can modify the color of an object by modifying the ambient component. So we can, as you can see, we can modify the color of an object. Okay, so let's go back. And also, let's say I select this object here, and now I want to modify it or add a texture. So we can load an existing texture. Here, this is a garage concrete texture. So if I modify it, it should appear in here. There must be an option in which is static texture. Here it is. It's modified. Okay. So this affects to the appearance, but the most important properties we can select is the when we enter in this dynamic properties dialog. So if we click here, then we have this dialog here, which is very important for us to control how the simulation works. So as I said before, objects in this simulator could be respondable or could be dynamic. or could be non-respondable or static. So this depends if we select these options here, will be respondable or non-respondable, dynamic or static in this case, okay? In the case of being dynamic, then this object will have additional properties like the mass, the inertial, the moment, the mass, and so on, okay? So these things we will see them later in, for advanced features. Okay, so let's see exactly in this scene that I have prepared here for you what we have. So let's start with this object. This is a non-respondable and static object. So this means that it won't move. And this is also non-respondable static object, so they won't move at all. Okay, this one here is respondable, means that if someone collides, it will generate a reaction force, but only if the other object is also respondable. But it's static, so it won't move too, either. So also this one is respondable and is static, so it won't move. And this one here is dynamic, so it will fall down because it will be affected by the gravity, but it's non-respondable, which means that even though this object here below is respondable, even though this object is respondable, when both of them collide, the green object will pass through the gray one and indeed will fall down to the minus infinity, okay? And these two objects here, this one is respondable and dynamic, this one is respondable and dynamic, and they will, the red one will fall on top of the other one. Okay, so let's run the simulation here to see how it works. Let's just first move this thing here. And as you can see, these two objects are static, so they haven't moved. This one has fallen down, but because it's reactive, it's respondable, they collide each other, so they stay there. But the green object has disappeared. Let's do it again, and slightly slowly, so you can see it. Okay? So the green object passes through the other one. Indeed, this object here right now is respondable and is static. But if we modify this and we set that to non-respondable, what happens is that this object is affected by gravity, but because it's non-respondable, what it will happen is that the floor is also a reactive object, so it won't react against the floor, so this object will fall down too. As you can see, both objects have fallen down. Okay, so this is a brief summary about the object properties in VREP or CoppeliaSim. Thank you very much. Hello, in this video I will explain how to apply translation and rotation operations in CoppeliaSim VREP. The aim of the video is to understand different operations of translation and rotation on objects, as well as to understand different reference systems with respect to we can perform these operations and what happens when we apply these operations on objects with a hierarchy relationship. Translation and rotation operations are basic operations in any robotic system. If you don't know these concepts, I recommend you to watch my videos about the position representation and orientation in the playlist of robotic systems in my YouTube channel. In CoppeliaSim, the position is expressed in meters, while the orientation is expressed in Euler XYZ angles in degrees. We can apply these operations by clicking on the icon, these icons, to access the translation or rotation dialog box. We can move objects with the mouse or manually enter the coordinates with respect to the world reference frame or the coordinates relative to an object that is hierarchically superior to that object, that is the parent. Finally, we can perform also basic translation and rotation operations relative to the world, parent, or even its own reference frame. The world reference frame can be found at the bottom right corner of the program, and it has the appearance as shown here. On the other hand, the object has its own reference system and it will be displayed when we select it. The color code for the reference frames is red for the x-axis, green for the y-axis, and blue for the z-axis. When two objects have a hierarchy relationship, these operations or the operations we perform on the parent object will affect to their children and all those objects that are hierarchically below it. Sometimes we need to move an object that has children, but only this object, maybe because its position is not correct. So in that case, in order to not to affect the children, then what we must do is to first undo the hierarchy relationship and then perform the translation or rotation operation and then redo the hierarchy relationship. In another video, I will explain about the hierarchy relationships between objects. For the moment, you just need to know that rotation and translation operations affect objects that are below it. Sometimes we are interested in aligning one object with respect to another one. Let's say its height or a given orientation. So what we can do is we can copy and paste the coordinates from one object to another. The procedure is actually quite simple. You need to select first the object you want to move and then press the Shift key and select the object where you want to move it. Then access to the translation or rotation operation dialog box and select here, select which coordinate you want to apply or paste. You can select them individually or you can apply all coordinates at the same time. In this video I have explained translation and rotation operations, and in the next video I will show how to apply these operations in the simulation software CoppeliaSim. Thank you very much. Hello, in this video I will explain translation and rotation operations in CoppeliaSim or VREP software. As you can see here, we have a very simple scene in which I have created one cuboid. Here is this one, and another one which is here. It's in a different position. Okay, so let's start by knowing how we can apply these operations. So first we have to select the object we want to move, and here if we click on this icon we will perform translation operations, and if we click on this icon here we will perform rotation operations. So let's start with the basics of doing translation operations, and this is the dialog box we have, and we have the option of doing the mouse translation, which means that we can move this object when clicking on the mouse. Okay, so you can see here, and we can do that by selecting these two things here. We move along X and Y, so this is the plane. Or we can do that by selecting Z and modify the height of the object. It is important to mention that all these operations are always relative to a reference frame. In this case, by default, we have the world frame, which is the reference frame that you have on the bottom right of the software. And you cannot see here because I'm occluding it, but you can clearly see on the software. Okay? But you can do that also if you apply these operations with respect to a parent frame or even to its own frame. As you can see here, the own frame is clearly shown here. Once we have selected the object, we have here an x-axis, which is the red arrow, and the z-axis, and the y-axis is just pointing there. Okay, so in this case, also we can obviously select or set the coordinates manually. Imagine that we have done some calculations and we determine that we would like to have this coordinate with this value. So we can modify the x coordinate or we can modify the z coordinate individually, or we can do it with respect to the world or with respect to the parent frame. Okay? Then we can also apply relative, or we can apply translations which are relative to the world frame, the parent or the own frame, and this is the amount that we're going to shift. Okay, so in this case, imagine that we want to shift along the x-axis a given quantity, and we can do that by clicking on each of the operations, or we can just simply undo this by applying the negative operation. Okay, we can, as I said, we can do that with respect to the wall frame or even with respect to its own frame. Okay, so now the aim is to explain how to, in this case, copy and paste the position of one object with respect to another object, and also how the hierarchy relation between objects, how does affect to the objects. Okay, but before that, just simply let me show you that in the case of the orientation, because we haven't seen that, we have also the option of modifying manually the orientation here, so we can rotate to a specific coordinate, or we can, in this case is the Z axis selected, or we can manually rotate a given amount. Okay, and yeah, okay, so now let's imagine that we want to move the x coordinate of this object exactly to the same coordinate, x coordinate of this object. So we want them to be aligned on the x axis, actually aligned on the y axis. Okay, so first thing we have to do is select the object we want to move, and then press Shift and select the object that we would like to align to. Okay, in this case, cuboid 0. Then we access to the translation dialog box, and in the position here we select, or we click on Apply X to Selection. This will copy the X coordinate of this object into the X coordinate of this object. Okay, and you can see now both objects are aligned. Okay, imagine also that we would like to have the Z coordinate also the same, so it will go just to the floor. Okay, good. And also imagine that we want the other way around, so we would like to have this object here, the same orientation of this object here. So we first select this object, we click Shift, select the other object, we go for the orientation, and we apply the selection, and the object rotates. Okay? Yeah, okay. So this is with respect to the copy and paste feature. And now let's see what happens when two objects have a hierarchy relationship. Okay, so imagine that this cuboid here is child of this other cuboid. So we can do that, just as you can see, just by click and drag there, drag and drop. Okay, so now this cuboid here, whenever we apply a translation, rotation, or whatever we want, let's say this thing here, it will also move the object that is below in the chain. As you can see here, we can do that with translations, or we can do that with even with rotations. Okay, thank you very much. Hello, in this video I will explain the hierarchy between objects necessary to create different robotic systems. Specifically, I will show the classic hierarchy of an articulated robotic arm and of a wheeled mobile robot. Therefore, the aims of the presentation are, on the one hand, to understand the advantages of using object hierarchy. In addition to this, our goal is to understand the hierarchies typically used for both of an articulated robotic arm and for the case of a wheeled mobile robot. Also, I will mention the recommended method to establish the hierarchy between pure and non-pure objects. The hierarchy between objects is necessary to be able to apply translation or rotation operations on objects in a serial link, as is the case of robots, since the hierarchically superior elements can move the objects that are below. In addition to this, it allows the parent object to access to objects that are hierarchically inferior, to access to their children, and this can be used, for instance, to read data from a sensor. Indeed, the software includes some calculation modules such as the inverse kinematics or motion planning, and these modules, they need indeed hierarchical structures. Pure geometries are typically hierarchically superior to non-pure geometries. This is because all collision physics and dynamics are applied to pure geometries, so that non-pure ones will always be associated with the position and orientation of pure geometries. Here we show an example in which we have a pure geometry and a non-pure geometry. The pure geometry is indeed this cube here with the transparency, and the non-pure geometry is indeed this object here inside. As you can see, we have dragged the non-pure object inside the pure object to establish the hierarchy. So obviously, the better adjusted the pure geometry to the non-pure geometry, the more realistic the simulation will be. Now we're going to study the hierarchy between links and joints. In the case of robot arms, we have a serial link structure, so that the first link is the base of the robot and usually is the fixed link, is this one here, and corresponds to this object here. Then after this, we find a set of joints and links in a chain structure. Each joint moves the next link of the chain. For instance, here, this joint here moves this link here, and this joint here moves this link here. And this can be seen here as this hierarchical structure here. In this other example, we will see that, what we need to use in case of a wheeled mobile robot. In this case, the hierarchically superior element is the robot base, which is this object here and corresponds to this object here. So the base includes two joints corresponding to the left and the wheel joints, and which are this one and this one, which correspond to these two joints. And each of the joints has another link which has the wheel shape here and corresponds to these two objects here. Also, we have a supporting wheel, a caster wheel in this case. We can model this wheel by adding a vertical joint here, which corresponds to this joint here, caster support, which will rotate freely based on the orientation of this joint, and another horizontal joint with a wheel that will be the one which will be indeed contact with the ground. Although we don't show it here, but if our robot will include sensors, for instance, they will be child of the robot base or any other object that will be child of the base. Well, in this video I have explained the hierarchy between objects in order to build the robot. I will show you how, in more detail, how this articulated robot arm or the wheeled mobile robot work in the CoppeliaSim software in the next videos. Thank you very much. Hello, in this video I'm going to show how a robot arm hierarchy should be in order to work with CoppeliaSim or VREP software. Okay, so as you know, a robotic arm is basically a serial link in which we have a first link, which is the base of the robot. This link here corresponds to the base of the robot, and then we have a sequence of joints and links serially connected. In this case, they have this hierarchy relationship, as you can see here, in which the first joint will drag all the objects below it. So it will move indeed the first link, and this will move the second joint, and when we move the second joint, we'll move the second link, and so on. Okay? So let's see, for instance, this in action. So imagine that we would like to move this joint here. I have to simply double click on the icon to modify the angle of the joint. So imagine that we would like to have 30 degrees here, and once we press, everything below the joint has moved and rotated properly. Okay? This is a typical case in which we move all the elements just by modifying the orientation of this joint, and also we can do that or we can do the same with respect to the second joint. For instance, imagine that this is 30 degrees. Imagine that we would like to have 10 degrees, and modifies the orientation of the remainder of links. Link 2, the joint, and also link 3. Okay, in this very simple example, I have just used pure geometries in order to represent the robot. In a more realistic scenario, we should use non-pure geometries like complex shapes, meshes, and so on in order to represent our robot, and they should be childs of each of the links we have here. So whenever this link moves, then the corresponding non-pure object will also move too. Okay, thank you very much. Hello. In this example, I'm going to show you which is the proper or the most convenient hierarchy between objects in order to model a mobile robot, as you can see here in the figure. So in this case, what we have is that the parent will be the robot base, which is indeed this object here. That's the robot base. And depending on this robot base, we have two axes. We have this joint here and this joint here, which correspond to the left and the right motor in this case. And each of the objects, each of the joints have associated to it a wheel. So whenever this motor spins, will actually make this wheel turn here. Also, we have a caster wheel, which has been modeled simply by including, in this case, a vertical axis will be free in motion, so it won't be attached to any motor. And this joint here will move the caster wheel support, which has been modeled for simplicity here with this object here. Also, this will move or rotate this joint here, which is a horizontal joint that will actually allow the wheel, or the caster wheel, to rotate, which is the one that is in contact to the ground. Okay, in this example, it's still very primitive, it's very basic, and it's not yet ready to run a proper simulation of a mobile robot base. So even if you run it here, you will still find some weird behaviors, like this one. Okay, in order to properly adjust all the dynamics properties of this mobile robot, we will explain them in different videos. Thank you very much. Hello, in this video I will explain different joint types that we can use in CoppeliaSim, VREP robot simulation software. The aim of the presentation are to understand the different joint types and how do they describe movement between objects, to know different joint modes, to implement torque force control, velocity, position control, or even a motor-free mode. And finally, another objective is to understand when the joints have to work dynamically or statically. There are three types of joints: revolute joints that allow turns around the joint axis, prismatic joints that allow linear displacement on an axis, and spherical joints that allow changing the orientation arbitrarily. Joint size is not important, it's just simply an aesthetic aspect. The important thing is the direction of the axis and the position value, angular or linear, depending on the joint type. Both revolute and prismatic joints have 1 degree of freedom, while spherical joints have 3 degrees of freedom. Indeed, they can be seen as 3 revolute joints intersecting at the same point. Joints allow relative movement between the parent and the child object. When a hierarchy relationship is established between a joint and an object, it will move according to the position of the joint. In the case of an articulated robot arm, the robot links moving according to its joint position will change. Joints may have physical limits where the position must lay. This is clear in the case of a robot arm, while wheels of a mobile robot can rotate, let's say, unlimited. Joints can be passive, that is, joints that are not directly controlled. and they are fixed, although the position can be modified through programming scripts. On the other hand, joints can be dynamic if we set the torque force mode, so they can be controlled through the physics engine. They can be actuated or non-actuated, and the reference values can be set through programming scripts too. Finally, joints can be in inverse kinematic mode, so the inverse kinematic module controls the position of the articulation, or a joint can be also in dependent mode, which means that its position depends on the position of a different joint. When a joint is set in torque force mode, it can have a free movement if there's no actuator. In the case of using a motor, then the speed of the joint can be modified or can be controlled if we do not activate the closed loop control. But if we activate or we enable the closed loop control, then we can implement a position control using a PID, or we can implement an impedance control acting as a spring damper. Speed control is quite simple. If the maximum torque of the joint is high enough to move child objects, then the speed of the joint will be equal to the reference speed, and this happens instantaneously. If the force is not enough, then it will gradually increase until it can be reached, as long as the maximum torque allows it. This mode is suitable for speed control of wheels of a mobile robot, or even, for instance, a kinematic control of an articulated robot arm. Position control of joints uses PID control, which sets in the end the joint speed. This is the most convenient way if you want to establish a position control of an articulated robot arm, but you don't want to consider all the complexities of implementing a pure dynamic control, for instance, in order to compensate gravity. This is more or less equivalent as using RC servos in a robot arm, and let's say that you establish the reference and that the RC servos are in charge of regulating the position. Tuning of PID control parameters or constants is an advanced topic, and this will be seen in another video. If, on the contrary, we intend to perform a force or impedance control, we can establish viscoelastic constants of a spring damper system. This may be convenient, for instance, in the case of robots with elastic joints, but again, this is an advanced topic, and this will be seen in another video. When using joints, you must take into account if the object that you are moving is static or dynamic. For dynamic objects, we must use the force-torque mode or activate the hybrid mode. If the object is static, you can use either a passive, inverse kinematic, or dependent mode, but then you cannot use the hybrid mode anymore. There's a mode in which we can expect, or there's a tool in which we can expect if an object is dynamic or static, and this will be very useful whenever we need to detect if we need to set the joint in dynamic or in a static mode. In this video, I have shown different joint types in CoppeliaSim VREP. On next video, I will show you how to work with joints using the simulator and how do they respond under different configurations. Thank you very much. Hello, in this video I'm going to explain how to work with joints in CoppeliaSim software or VREP and how to configure them. Okay, so first let's start by knowing where or how to add a new joint in our simulation. We have the add menu here and we have the joint. And we have the three different types of joints. We have a revolute joint, we have a prismatic joint, and then we have also a spherical joint. Okay? In this example here, I have just prepared an example in which I have configured different types of joints, and in this case all of them are prismatic, but yeah, you can see similar things with revolute joints too. Okay, so let's try to understand first what we're doing in this simulation. Here we have a joint, which is this one, which is if you double click on the icon, you can get to the properties of the joint of the object, and then you can see here that you have different modes. Okay, in this case this joint is set to torque force mode, but as I explained in a previous video, you can also use the passive mode, the inverse kinematic mode, or even the dependent mode. Okay, so this is the force torque mode, means that the joint is dynamic, and therefore you can activate or set here the properties for dynamic joints, and in this case there's no motor enabled, so it's just simply joint without a motor, and which means that this link here, this object here, by gravity will fall down because there's no actuator. Okay, so let me just open this. Yeah, sorry, not this one, this one and this one. Yeah, exactly. So this is the first joint. The second one, which corresponds to that one, is in this case again torque force mode and has a motor enabled, so it's actuated, and also has a control loop enabled, in particular the position control with a PID. This one here, the next one, will be exactly the same, but instead of position control we'll have a spring damper mode, which basically will set or will act as a spring damper, and because of the gravity will just simply fall down, but not completely. This joint here is motor enabled, so it's actuated, but there's no control loop enabled, so it means indeed that it's in a velocity mode. So we can set the target velocity and this will move accordingly. Here it is just simply stopped, but you can do that through programming. This joint here, the next one here, is a passive mode. It's in passive mode, as you can see here, but we have activated the hybrid operation, which means that indeed the motor or the joint is actuated with a motor, and we can select either if we want to set the position control or the spring damper. In this case is the position control. This one here, the next one, is in passive mode again, but the hybrid mode is not activated. Okay, this should be correct if the object we move is static. But if we take a look to the object here, if we see the properties, this object is dynamic, so this is not correct. Okay, so it can send us a warning or could generate incorrect simulations. So this is just simply to show an incorrect case. Okay, this one here is indeed the correct way to do things. Is the joint is exactly in the same way, so it's passive and the hybrid mode is not activated, but the object here is static, so it's the dynamic property is not active, is not enabled. Okay, so the object is static, and that's fine, that's correct. Okay, and the last one here is the other way around. So the thing is that the joint in this case is in a torque force mode, which means that it's dynamic, could be passive mode with hybrid operation, whatever, it's still dynamic, but the object we're moving here, if we take a look, is static, and this will also generate problems. Okay, indeed, if we run the simulation, we will see this message here that is actually indicating us that there's a warning here caused by the fact that this joint is dynamic, but it's moving a non-dynamic object, it's a static object. Okay, so this is not the proper way to do things. Okay, and that's why we get the warning. Indeed, if we stop and run it again, you see that this joint here, because it was not actuated, has fallen down. This one has a position control enabled, so yeah, it's just simply controlling exactly the weight or this link here on the expected position. This was in a spring damper mode, impedance control, so it has just simply fall down a little bit until the spring or the force caused by the spring is strong enough to hold this block here. This is in target velocity mode. At the moment it's stopped, but yeah. And then we have this passive hybrid position, so this could be more or less equivalent to that one. The difference is that here we need to modify the target position using the script, and in this case is the case in which was passive and non-hybrid, but this was a dynamic object. That's why it has been somehow broken. Okay, so it's not working properly, and this one is exactly the expected behavior if we use a static object. It doesn't fall because it's a static, but it's not causing problems. And this one here is actually causing a problem and it's not working properly. Okay, well, I hope with all these examples I've shown here, you have more or less a clear idea how to work with joints in CoppeliaSim or VREP software. Thank you very much. Hello, in this video I will explain what kind of sensors we can simulate in CoppeliaSim VREP. In particular, I will explain how proximity sensors, vision sensors and force sensors work and what are their main properties. CoppeliaSim allows you to simulate proximity sensors to obtain the minimum distance between the robot and any detectable object in the scene. It implements up to 6 different types of detection volumes that allow you to simulate different types of sensors, such as ray type, typically used to simulate a laser sensor, or a cone type, typically used to simulate an ultrasound sensor. Detectable objects can be detected only even under certain type of sensors, which can be useful under certain conditions. For instance, a Hall effect sensor detects metallic objects, so you can set that a specific object is only detectable by inductive sensors, and then it cannot be detected with other type of sensors. Or for instance, another case is crystals. Objects should not reflect light from a laser sensor, but can be detected with an ultrasound sensor. This can be set in each object in the detectable properties dialog box. In addition to this, on each sensor we can set properties to define the sensor type, to adjust the detection volume, and also some detection parameters. Vision sensors allow you to simulate cameras that can be processed. You can obtain images from visible and renderable objects. Vision sensors can be orthographic type, which indeed define a rectangular volume, or perspective type, which define a trapezoidal volume, as is shown in the figure. In addition to this, the camera view, either the original or the processed image, can be displayed on a floating view during a simulation, and this could be very useful. Vision camera processing can be implemented using function callbacks. These are special type of functions that will be called whenever we get a new image using this sensor, but this is something we will see in a different video. Vision sensors can be used as standard RGB color cameras or can be also used as 3D cameras. That is, they provide the depth or the distance to the objects on the scene. The most relevant parameters when using vision sensors are the field of view, which are indeed the near and the far clipping planes where the object is focused, as well as perspective angles and the ortho size. Also, a very important parameter or property is the sensor resolution, which indeed defines the number of pixels of your image. Finally, force sensors allow you to measure torque or forces in the 3D axis, as is shown in the figure. They indeed act as links between two objects, so they make that the two objects are linked together, but this link is weak because it could be broken if the force that this sensor supports is higher than a given threshold. In this video, I explained sensors that we can use in CoppeliaSim. In the following videos, we will show how this sensor works. Thank you very much. Hello, in this video I'm going to explain how to work and how to configure proximity sensors in CoppeliaSim VREP software. So basically the first thing you need to know is whenever you want to create or add a new sensor, proximity sensor, you need to access to the add menu and go here for proximity sensor, and you have different type of sensors types or proximity sensors like the rate type, randomized rate type, pyramid type, cylinder type, disc type, and cone type. Indeed, all of them are basically the same. The only thing that changes mainly is the volume, detection volume that you use in order to detect your object. And this is something we need to configure in order to simulate or properly simulate different type of sensors. Okay, and this depends on the sensor. In this particular example, what I have created is 4 different sensors. This is a Hall effect sensor, which is it has this in this case this cylinder type. Okay, and you have also an infrared sensor, which is that one. It's a pyramid type. This is a laser, which is in this case is a ray type. And this is an ultrasonic sensor which has the cone type. Okay, so depending on the sensor, you can set the different sensor subtype, and this is something you can set here. And this is only important or relevant if you want to a specific object to be detectable only for a specific sensor type. So this is something we will see later. Okay, so here we have different types of sensors like ultrasonic, infrared, laser, inductive, or capacitive. And any sensor can have some volume parameters that we can set. In this case, this is a cone, and depending on the volume type we set, we could access to different kind of parameters here on this dialog box. Okay, so for instance, in this case, the angle will define, for instance, the angle of the cone. So this is more narrower. Okay. And this is something we can change. For instance, here in the laser beam, we can set here this to 0.5, and then you will see that this is longer. Okay, you see here 0.6. It's longer. Okay, so it detects farther. Okay, so this is how do they work, and the important thing here when working with proximity sensors is that they only detect detectable objects, and this is a property that depends on each of the objects. So if we access here to the object and we go for the common properties, all of them should have the detectable property on. If you see here, all of them are on, okay, and are detectable. In particular, also in addition to that, we have the option to specifically set which kind of sensor we would like to detect or be detected by. Okay, in this case we can or by default we always activate all of them, but we can set a specific simulation so they are only active for a specific type of sensors. Okay, depending on how we want to perform our simulation. Okay, so let's start with the simulation. Let's run it, and you can see here that in this case, both all of sensors are detecting the object, and this is indicated by this flashing black-yellow line here, and it's detecting the minimum distance to the object. Okay, the way or the value for that distance, this is something we can get through scripting, coding, and this is something we will explain in a different video. Okay, not in this one, but here you can see at least in the simulation that is successfully detecting the object. We can, for instance, move an object, like in this case that one, and if we put it far enough, it will stop detecting. Okay, so it's not detecting anymore. So the object, it's outside our range. So we can put it here and will be still detected. Yeah, but if we put it there, it won't be detected. Okay, we can do that also for the laser. So here is not detected, here is detected. Also here, even if it's too close, it's not detected anymore. And here will be detected. This is something we can set this is an offset distance, and we can play with, specifically with ultrasonic or infrared sensors. Sometimes they have this offset. Okay, and thank you very much, and I hope to see you on my next video. Hello, in this video I'm going to explain how to configure vision sensors in CoppeliaSim VREP software. So the idea is that if you want to add a vision sensor, what you have to do is to access to the add menu and then go here for vision sensor, and then you have two different type of sensors, the orthographic type and the perspective type. Okay, the main difference of those sensors is the in this case the rendering volume that you use in order to detect your your objects. And here, for instance, this is the orthographic sensor. You can see here this is a rectangular shape, and the perspective sensor, which is that one here, is indeed a trapezoidal shape here. Okay, so it's a perspective sensor. It's like a regular camera. Okay, so the important thing with vision sensors is that they will render any object on the scene that have the renderable property enabled, and this is something that by default will be activated. So if you access, for instance, for the properties of a specific object like this one, the blue one, you go for common properties, and then you have the renderable properties here on, which means that will be seen by the default. By default, it will be seen by the sensor, and also it's a condition that obviously the object has to be visible. So if we deactivate this layer here, will be invisible also for the vision sensor too. So it has to be visible in our scene. Okay, so as I said, any renderable and visible object will be rendered by this sensors as long as they enter inside this trapezoidal or rectangular shape you can see here. Okay, if nothing is there, like for instance right now here the situation for the orthographic sensor, there's no object there, there's the infinity, then it will render with the black color, as we will see. Okay, so now let's go for the properties and to see how we can set them. Okay, so let's start with the orthographic sensor. If we double click on it, we can see that we have options, for instance, to set the near and the far clipping planes. So this is defining where the sensor will be focused, and it's rendering proper objects. Also, we have here the ortho size, which is basically the size of this rectangular shape. And if, for instance, we can modify this and we can make it bigger. Okay, we can set it backwards to the previous value. And also we can use, or we can set this resolution to determine which is the amount of pixels on the X and Y coordinates of our image. Okay, so this is something we can easily change. Okay, so and now if we go for the perspective sensor here, that one, it's basically also has the same properties. They are basically the same properties. We have the near and the far clipping planes as well, but in this case what we have is an angle. So instead of the size of the orthographic size, what we have is a perspective angle, and this will make the angle could be narrower or wider, and this is related with the optics of the camera you're using. And also you can have, or you can set here the resolution as well. Okay, in this video I'm not explaining how to process or how to work with the images that we get from the vision sensors. This is something we will see in a different video. Right now I'm only interested in seeing or showing you how these vision sensors are providing an image. Okay, so in order to do that, what I have done is I have created two floating views here. This is something we can easily do by just simply right click here and add floating view. Yeah, okay, this is the floating view, and floating view could be associated to the vision sensor. So in this case we need first to make sure that this vision sensor is activated. So for instance, if we want to see the vision or the perspective vision sensor, we have to click here and then right click here, go for view and associate view with the selected vision sensor. This will indeed render whatever this sensor is showing, this will render it here. Okay, indeed this is what I have here. I have a floating view for the orthographic sensor and also a floating view for the perspective sensor. In this simulation I have just simply created a very simple scenario in which I have three colored objects that I'm just simply shifting forward and backward in front of the sensor, so you can see how this works. Okay, so let's run the simulation, and as you can see here we have the orthographic sensor. Whenever an object is in front of the orthographic sensor we can see the blue, red and green, and also we can do the same thing with the perspective sensor, which is the blue, red and green. The main difference here, as you can see, is that, for instance, the orthographic sensor, there are moments in which there's no renderable object in front of it, and that's why it's rendering completely black image. And in here we are rendering part of the ground. You see here the floor, but the rest of the image will be rendered black because it's in the open sky. Okay, so there's no object there and there's nothing to render unless an object, these planes pass just right there. Okay, well, I hope that with this video you have a clear idea how to work with vision sensors, and as I said, we will explain in a different video how to process the image we get from these sensors. Thank you very much. Hello, in this video I'm going to explain you some of the fundamentals when programming in Lua, especially focused in order to create robotic simulations using the CoppeliaSim software or VREP. So these are the aims of the presentation. First, I just simply try to make you understand the basics of the Lua syntax. Also I will show you some of the keywords and the arithmetic operators, relational operators, some math functions and so on. And the idea is basically to learn Lua from very simple examples, okay, with 5 simple examples in which you will get used to that language, and also you will learn more whenever we see more videos and more examples when programming in Lua or programming in Lua in more advanced features. So the Lua is an interpreted language, which means that it's a slow language. It's actually based on Z, but it makes things easier. Okay, so especially when handling with memory and things like that. Okay, and it has different type of data, especially the nil value, which is something that it has no value indeed, and Boolean, a number, or you can use strings or even tables, and you can just simply declare a variable by doing an assignment of that variable, so you don't need to pre-declare it in advance as we do in C language. And for instance, Lua also accepts, when calling a function, accepts variable arguments, especially this is an interesting feature if you use multiple arguments on the output, you will see that. And just to remark that Lua, it's an extensible language, which means that it can include additional libraries to extend the features. So these are some of the keywords of Lua language. So this is, for instance, we will use, for instance, true constant for booleans or false constant. We can use, for instance, as well the for keyword, as well do and end together to create loops, or if, then, and then end again, or even else if to create more cases if we want to make some decision making. And for instance, also we can use the keyword local to declare local variables. And also we have keywords, for instance, in order to perform Boolean operations with and, or not. Where is it? Not here. Yeah. And also, for instance, when we work with functions, we will work with function keyword and also the return keyword. And yeah, this are some of the arithmetic operators that we will use in Lua. They are quite common and very similar to the ones we use in C. It's the plus sign, the minus sign, we have the multiplication and division, and then we have this operator here. It's actually performing a division, and it gives us actually the remainder of an integer division. And we have here to create an exponent operator, and also the unary operator to change the value of a given number. So also we have relational operators to compare numbers, and this is quite simple as well, because we have this double equal sign here to compare if two things are equal or not, and then it returns true if they are. This one is actually if they are not equal. This is if they are greater, smaller than, or greater or equal than, smaller or equal than. And finally, here we have some logic operators like AND keyword to make sure that two things will return true if both of them are true. Otherwise, it will return false. This is the OR keyword, which will return true if one of them is true, but it will return false if both of them are false. And the NOT keyword that will negate the value. And these are some of the functions or math functions that we will use over the examples. And they are indeed based on a math library that is usually integrated in the language. And as any library in Lua, you have to access to the library using the name of the library. Like in this case, in order to create or to access to, for instance, the absolute value, you need to access to it with math.apps, which is the name of the function, and then provide with whatever input arguments this function requires. Okay. So I'm here just highlighting some of the most important ones, like the ones for trigonometric functions like arccosinus, arcsinus, arctan. This is also the arctangent with two arguments, so it's in 4 quadrants. Cosinus, also the sinus here. Here we have functions for converting from radians to degrees and degrees to radians. We have the pi constant as well, the tangent. We have also, as I said, absolute value, exponential, logarithm or square root. We have functions to compute the minimum and maximum of numbers, to do some rounding like ceiling and flooring operations, and also to get the remainder of values, and also to obtain random numbers like these ones. Okay. So the documentation for these functions, it's something more specific, and you can access to that if you Google it, and then you get more information if you don't know how to use them, but they are quite standard. Okay, so now let's move to the examples. So let's start with this very simple example in which what I'm doing here is declaring a variable which is called name, and this variable equals to a string constant which is James. Okay, this is the first line here, and then I'm showing I'm showing a text on the console, the Lua console, and in particular, what I'm doing is I'm declaring, or I'm using this string variable here, or this string constant here, sorry, and I'm using this operator to concatenate two strings. This actually could be valid to concatenate a string with a number or a string with another string and so on. And this is useful, for instance, whenever we have something that changes like a variable, and then we want to show different values with that, and then here in this example it will show in the console, hello James. Okay, in this second example I'm declaring a function which is called sum. This function has two input arguments, a and b, and I'm returning actually the sum of them, so it's a plus b. And this is where the function it's been declared, and then in the rest of the code I'm declaring two numeric variables, var1, var2, and then I'm calling the function, so I'm using the parentheses and with the same number of arguments that this function requires, and I'm assigning the resulting of this sum to a new variable which is called result, and then I'm printing the result. Okay, in this other example, I'm just basically computing the minimum and the maximum of two numbers. So the function, I'm also declaring a function. It accepts two numbers as well. And in this case, I'm just simply doing a decision, or I'm making a decision in which I'm comparing the numbers. If A is smaller than B, then I will return, and then you have to take a look to that, I will return two arguments, A, B. This is the way we use in Lua to return two output arguments. Otherwise, I will return B, A. So then I always return on the first argument the minimum value, and on the second argument I always return the maximum value. And indeed, this is what I'm doing here. I'm declaring two numbers again. I'm calling the function with the two input arguments, but here, if you look at that, we have a new variable which is called minval and a new variable which is called maxval. And these two variables, this one will always have the minimum value and this one will have the maximum value. And this is what I'm printing there. In this example, I'm indeed declaring a table. I'm doing that in a variable which is called A. And in indeed, this table is indeed contains three different tables. As you can see here, in order to declare tables, we use these brackets here. And tables could contain any kind of number, even strings, any kind of object. Okay, so they are very flexible. Although we usually will use standard tables like in C, and we could, for instance, use them in order to store matrices, like I'm doing here. Okay. Indeed, as I said, this table here is storing three different tables, 1, 2, and 3. And each of these tables, it's storing and could have different variable length, in this case 3 numbers with zeros. Then I'm doing a for loop in which I'm iterating from 1 to the number of elements of A. This will return 3 because it has 3 elements. A has 3 elements, which are 3 tables, and then the step is 1. And then I'm doing a second loop to iterate over from 1 to the number of elements of each of the tables inside A, and this will return in this case 3 as well, and then with the step 1. And then if in this case, if the diagonal, if the element is on the diagonal, and then I'm assigning a 1. Then in this last example, I'm doing basically the same thing, but the difference is that I'm not declaring any kind of predefined matrix in advance with the amount of numbers I set. Okay, so in this case, it's an empty table, and I can do that just using this instruction here, and then I can do this for as many times as I want and declare in another table on each of these elements of this table here. So this is where I create new elements, and in this case is also another empty table. And again, I'm doing the second for loop, again in this case with 3 elements, and in this case, as before, if both I and j are equal, then I am assigning 1, and otherwise then I'm assigning 0. Okay, so this is the way I could assign the element I of the variable A, and then inside that element I have another table, remember, with the element j. Okay, so in this example I have shown you some of the basic programming concepts within Lua. Thank you very much. Hello, my name is Leopoldo Armesto, and in this video I'm going to explain how to program with the CoppeliaSim software VREP API, application programming interface, specifically with the language Lua, okay, which is the language that comes by default with the educational and free version of VREP software. Okay, so let's start by understanding how programming scripts work. Okay, so any object in my scene could have a script or a code attached to it, and this code will be executed depending on certain conditions. Okay, so first of all, let's create an object not specifically with a given purpose, just simply because we want to associate or show how to associate a script. Okay, so let's just simply create a cuboid here. And now what we need to do is to create the script. Okay, so you can do that by accessing to the Tools menu, Scripts, okay? And then here you have, by default, you have already created a main script. This is the script of the scene, and you shouldn't access or you shouldn't touch this screen unless you know what you're doing, okay? But this is the one which is created by default. Now, if you want to create your own script, okay, what you have to do is insert new script, and here you have to select the script type. There are 4 different type of scripts, okay? The most common one that we will use will be a child script, the non-threaded version, okay? This is because any object of my scene will be a child, and we usually use the non-threaded version because it's much easier to use, and that implies that basically that the simulation software is controlling when each of the scripts are executed, okay? So we don't have to care about if it's running on a different thread or than our simulation script. Threaded scripts will be only useful if we want to, let's say, exploit our capability or computational resources that we need to do something in parallel that takes some time, for instance, okay? But the default script that we will create will be a non-threaded script, okay? So let's click there and accept it, okay? So as you can see here, it's a non-threaded child script, and right now it's unassociated. So it means that this script won't be executed unless it's associated to a specific object, okay? In order to associate it, we need to just click somewhere else, click again on the script, and now we have these options enabled, and we have to select the cuboid object. Okay, now it's associated to the cuboid, and as you can see here, now the cuboid has an icon indicating that has an associated script to it. Okay, so this is the way we need to create the script. So now we can close this, and in order to access to the actual script, we can, for instance, double click here, and this is the actual script associated to this object right now. This is the standard or the default code that we will get whenever we use a child non-threaded script, and it's based on Lua, as I said, and this is something we already seen in a different video. But basically what we have right now is we have 4 different functions that will be called by the software depending on the given or the current situation. Okay, the first one will be used to initialize your code, and this is executed once at the beginning when you click run on your simulation, and this is something we usually in here we usually put code for getting, for instance, hundreds of objects, initializing values for specific variables or things like that. Okay, then we have two functions that one will be called whenever we need to update information about sensors, for instance. So we need to get information from our sensors, and we need to read those sensors and store that variable or that data in a variable. And there's another function in which usually we set the target values for our joints, let's say in order to move to a position or to have a target velocity or whatever. Okay, and there's a fourth function that will be called when we stop our simulation and we need to do a cleanup of our let's say environment and restore something we have changed, and this is something we can do here, but usually in our examples we don't put anything here. Okay, so in order to know how to program with CoppeliaSim or VREP using Lua, there's a complete API, okay, describing a lot of features, and you can access to the documentation of this regular API if you go here to this URL you have in here. Okay, this is a web page which is fully documented. It's mostly intended for, let's say, as any API for developers. So now, right now you are a developer, okay? And you have two options. You can access to the API in an alphabetical list or listed by category, okay? So let's access by alphabetical, that's in mind. Here, the only thing I want to show is that you have a full set of functions, okay, that you can use in your software, and it's really huge, okay? So the idea is that in the following videos, we will see how to work with these functions, let's say step by step, depending on the situation. If we want to move a joint, we will explain how to work with a proper function to move a joint and so on, okay? So this is a complete list of functions. So I recommend you to really take a look or a look to them and to try to understand how they work, okay? So for instance, here, one of the most important ones, or the first ones that we will use, will be the function sim.getObjectHandle. This function, it's used regularly to obtain handles or pointers of our objects that exist in our sim and that we want to use in our code, okay? Indeed, if we click here, we would go right there. So it's exactly the same function. We have the documentation how to use this function, and it's quite clear, or it's relatively easy to understand, okay? So you always have a description about the function. Here it says that retrieves an object handle based on its name, which means that you get a handle, which is basically a number, based on the object name that you have in your scene, okay? So usually we will have the synopsis when working with C and the synopsis when working with Lua language, okay? In our case, we are focusing on Lua language, which is this line here. So as you can see here, how to work with this function is rather quite simple, because we have sim.getObjectHandle, and then we have a parameter which is called object name, and it expects a string, okay, and returns a number, which is indeed the object handle, okay? So, and then we have to take a look to the Lua parameters and the return values. In this case, and this is quite common indeed, the description for these Lua parameters and the return values are the same as a C function, okay? So if you go here, so the C parameters, we have the object name. This is the input parameter that we have to indicate to our function. And in this case, it's just basically the object name with a string. Okay, so it's just a string with the object name. And what it returns is a handle of the object. And it gives you the return information, it gives you -1 if the operation is not successful. Imagine that we type incorrect our name of the object, then the object won't be found, and then we will get a -1, which means that if we try to use this handle for different functions, it will fail. Okay. Okay. So in this video, I've just briefly explained how to work with a regular API in Lua using CoppeliaSim software. Thank you very much. Hello. The purpose of this presentation is to show you, or to explain how to control the velocity of a joint in software CoppeliaSim vrep, and for that purpose I have just simply created a very basic scene that I'm going to explain, and we're going to do that by scripting. That means that we are going to use the regular API of Lua that we have available in the software. Okay. So first thing, just simply I have created a base cuboid, okay, which is acting as a base. Then I have a joint, which is called revolute_joint. This is the default name. And then I have another cuboid, which is actually with the shape of a bar. Okay. And this example, as you can see, if we access to the dynamic properties of the objects, so this bar here is dynamic, okay, which implies that in order for this simulation to properly work, the joint needs to be in torque force mode or any other mode with a hybrid operation mode enabled. Okay, so Indeed, if you access to the dynamic properties of the joint, you will see that we have a motor attached to it, so it's actuated, okay? And by default, the target velocity is 0, okay? So it will be stopped unless we modify this target velocity in our code. That's what we are actually going to do that, okay? The control loop is not enabled, means that we are not doing a position control right now with this joint, okay? So yeah, this should be disabled, okay? So with that, I have created a script for you, and I associate this script to the base. This is the common thing to do. And if we access to the script, I'm going to explain how it works, okay? So first thing you see is that we are basically or only using the init function, because this is a very simple example, in which at the beginning what we do is we get the object handle of revolute underscore join object, which is this one here, okay? And this object handle, so this name has to match with this name here. And remember that I already mentioned this function here. This object handle will return a number, which is indeed the handle. And this number is something internal of the program. We don't care about the number itself. It's something that the program needs in order to properly, let's say, modify the velocity, okay? For instance, if we go for the next instruction here, what we're doing is we are setting the join target velocity. So actually we are modifying this target velocity parameter that I showed you before, and we can see exactly how this instruction works, okay? So if we right click there and we click on open reference there, we have this documentation about this instruction here, and it's basically saying what I have already said to you. That is setting the intrinsic target velocity and works for non-spherical joints, means that it works for revolute joints and prismatic joints, okay, both of them, okay? And this command only makes sense when the joint is in mode torque force, okay? So that's exactly what we're doing, okay? And if you take a look to the synopsis, this function here expects two numbers indeed. The first one is the object handle. That is the joint handle that we are going to set the target velocity. And the second one is also a number and is the target velocity. And the description of these parameters is actually, as you can see here, described in the C description of the parameters. So first one is the object handle and the second one is the target velocity. And this target velocity could be the linear velocity if we are using a prismatic joint, or the angular velocity if we're doing a revolute joint, okay? So it depends on the type. And in case of revolute joints, the units are radians per second, while for prismatic joints are meters per second, okay? Well, this function returns a number. In our case, we are not using this number, but if something is wrong, we could always see if there's something wrong, because it returns a -1 after calling this function. Let's say that the joint is not in torque force mode, for instance, and that will return a -1, okay? So, yeah, okay. So with this example, we have everything we need right now to run the simulation, and we will see how it works, okay? So at the beginning, indeed, without our script, the bar won't move because the target velocity is 0, but we are setting at the beginning that target velocity to be 0.1 radians per second. So if we play run, we see that is spinning, in this case, counterclockwise, okay? We can stop and we can modify this and increase the speed, for instance, doubling it, and it's rotating faster, okay? And we can also reverse the rotation direction, so with a minus, so it will spin, in this case, clockwise, okay? So in this video I have explained you how to work with joints, or how to program joints that can be controlled with the velocity. Thank you very much. Hello, in this video I'm going to explain how to control the position of a joint in the software CoppeliaSim or VREP using the regular API based on Lua. As you can see here, we have a scene. I have created already a scene for you, which is actually very similar to our previous video in which we explain how to control the joint through velocity. As you can see, for instance, this object is a dynamic object, which is the bar that we would like to move. Okay, so it's a dynamic object. And this joint is also in force or torque force mode. And the difference is that now we have not only the motor enabled, so it's actuated, but also we have enabled the control loop. So now we can set the target position of our, in this case, the target position of our joint. Okay, by default is 0. Okay, and with this parameter here, we can set the maximum velocity we allow this joint to move. Okay, so this is also an interesting parameter. Okay, and okay, so now let's go to the script and explain which is the purpose of this this example. Okay, the idea is that the bar will be alternating in one position on another position every 5 seconds. Okay, so let's take a look to the script and I will explain step by step what I'm doing here. Okay, so first thing, in the init function, I'm just simply obtaining the handle of revolute joint, which is this joint or this object here. Okay, and I'm storing this handle in this variable which is called joint. Then I get the current simulation time in seconds and I store that in this variable here which is called last time. Okay, I do that because I would like to register or to do something every 5 seconds. Okay, and this is something we do here. I'll explain. And also I declare a variable. By default I started with false, in which I decide whether if I want to go counterclockwise or clockwise. Okay, so in the actuation function, this will be called every time the simulation is running. Okay, what I check first is if the current simulation time minus the last time I store is greater than 5 seconds in this case. So if that's the case, I set time elapsed true and update the variable last time with my current simulation time. This is a way to do, okay, if I want to do something every 5 seconds, then time elapsed will be true every 5 seconds and otherwise will be false. Okay, so you can see here. Okay, so next step will be, okay, now we have the time elapsed. So every 5 seconds, this variable here will be true, only for one iteration and then will be false. Okay, so now the idea is, okay, with this other variable, I can do the alternate mode, okay, in which I have, if this is true and this condition is true, then I set this to false and I call the function setJoint target position, which is actually quite similar to the previous function we saw, which was setJoint target velocity. Okay. Otherwise, we have to check again if the time elapsed is true, but this is false, and then we do the inverse logic. Okay. So that's how it works, this alternate mode. So now let's take a look to the setJoint target position function. So indeed, if we go to the reference, we have it here. It basically says that it sets the target position of a joint if it's in torque force mode and also motor it's enabled and the position control are enabled. Okay, so we need to make sure these things are correct. Okay, and what this function expects is a handle, exactly as the previous function we saw, the sim set target velocity. So this is the joint handle and expects a target position. So these are the two parameters. So it's the joint object handle and the target position, which could be a position in meters if we have a prismatic joint or a position in radians if we have, in this case, a revolute joint. Okay. So that's why, because we have a revolute joint, that's why I'm providing here 90 degrees but expressed in radians. So I'm just doing the conversion from degrees to radians just by multiplying with this number, which is pi, which is a constant which is defined in Lua by default, math.pi, divided by 180. This is a conversion from degrees to radians, and then 90 degrees multiplied with this constant here will be actually a half pi, okay? And this is the same but with the negative number, so it will go to 90 degrees and minus 90 degrees. So let's run the simulation and see how it works. Okay, first it just simply waits 5 seconds until the elapsed time condition is met, and then goes to one position, and then after 5 seconds goes to another position. Okay, right now you can see the speed is quite slow, and almost it did not have time in order to reach the final or the target position. Okay, so if we want to increase that, we can just simply modify this and increase the maximum velocity that we allow this joint to move. Okay, or we need to increase the time. Okay, so we run it again, and after 5 seconds you see that right now the bar is moving much faster. Okay, after 5 seconds again moving much faster. Okay, so in this video I have explained how to control the position of a joint. Thank you very much. Hello, in this video I'm about to explain how to create graphs, even temporal series graphs, two-dimensional graphs or XY plots, and three-dimensional plots including three-dimension X, Y and Z. Okay, so I have just prepared an example. It's rather quite simple and similar to the one we previously saw regarding with controlling the velocity of the joint. I just simply added here an object, which is a special kind of object. It's called a dummy. This dummy is just an object that I will use to register the position. Dummy objects can be used also for the inverse kinematic module to set the relation or of the position or orientation between different kind of links. But this is something we will see in a different video. Okay, but particularly in this video, I'm interested in explaining about creating graphs in order to record or data stream. Okay, so we have to start by adding a graph here in the add menu graph. Yeah, and then we have here our graph that we have some options here. We can check or uncheck these things, and this will be the actual window in which we will display the graph. Okay, and we have time series graph and we have XY graphs as well. Okay, and yeah, so we can show them or hide them depending what we want. Okay, during the simulation or not. Okay, so how graphs work are rather quite simple, because we have to access to the properties of the graph, and then we have here a data stream recorded list. This will be the list of variables that I would like to register or to record in order to display my graphs, let's say with a time series or the XY graph or whatever. Okay, so for instance, let's say we can add data stream regarding with positions and orientations of objects in my scene, but also whatever interesting variable about joints, also about any kind of sensors like proximity sensors and everything. Okay, so what you have to do is click here, and then here you have the data stream type, and here is where you select exactly what you want to register. As you can see, there's a huge list. Okay, in this example I'm just basically interested in the absolute X position of the object. Okay, so I'm just selecting this thing here, and then the object I'm interested in, which is the tip. Okay, so I register this stream, and then I change the name and I rename it as X here. And then I do the same thing with the Y absolute position of the same object. Okay, and then I rename it here. Okay, So then on every data stream, I can apply specific transformations, let's say to scale it or to apply some kind of offset. And also I can decide if I want to be visible or if I want this data stream to be visible on the time graph here, okay? And also if I want to show the label, and if I want to link any of the points I'm registering, okay? So it's a continuous line, okay? I can obviously modify the color of the curve, so I can set, for instance, the x coordinate to be blue. Yeah, and so this will be blue, and this will be by default red, okay? In order to apply the changes, we have to check and uncheck this thing here, okay? So we see the updates here. Okay, so if I run, or if I press the play button here, you will see that we have here the time plot or the time graph that we have created. Particularly, we are registering the X and the Y position here, okay? And you can see it has this sinusoidal aspect as expected, okay? So this is one thing, but then we can also create XY graphs or 3D cubes, okay? So with XY graphs, it's rather quite simple as well. So we can edit it here and add a curve we want to register based on the data stream we have here. So we have to select for the X coordinate which variable or which data we want to register, which is the X in this case, and for the Y we want to register the Y. We accept that. We can modify as well the color, so we can leave it like that, whatever, okay? And then here, I close this thing here, and in here, I will have, if I even select this thing here, I will have, let's for instance uncheck the label. Yeah, because it did not finish before, okay, yeah. So now if I click on the play, I have the XY graph that is being created, and as you can see, it's obviously working properly, okay? So this will complete the circle once it has completed the full turn, okay? So also, let's stop it, okay? Also, I can create here 3D cubes, okay? The difference with 3D cubes is that they will not be displayed here in this window here, but they will be directly displayed on the scene that we have here. So in order to generate 3D cubes, okay, let me first register another stream object, will be the Z position of the tip. And let's rename it with Z. Okay, so now I can create a 3D cube here and add a new one, and register again X with X, Y with Y, Z with Z, and set whatever I want here. I can increase the size I would like to display, and also the color, whatever, let's say green color, whatever, okay? And then I accept all the changes, and then I have a 3D graph right there in my simulation. You can see that it's working properly, okay? So I can use it in order to trace the movement of a specific object, okay? So thank you very much. Hello. In this video, I'm going to explain how to create a Dyer robot from scratch. It's a mobile robot, low-cost mobile robot that actually I have an online MOOC explaining how to program this robot and also to design it. And we're going to do that in order to obtain a robot simulation, and then after that, then we will have more lab exercises playing with this robot, okay? So first thing you need to know is that we have a set of files in the video description that you can download in order to create the robot, okay? So We are going to start by importing the robot mesh files. So we can do that if we access on the file menu and then import mesh. And then we have to look for the files. These are some of the files that I provide you. And let's start by importing the robot base, which is that one. And whenever you import a mesh, in this case, because of the some scaling issues, we need to, they were in millimeters and here accepts meters. So we need to use this scaling here. I also recommend to select Z as the up vector. And then we click import. And here we have, if we zoom it like that, yeah, here we have robot base. Okay, of the robot. So this is something that we have just imported. We can put here a name called base, for instance. Okay, and we can do the same with more files. You will see easily how quick we can have the aspect of a robot. Let's import the front. Again, this is 0.001. And Z there. Okay. And this is another one, so that will be front. And we can also import, for instance, let's just do a few more, okay? Let's import the wheels, so it will be the left wheel, for instance. Yeah, there, and so on. Okay, so we can just by importing the appropriate meshes to our simulation, we will have the robot with a given aspect. But this is still not a robot. Okay, there are a lot of steps we need to do in order to have a proper robot simulation. Okay, so just before in this step, what I want you to do is I want you to access and import all the shapes and adjust the color to whatever color you want. This is something we saw before. So you can just simply adjust it something like that, for instance, whatever color you want, okay? And this is something you have to do with any component you have. For instance, wheels are usually black. Here, so we have this, and so on, okay? And there's one special component, yeah? All these things are meshes, but there's one special component which was, or that included more advanced things, that it is indeed a model. A model is indeed a collection of objects that has been created already with VREP. So this model, it's related with the LED matrix, as you can see here. This is the one I'm providing you, and this is the model. And the model, you will see that indeed it's a collection, as I said, of objects, and it also has a code attached to it. Okay, I did that. Yeah, let's just shift this is the front. Let's properly set the X component. Yeah, there. Now it's centered. Okay, yeah, this is the model, and the idea of this LED matrix is that it was a complex object to create for you, so that's why I create this model and I'm giving it to you. And just to mention that this is still not a robot. This is just, or it will have, once you end this step, the shape or the aspect of a robot, okay? So in further steps, we will actually provide a proper hierarchy, proper objects to implement the dynamics, the collisions and sensors and so on. Okay, so I hope to see you in my next videos. Thank you very much. Hello, so now we are supposed to have, as I said before, the aspect of a robot once we have imported all the meshes here, as you can see. Okay, so this is a robot, but still it's not a robot because we have no, as remember that I explained before, we don't have any kind of geometry or pure geometry in order to compute the collisions and so on. Meshes are not the best way to make objects respondable against collisions and also to implement the dynamics and so on. So in order to do that, what we are going to do is for each of the components here, well, not each of them, but basically the robot base front, these arms here, so these Lego parts here we have as a gripper, and also for the wheels, left and right wheel, and also for this caster wheel here, okay, we need to create pure geometries based on the shape of these existing objects, okay, and this is rather quite easy. Okay, so let's start by creating an object with the base. Okay, so in order to do that, what I suggest is you double click on here, you go for common properties, and then you check this object to be in second layer 2 visible, okay, and then you access here to the visibility layers, and then you disable the first layer, so we get only this object here, okay. And now once we have this object here, this is to make things clear, okay, so once we have this object here, the idea is to edit this mesh and create a cube from this mesh. So we can do that from here, so we have to go for the shape edit mode, and we can do that by clicking here, and as you can see, this is the mesh. Mesh is basically a set of triangles properly, let's say, put together, and this is a mesh. So the idea is if you click the shift key and then click and select all the triangles of the mesh, okay, all of them, we have an option that we can extract a cuboid from the selected shapes or the selected triangles. So if you click there once, important thing is that we set the object to be dynamic respondable and especially to be a pure shape, otherwise it will be a convex shape, okay, so we want to be a pure shape, and we click OK, and we can exit from this mode. Sorry, yeah, here it is, and that's the cuboid, okay. If you go for the cuboid and double click on the common properties, we are going to put this cuboid on the ninth layer, okay, that one here, because we want pure objects to be invisible for the normal aspect of our simulation, but to be accessible whenever we invert. Now this will be our robot, and whenever we invert, we will have our cuboid here, okay. So the idea is that you do the same thing with, as I said, the wheels, the arms, and the caster wheel. But for instance, this shape here, let's do it with the left arm, okay. If we create a cuboid from that, it will actually create a cuboid with this shape that you see here in white, okay, and we don't want that. We would like to create two separate parts here, so we can do that by again accessing to the edit shape mode and only selecting the ones which are, we click shift, only these ones are selected, and we create one cuboid from that. That's it, and that's the cuboid, and this is the cuboid, and we can put it on the other layer. So this is what we have created, and also we can do the same for the wheel, but in this case it's not a cuboid, it will be a cylinder. So this is the wheel, so I click shift, I select all of them, sorry, shift, I select all of them, yeah, and then I extract a cylinder. That's it. I exit this mode, and then we have here the cylinder, okay. So remember to rename with proper names like base, pure, or whatever name you want to use, okay. And this cylinder will be visible again in the layer, the bottom layer. Okay. That's it. Okay. Yeah, so you have to complete the steps in order to do the same thing with the other arm, with the other wheel, and also with the caster wheel. The caster wheel, again, it's a complex shape that we will, let me focus on the caster wheel. It will be here, base, for instance. The caster wheel, we can create, especially with this side here, this part here, we need to create 3 pure components, one here, one on the side, and one on the other side. And we have to create a cylinder for the actual caster wheel. Okay, thank you very much. Okay, so now what we have, or what you should have already, is these shapes created as I indicated before. Okay, so remember we have a base, the front, 2 arms, but right now they are these parts here, so they are different objects. Okay, and if you run the simulation, indeed, this is something we haven't done before, but if you run the simulation, you will see that obviously this is not working yet and it will fall apart. Okay, so if you play click, it will fall apart. Okay, but most importantly, for instance, the base and the front, they are supposed to be attached, as well as these 2 parts here are supposed to be the same component or the same object, and these 3 here in the caster wheel, the one on top and the 2 on the sides, are supposed to be the same object. So what we have to do is to group them. Okay, so in order to not to fall apart, because they are respondable objects, and if they are individual objects, they will respond one against each other, and we don't want that. We would like to be just one single solid. Okay, so in order to do that, we select the base, we click shift, we select the front, we have both objects. We could do the same here. Okay, and we right click and go for edit, grouping, and then we have group selected shapes. And you will see that now we have one single shape, which is front, and well, we can change the name for that to robot. And that shape here, it's one single object. Indeed, if I run the simulation again, you will see that compared to the previous simulation, these 2 objects right now stay together. Okay, so we can do the same thing with this object here and this object here, so we can group them again, edit, group merging, group selected shape, and this is the new object. And now if we play simulation, you will see that these 2 objects stay together. Okay, and yeah, you have to do that with the other arm, we have to do that with the caster wheel, and in addition to that, also in particular, we have to edit some of the dynamic properties of the object, particularly the wheels. Okay, so if you access to the wheel properties, the dynamic properties here, yeah, in order to make the simulation more realistic, we need to edit the type of material. So we especially edit some of the coefficients that are related with the friction against the floor. So we can do that by just simply editing the material and apply some of the predefined settings we have here, like high friction material. This is something which is convenient in order that our simulation is more realistic whenever we assemble everything together. Okay, so we have to do that with that wheel, the left wheel as well, and also the caster wheel. So the wheels in the contact in the ground, they need to be, or they need to have a high friction material. Okay, thank you very much. Okay, so now in this newest step, the idea is to include or add our joints to our simulation. Joints will allow us to, for instance, move different kind of objects like the gripper or the wheels and so on. So in this particular robot, we have joints for the left wheel and the right wheel. We have a vertical joint here that will make the caster support to rotate. And also we have a horizontal joint here that will the actual caster will spin. And we have also two, in this case, two vertical joints here that will be for the grippers. So they will be actually related with the servos moving the gripper. Okay, so let's start by creating a simple joint. So let's add a joint here, a revolute joint. All joints are revolute in this robot. Okay, so let's add a revolute joint. Yeah, let's move the joint to the proper layer. Okay, that one. Yeah, and that's the joint. As I said, the size of the joint is not that relevant, so I used to make it quite more smaller, like that one and that one. So it will be just a small joint like that one. Yeah, or maybe even that one. Yeah, small joint. But if you take a look to the joint, let's zoom. Okay, if you look at the joint, it's vertical, and we would like to attach a joint here. So the joint is just an axis that makes this wheel spin. So we need to rotate it, and if you take a look, we need to rotate it on the y-axis of the joint reference frame. So we go to the orientation, rotation, on frame, and then we select, this is a positive 90 degrees rotation, and that will make the joint horizontal. Okay, and now we want this axis to be just right in the middle of the wheel. So in order to compute where the wheel is, or to know exactly where is the center of the wheel, remember that we have a trick in which we select the joint, and then we have, if you click shift and select the wheel, yeah, and then you go for position, you can set the y coordinate to be equal, and in this case also the z coordinate to be equal, and the x coordinate to be equal. Okay, this would actually take the same effect as applying this or pushing this vector, this button there. Okay, so that's the joint. Okay, that's the way we want the joint to be. Okay, so we have to do the same thing with the other wheel, and also here with, in this case, a vertical joint. For instance, let's add a new one for that's the new joint. Let's move it to this layer here. Let's change the size. Okay, and let's make this joint to be exactly right there. So we want to be right there. Yeah, that's the correct position. We can put it upwards if we want, but that's fine. Yeah, and we have to do the same with the caster wheel here. Okay, and we have to do the same with the servo ones, but the servo ones is a special case. Let's switch to this view, because we don't have a center. This object here, we have the center is right there. Okay, but we want the axis to be right there. Okay, so in order to do that, we need to create an auxiliary or temporary object from the servo shape, and that's rather quite easy. We select the servo, we go for the shape editing mode there, we click shift, and we select those triangles there, and we create or we extract a cylinder. That object will be temporary. Okay, something we use in order to actually to get the correct position of the joint we want. Okay, so now where's the cylinder? That one. Okay, this is the cylinder. I'll just simply move it on the other layer. So now I invert the layers. So here it is. That's the cylinder. You can see it. Okay, so now we have an object there exactly where we want. we can create a joint and place it exactly in that place. So we have to add the joint, again a revolute joint, we change the layer, there it is, and we reduce the size, there it is. So that's the joint. So now we have to select Shift or click Shift and then select the object we want, where we want to move it, and then we can just simply apply. Sorry, I have 3 objects selected. Let me undo. Yeah. So I selected the wrong one. So that's the joint. That's the auxiliary or sorry. This one and this one. Yeah, sorry. And then we apply it. There it is. Okay. And now once we have that, we can remove this cylinder here because we don't need it anymore. Okay. And just to conclude with this video, the next step or the next step we need to do in this video is to set the joints in a proper mode. Okay. So for the wheels, we have joints that will be controlled on velocity. The ones with the caster wheel will be in free mode. Okay, no motor attached to them. And these ones will be controlled with position. So we can set their standard servo so we can control the position of the grips. So in order to do that, this joint here, for instance, we need to access to the properties. By default it was created in a force torque mode, that's fine. But we need to enable a motor in order to be activated. Okay. But we don't need, in this case, the control loop enabled because it will be controlled by velocity. For this joint here, yeah, that one here will be in torque force mode, that's fine, and motor won't be enabled because it's not actuated, it's free. Okay. And finally, in this joint here, will be also in torque force mode, but we need to enable the motor and also enable the position control loop. Okay, the position control loop. So this is the proper settings for the joints in order to work with our robot. Okay, so please complete the steps and I'll see you on my next video. Okay, so if you have completed this step, this is the actual aspect that your robot will have. But still it is not a robot. There's one more step to, let's say, have a proper robot. Why? Because if we run here the simulation, you will see that indeed all parts still fall apart. That's because there's no hierarchy there's no hierarchy between the objects. So joints are not connecting the objects. And that's something we saw already or previously in a different video. So let's start by creating a hierarchy. So the key idea is that all pure objects like the robot base will be the parent of or the root of all objects. This robot here will drag or will include all other non-pure objects, like in this case that could be attached to them, like for instance in this case the diode base here, the front and so on. Okay, this is the idea, okay, to include all of them. Also we'll include the left joint and the right joint, which are the joints for the wheels. Okay, these two joints, this joint here will include as a child the wheel itself. So the wheel is, let me see, left pure wheel here, that one. So we have to drag it inside the joint, so to make it a child. And we have to do the same thing with the right wheel pure here and drag it inside the other wheel, okay, the other joint. And then we have, for instance, this joint here, let me see, this caster joint here. this joint here will be included in the robot, and then we have this object here, yeah, that one, which has to be included inside this caster joint, and then you have another joint which is the horizontal one, which is that one, yeah, and include the actual well inside, yeah. And you have to do the same for the servo arms, okay. So if it happens that whenever you play the simulation, still the robot maybe falls, let's say, because it falls upwards, because of maybe there's you have to adjust the mass of some of the components to make it, let's say, stable, because that could happen if these two parts here are actually creating an overweight on the front and could fall down, and that's not realistic because these parts are made of plastic and they are very light, okay. So maybe you need to adjust some of the dynamic properties to actually have a stable robot. Thank you very much. So now you should have, or you should get to this result. Actually, if we run the simulation right now, you can see we have a proper robot running and it's not falling apart, okay? So that's the correct way to have a robot, as I said. So now the only thing that we are missing is we would like to add two of the sensors that this robot has. It's in particular is a proximity sensor corresponding to an ultrasound sensor, so we have to add a proximity sensor here, cone type, because of it's an ultrasonic sensor. That's it. That's the sensor. So we can rotate it, in this case, along the x-axis. You see here the x-axis, so we have to rotate it 90 degrees around x-axis. There it is. So it's pointing forwards, and then we have to place it close to the, in this case, close to the sonar object there. So we select both of them and then apply the selection. There it is. And then we have to include it as a child, for instance, of the sonar. So whenever the sonar goes, it will also go the actual sensor, okay? And then if you right click on the properties, you can adjust the volume parameters. For instance, you can adjust this radius here will affect to this blue area here, so you can make it, if you want, slightly smaller, let's say. Sorry, no, this affecting, this is the range of the sensor, so that could be 0.8 meters, for instance. That's the range. And also we can modify, in this case, the angle, okay? So this is how to set the ultrasonic sensor. And also we need to include an infrared sensor to detect light here pointing to the ground, okay? And this will be actually done with a camera, a vision sensor, which is indeed, in our case, is an orthographic type sensor. It will be just one pixel pointing downwards, okay? So this is the default sensor that we have created. So we have to rotate it and make sure that we point downwards. So we can double click here once and two, and now we're pointing downwards, okay? Now the sensor is pointing downwards. And we can make it smaller, like this size here. We can put another 0, x, y, maybe 1 here. That's the object size, is rather much more smaller. We will see that soon. And we can make sure that we put it or place it right just where this sensor is. So we can put it there. And now we are going to zoom to see if it's correct. So yeah, that's because the detection parameters of the sensor Here it is. So we have to select 1 pixel resolution, and that's because the near and far clipping plane are too big. Okay, so let's make this much smaller and make this sensor is basically detecting 4 millimeters. Okay, not more than that. So it's 4 millimeters far away. Yeah. So if now we zoom, there it is. Okay. Still is not on the correct place because we set it on the center of the sensor, so we can just simply shift it manually by applying, in this case, for instance, positive translations with respect to its own y-axis of 1 millimeter. Okay, and now we shift it there. And to make sure that we are properly detecting things, maybe what we have to do is increase also the set coordinate with respect to its own reference frame. So that's the correct place for the sensor, for instance. Okay, and then we have to make it child of the actual shape. Okay, yeah, that's a possible shape for the sensor. Okay, so thank you very much, and next step I will explain you how to create a user interface. Thank you very much. Hello, in this video I'm going to explain how to create a user interface to command the robot to generate movements with the robot. So we could have, or we can have, a set of buttons and sliders, and the robot will move according to our user input. Okay, this is something similar we saw in the case for the LED matrix, in which you had some buttons and then you could see some expressions. The idea here is to generate a code to do that, and I recommend you to see the previous videos you have about programming in Lua, and particularly the API that the CoppeliaSim software uses in order to set, for instance, the velocities or the positions of joints. Okay, so let's start by seeing what we have here. I will access to the code that I created and I associated to the robot base here. So if I double click, this is the code. I generated a set of functions. I'm about to explain them, but first let's go to the syscall init function, this one here. Okay, and let's see what we have. Okay, so first thing we have is we get the object handles of the joints, particularly for the wheels and the arms, and then we have a parameter which is the wheel radius, is 3 centimeters. The maximum speed we want to move, this is something we can modify, and also the max turn speed. This is the actual speed and the actual turn. Turn is expressed in radians per second. And this parameter here is the separation of the wheels with respect to the center of the robot. This is called the wheel basis, and it's 5,65 centimeters. Okay, this is something you can measure. And this is a variable that we set in order to know if our grips, or if our gripper, sorry, it's open or closed. And the important instruction here to create a user interface is actually that one, simue.create. This is an instruction that uses a plugin which is by default added in CoppeliaSim to create an user interface based on Qt XML syntax, and this is exactly what we have here. It just basically requires a string. This is just one single string, okay, which has been separated into or broken into several lines using this concatenation here, so you can see it better. Okay, so this string basically requires a UE tag. This is a UE tag that it's closed right there at the end. So we open UE and then we close with /UE. Okay, and then it has a set of attributes. In order to define how we want this user interface to be. For instance, it has to be enabled so we can interact with it. If it's mobile, then it will block other windows. Then we have a title for the user interface. We can set if it's closable, what kind of layout we want for our, let's say, elements that we add in our user interface. In this case, it's a vertical box, so they will be added vertically. Placement relative, and this is the position we want. Okay, these are a set of attributes that you can obviously modify, and then we have a set of elements. For instance, here we have a label. That label includes the text linear speed, and then we have a horizontal slider that has a minimum value of -100 and a maximum value of 100, and then we have a callback function. This callback function will be indeed a Lua function that we have in our code that will be called every time there's a change on the value on this slider. And this function here, this is something we can define. It's a user-defined function. I call it onSpeedChange. And this function indeed is, as I said before, right there at the top of my code. And it accepts, basically this is the way it has to be defined. It accepts a UV handle. It accepts an identification, and particularly the thing we are interested in right now is on which is the new value. Okay, so based on this new value, for instance, we have two functions, on speed change and also on turn change, because there's another slider for modifying the angular velocity. And if we modify the speed, then we update the speed variable, and if we modify the angular velocity, then we update the turn variable. Remember that this speed and turn variable were set to 0 at the beginning. So whenever in this slider, I call the on speed change, or in this other slider here, I call the on turn change, these variables will be modified, okay? Then we have also a set of buttons. They also include a text, for instance, here, open, close, forward, backwards, left, right, stop. And each of them has also a callback function with the event on click. So whenever we click on the button, we will call a function that we specified here. For instance, move forward. Move forward is this function here. And this function basically, what it's doing is setting the target velocity for the wheels. So it's half of the maximum speed divided by the wheel radius, because remember that this set join target velocity requires the velocity argument in radians per second. Okay, so that's why we are doing that. In both wheels, left and right, we are applying exactly the same speed, so it will move forward. We can do the same thing for move backwards, but with the negative sign. Turn left will imply a negative sign on the left and positive on the right, so it will turn left. And then turn right the other way around. So it's positive on the left, negative on the right. And stop just basically 0, 0. Okay? And the last function I have created, sorry, not the last one, but a function that I have created is the move function, which accepts the linear velocity and an angular velocity. This function indeed was called in the callback functions for the sliders. Once we update the speed, we called the move function. And this move function is basically setting the target velocities for the wheels, but depends on an expression which comes from a well-known formulas for kinematics in mobile robotics, which is basically that the left wheel speed will be the linear velocity minus the separation of the wheel with respect to the center times the omega, which is the angular velocity. And for the right wheel, it will be the same thing, but with a positive sign here, okay? And then finally, we have a special button too, which is the open close button, which is checkable, which means that whenever we click on it, it will remain pushed, and then we need to click again to, let's say, uncheck the button, okay? This button here, it's calling the onGripper function, which is that one. And remember at the beginning that I said, okay, we need a variable to know if the gripper is open or closed. Okay, so that's the variable. So if it's open, then we need to close the gripper and then set it to open false, because now it's closed. And otherwise, we'll need to open the gripper and set gripper open true for the next time we click, so we know that we have to open it or close. And these open and close gripper functions are just simply calling a similar function. So instead of set join target velocity, here we are calling set join target position, because these joins were controlled by position, and we set, in this case, the degrees we want to set this joint, multiply with this constant here, which is basically translated degrees into radians, which is required by the function here. So for instance, in my case, I set 30 degrees here on the left minus 30 degrees on the right to be open, and to close the gripper I set minus 10 and 10. This is something you can modify, obviously. Okay, so once you have that, let's play with the simulation and to see how it works. Okay, this is the interface I have created, and then here you have buttons and the sliders, and we can click forward, we can click backward, we can stop, we can go for left, we can go right, or we can just basically modify the speed so it will go faster or even backwards. Yeah, and then also at the same time it's moving, it will rotate, so it's doing circles. Okay, and just to conclude this video, I would like you to take a look to the documentation regarding with how to create user interfaces. You have to access to this, in this case, to this URL here, and there you have all the UE XML syntax that you need with all the attributes and what they mean. And this is something you can obviously take a look if you want to modify or create different kind of interfaces. Okay, everything is described here, all type of elements and with their attributes. Okay, so I recommend you to take a look to this. Okay, thank you very much. Hello, in this video I will explain how to work with proximity sensors in CoppeliaSim VREP. The aims are therefore to understand the programming API in CoppeliaSim to access to the distance information provided by proximity sensors. We want to implement a robot control that allows us to establish wheels angular velocities based on the separation distance with respect to lateral walls of the environment. So for this purpose, we will use low-cost LiDAR sensors. In particular, we will simulate the VL5310X sensor. In addition to this, we want to adjust the speed of the robot and stop in case there's an object in front of it using the ultrasonic sensor, which is already included in the robot. So in order to succeed, we will need a set of computations that I'm going to explain, having in mind that the ultimate goal is to set the robot's wheel's velocity based on the distance we get from sensors. Therefore, the first thing we will have to do is to add proximity sensors as shown in the figure. On the one hand, we have the ultrasonic sensors that must be already included in our robot, and this is something I explained in the previous videos. On the other hand, we have to add 4 VL5310X sensors. They are stuck right on the robot's arm, so as you can see there, 2 on the left, 2 on the right, with a separation about 3 centimeters, and you have to approximately place them in a similar situation as we show here in this picture. Thus, we will include an object as an imported geometry from an ESTL file. This is a file that you can download with the link that we provide in the video description. So this is just simply the aspect of the sensor, but then for each object we will add a ray type proximity sensor, and in this case the configuration parameters for this sensor are rather quite simple. We have 5 centimeters offset, and the maximum detection distance according to the manufacturer is 1.2 meters. Remember that if we want the sensors move as the robot moves as well, then they must be children of the robot. And in fact, the most convenient hierarchy in this case is where the sensors are children of the imported mesh, and at the same time these objects are children of the robot arms as shown. Once you have the sensors, you must create an appropriate environment for the correct performance of this exercise. So in this environment, the robot must always stay or lay between two walls. So one on the left and one on the right. So the separation distance of the walls must be reasonably large so that the robot can move without colliding, but smaller than the maximum detection distance of the sensors, obviously. We provide you with an STL file with a wall geometry that we have created for you, and you can download it with the link provided in the video description too. However, we encourage you to create your own walls, even with simple geometry such as planes, or to create your own STL file with any suitable CAD program. In order to get data from a proximity sensor, we must use Lua code in a programming script associated to the robot main object. The first thing we should do is to, in the syscall init function, is to get the object handle. Here we show the case for the ultrasonic sensor, but we should do the same for the LiDAR VL 5310X sensors too. So we must, in this case, we have defined a maximum distance parameter where the sensor no longer detects an object, and we will use this to ensure that even there's no object detected, the function getDistance, the one you see here, will always return a value between 0 and the maximum distance. In fact, if we take a look to the getDistance function, we see that the sim or the function sim.read proximity sensor, it's called inside this function, and this is indeed the CoppeliaSim function that will allow us to obtain or to get the sensor distance. This function actually returns two output arguments. The first one indicates if an object has been detected, while the second argument returns the distance to the closest object or obstacle. So it is important to remark that we should not use the distance value unless the detected variable is equal to 1. Otherwise, the distance will return always a known value, okay, and this will cause errors for the subsequent calculations. So for these reasons, we actually, this is why we are actually always returning the maximum distance even when the object is not detected. So now we are going to explain how to proceed with the proper calculations in order to regulate the speed and also of the wheels. Okay, so let's start by establishing, let's say, the linear speed or the speed we want the robot to move forward. Okay, and in this case, we will need to get access to the wheel's velocity, or to set the wheel's velocity. So this here we show you the API in order to do that. So we again need the object handle for each of the joints, and then we need to call to the function set joint target velocity. In this case we have set it here 0, but this will be changed based on the computations we're about to explain. Okay, so as I mentioned, we would like to adjust the robot's velocity. So if there's an object in front of it, okay, so the working principle here is rather quite simple. So if the distance we obtain from the ultrasonic sensor is less than the minimum value, this is something we can easily set, then we want the robot to be stopped, okay. Otherwise, we make the velocity proportional to the measured distance, and in this case Vmax is the maximum speed in normal operations, that is when there's no obstacle detected. On the other hand, with the LiDAR sensors we can estimate the angle of and distance of each wall, the one on the left and the one on the right. Here we show some simple calculations that I'm pretty sure that you will understand, because basically it's computing the angle of a line and the mean distance using these sensors. So once we have the angle and distance of each wall, now we need to have some kind of error measure. So this error measure is something we would like to minimize. Okay. So for instance, we can see that a rough estimate of the heading error, that is the heading angle of the robot with respect to the environment, the walls of the environment, is a semi-sum of the angles of the walls, while the separation error is proportional to the difference between the right and left distances. In the first case, we want the robot to point to the same direction as the intermediate line, the one you can see here. We can think of a third fictitious wheel that will help us to point towards this imaginary line. Okay. In the second case, I mean in the separation error, we would like this line to pass through through the center of the robot. So we will use a measure in order to correct this wheel angle typically used in car-like configurations. So indeed, in order to have proper units, what I've said before is that the separation error is proportional to the distance, and this is indeed a totally arbitrary criterion, but it will help to compensate the angle of the third wheel, and therefore requires a parameter. Here I use the letter K that you must adjust. My suggestion is that you start with a value 0, and then you gradually increase this value to see if you observe that the behavior improves. Then, in order to obtain the wheel's velocity, the kinematics for this robot are well known, and therefore here I include the formulas that you will need to obtain the right and on the left and right wheels velocities based on this car-like configuration. As geometric parameters, you need the semi-distance of the wheel basis, which is the parameter B. In our robot is 5.65 centimeters. And then you also need the separation distance of the third dummy wheel. Okay, this is the parameter E, and this is something you must adjust. And just take into account that the larger this parameter is, the less correction you will have, but the control will be smoother. And indeed, if you make this, you set this parameter very small, this could make the robot or the control to be more prone to instability. Okay, so please set this value properly based on the behavior you get. Okay, and the last of the calculations you must do before applying the speed of the wheel is to convert these values into radians per second. And in order to do that, we need the wheel's radio, which is 3 centimeters in our robot. Okay, this is something required by the CoppeliaSim API in order to set the joints velocities. Well, in this video I have explained how to use proximity sensors with CoppeliaSim, and I have also shown you a set of calculations that will allow you to move the robot between walls. In the following video, I will show you how this is expected to work. Thank you very much. Hello, in this video I will show you how this algorithm that I have previously explained works. The idea is that the robot will move between the walls. So we have set the environment, as you can see here, and the idea is that the robot will move within the walls using the LiDAR sensors, basically. And indeed, we can zoom to these sensors to see how they are. We have them here, right in the robot's arm. On the left side and the right side, we have 1 or 2 on the front and 2 slightly behind them, and these sensors will detect the distance to these walls here. Okay, and we use the sonar sensor in order to detect if there's something in front of the robot and regulate the speed or adapt the speed to that. Okay, so let's zoom out and play this simulation. Okay, as you saw here at the beginning, there was a huge correction. That was because the robot was not right in the center of, let me just zoom out so you can see the rest of the simulation. So that was because the robot was not just in the middle, but so he detected that was the separation line was slightly shifted, so that's why he corrected that. And then after that, most of the time is basically in the middle of between the walls, and the corrections are done because the slight difference between the distance these sensors are detecting here, and this is used to estimate a line passing through the path we want. Okay, you could also see that sometimes the sonar sensor detects the walls and the robot slows down the velocity, and here it also happens, is slowing down, and then here at the end of our circuit, the robot will stop once we have reached the minimum distance we set. Okay, thank you very much. Hello, in this video I'm about to explain how to create paths and trajectory objects that we can use in our applications, for instance, to follow lines or to perform a kinematic control to follow that path or that trajectory with our robot. Okay, so this is in CoppeliaSim software we have a path object. This can be added here. If we click on Add menu, we select Path, and I usually select the segment type path. Okay, so this is the path object. Let's take a closer look. Okay, and this path object that we have created here indeed has 2 points, one at the beginning and the other one at the end. Indeed, these are called control points that define our path, and it also has, these are the blue ones. Okay, if you can see here, there's a blue box hidden by this red dot here. Okay, and there's also a red dot that it's a point that we can move along this path or this trajectory with a given speed, and we have specific functions in the CoppeliaSim API to access to some of the properties like the position and the orientation of this point in the path. Okay, and this can be used, for instance, to follow up trajectory, so we can try to pursue with the robot this point as a dog trying to follow or chasing something. Okay, so let's modify the aspect of the path. The idea is that we can generate an aspect or a shape that will actually look like a line painted on the floor that we can follow. Okay, for instance, in this case, what we have to do is double click on the icon, so we get to the access to the properties of the object, and in particular we are interested in the shaping and path shaping dialog. Okay, here, so we go there and we enable the path shaping. Okay, so here we select the type of path we want. I usually select the horizontal segment. Okay, and I set the size to 5. Okay, as you can see here, this is not actually horizontal, it's rather vertical, but this is because the path is not properly oriented, and that could be modified later on. Okay, we'll see how to do it. Okay, and also we can modify the color of the path if we click on adjust color and the ambient diffuse component, so we can modify the aspect of the path, let's say with a black line. Okay, so we accept, we close, and we close. We're done here. Okay, so now we have a path, but as I said, this is just simply a straight line, so we would like to have actually a very flexible path that we would like to follow. So for that we need to modify it or to include more control points in our path. Okay, so we can do that by accessing here to this option here we have, or to this icon here. It's the toggle path edit mode. So we need the path being selected, and then we click here, and then we enter into a mode in which we can edit, in this case, the path. So as you can see here, these are the control points of the path. As I said before, we have 2 of them, one here and the other one here. Okay, So in order to create more control points, we just simply need to do the combination of keys like Ctrl+C, Ctrl+V, and then we have another point here. And then we can move it. If we go here to the Object Shift dialog, with the point selected, then we can move it. Okay? And then we can just basically create more. So it's Ctrl+C, Ctrl+V. And then we have another one, and then we can move it. Ctrl+C, Ctrl+V, another one, and we can move it. Ctrl+C, Ctrl+V, another one, let's say that one here, okay? And one important thing about the path is that, as you can see, the control points, the first one, which is that one here, and the last one, which is that one there, the path always intersects these points. So it passes through these points. The rest of the points, the path will be approximated. This is because it's using a Bezier curve, and because of the properties of Bezier curve, these control points will be approximated, the ones which are in the middle. Okay, so that's why the path actually it's doing this curve here, and this is this curve here, and so on. Okay, and okay, so we're done with generating control points, and now we would like to set some path properties. In particular, I like to select the path flat option, so we make sure the path is flat. And also I like to click on the keep X up. This is because what I said before, the path is not properly oriented. So as you can see here, by default, the path includes some reference here that will give us how the path is internally oriented. Okay, this is something relevant for the point that it's about to move on the path, and this orientation here modifies the aspect in the end of the path. So I suggest to select the keep X up. So as you can see now, the X coordinate inside the path is always up. Okay, so the control points are always pointing with the X up, and that's because I suggest to use that because all of you will have exactly the same orientation. Okay, so this is an assumption, but you can do whatever. Okay, and the last option we can do, or the last property we can check, is this path is closed. So if we select it, the first and the last point will be no longer interpolated and will be approximated, and the path will be closed like that. Okay, so this is the configuration that I suggest you to use in order to create your own paths. Okay, so let's accept it, and now let's see what happens. Now we have a path. You have the control points, but the path is not properly rendered. Okay, this is something which was not the software did not behave like that in previous version. So there's a simple solution. We just simply need to save it and open it again. Okay, so it's like save like test, and then we close this scene and we open it again, and here we have our path properly rendered. Okay, this shouldn't happen, but yeah, you know, it's an easy workaround. Okay, so in this video I explain how to create and work with paths. Thank you very much. Hello, in this video I will explain how to work with vision sensors in CoppeliaSim VREP for line tracking applications. More specifically, the aim is to understand how does CoppeliaSim programming API work to get data from vision sensors. The goal is to implement a basic line tracking algorithm. So to do this, we need to create a path with the layout of the circuit, or the path we want to follow, and also I suggest to add a graph to see the robot's trace, so you can see the difference between the actual path of the robot and the circuit you created. In this video, we will simulate an infrared sensor TC-RT5000 to detect the color of a floor. In CoppeliaSim, this can be implemented with an orthographic vision sensor pointing towards the floor. This is something I showed you how to do it in a previous video. Here I just simply show you the main properties of the sensor that I used for my simulation. As you can see, we have a single pixel camera, okay, without depth. I'm ignoring the depth, so don't forget to include that option too. That allows me to detect a line on the floor less than 10 centimeters because of the far clipping plane property you see there, okay? And the width or the size of the sensor is 5 millimeters. As I said, you must create a path, so please watch the corresponding video on how to create paths and how to configure them if you don't know how to, okay? In this case, I have created a closed and flat path with x-axis pointing up. The path is made with horizontal segments, as you can see there, with a scaling factor of 5, and the color of the path is black in this case. Adjust the color to a black color. Okay, so on the other hand, I have added a graph that will allow us to visualize the robot trace. If you have any questions about the creation of graphics, then I also recommend you to watch the corresponding video in which I explain how to work with graphs. So, in order to be able to access to the information provided by the vision sensor, we must first obtain the object handle, as you can see there. Okay. Then, within the syscall sensing function, we must call the sim.getVision sensor image function. This function will return the image of the vision sensor, but in this case, because we are simulating an infrared sensor, we need to provide a flag to obtain the image in a grayscale format, okay, as you can see there. So the function returns a list with all the information of the image. In this case, because it's a single pixel and it's a grayscale image, the information of interest will be obtained directly on the first element of the list, the first pixel. But for higher resolution color cameras, you will actually get a list with RGB, which is red, green, blue channels of each of the pixels, all sorted in a single list. So this is something we will see in a different video, okay? So if you show the value, if you print the value you obtain with the vision sensor on the console, okay, using just the print instruction, you will see indeed that the sensor, whenever it's pointing to the black line, it will return a value approximately of 0.1, while if we move the robot to an area which is white, then we will, the expected return value will be approximately 0.9. So therefore, when the robot is when the sensor is just right on the edge of the line, the information that we expect to get will be 0.5, because it's just right in the middle of black and white. So part of the image will be black, part of the image will be white. So that's why we will get a 0.5 value whenever we are on the edge of the line, okay? And we will use this value as a reference to track the line indeed, okay? So the goal is that the robot is always on the edge of the line and any deviation must be corrected. And therefore, a simple way to implement a line tracking algorithm is to compute indeed the difference between the current measured color, which is represented by the variable line color here, and the reference value, which is the variable gray, and that's the variable that should take the value 0.5 as said before. So if, for example, if the robot is in the white area of the line, the difference between these two variables will be positive, and multiply with a given gain, in this case is the variable k line, will provide a negative angular velocity for a robot, and that's indeed implies somehow a clockwise turn of the robot, so it will move towards the line. Okay. On the opposite, if we are on the black zone, just right in the middle, the angular velocity will be positive, so it will try to move towards the edge. Okay. And indeed, if we are just right on the edge, so the difference is 0, the angular velocity will be also 0, so the robot will move straight. The linear speed will be set based on the distance we get from an object, but for now you can make it simple and just put a fixed value there, let's say something between 0.1 and 0.5, and then you will see how the robot try to adjust the gain correction to the line to see that the robot is behaving properly and tracking the line. And the idea is that we can combine what we already see about reading distances from an ultrasonic sensor, and the idea is that to use that distance to regulate the speed. Okay, so as usual, we can get the handle during the initialization of the simulation, and then in the call sensing function we can obtain the actual distance of the value using the get distance function as shown. Okay, this is something we already saw in a previous video. And also we can adjust the linear speed based on the distance or the sensor distance. This is something we already saw again, and in this case it is what I recommend is to implement the get velocity function, as you can see here, in order to obtain the linear velocity of the robot. Okay. So in this video, I have explained how to use the vision sensor in CoppeliaSim for simulating an infrared sensor. We will see later on how to access to a full image or color image using a camera and how to process it in a different video. Okay, and also in particular in this video, what I have explained is a basic algorithm how to follow lines using a single infrared sensor and how to regulate the speed so we can stop if there's an object just right in front of the robot. Okay, I recommend you to watch the next video to see what's the expected result even before you start programming your own code. Okay, so you get a clear idea on how it works. Okay, thank you very much. Hello, in this video I'm about to show you how this line following algorithm works based on the algorithm I described in a previous video. Okay, so as you can see here, you have I have created a path in this case. This is something you can generate the shape you want, but make sure that the turns that you do, they are smooth enough based on the parameters of the algorithm, which mainly are the speed you want to follow the line and the gain you correct your angular rate. Okay, so based on that, you can easily generate a path which is smooth enough for your speed and gain. Okay, and also you need to make sure that in this case the infrared sensor detecting the line, which is the TCRT 5000 sensor, I'm going to zoom it. Okay, this sensor here, yeah, this sensor here, it's a vision sensor with 1 pixel, and it's configured wide enough to make sure that you can get at least part of what is the edge of the line. If it's too narrow, it will be very difficult to control. You can make it even slightly bigger, and that's acceptable considering the real conditions of the sensor. Okay, and as I said, also if you make the path this wide will also be helpful, especially whenever you turn, so it doesn't overturn to the other side of the line. Okay, so make it slightly wider. Okay, this is the size, in this case is 5. Okay, so let's see how it works. Let's go for this view here. Okay, and let's see how it works. Okay, as I said, you should adapt the turns here so the algorithm is smooth enough and can follow your path. Okay, and let's just simply make sure that it's able to complete the whole path I created for this demonstration. Okay, so as you can see, it works. Okay, and it will be looping forever. Okay, thank you very much. Hello, in this video, I'm just simply showing you the expected result when you combine the line tracking algorithm with the obstacle avoidance. Okay, as you can see, the robot is tracking the line, and we can see that whenever there's an obstacle just right in front of the line, then it will be detected and the robot will stop. Okay, thank you very much. Yeah. And in this video, this is an advanced exercise. Obviously, it's optional, in which what I'm showing you is how to, the result when you combine the line tracking algorithm, detecting the obstacle, but also following, in this case, a wall on the right. Okay. So if you combine what you have already seen in the line tracking and the algorithm to stay within the walls, you will see that you are not so far from getting this result. Thank you very much. Hello, my name is Leopoldo Armesto, and in this video I'm about to explain how to create a robot from scratch using the software CoppeliaSim or VREP. And in this case, we are going to create a walking robot. It's a hipless robot indeed. It's called VPET because it has 2 feet. And the files associated with this robot, you can find them in the video description. Okay, so there's a link there. You can download the files and follow the following steps in order to create this robot. Okay, so let's start by actually importing the files or the mesh files associated with this robot. So let's go for File menu, Import Mesh, and let's go to, these are the files indeed that I have or that I provide you. So you can select all of them and just click in Open. Remember to, here we need to set the proper scaling because of the units included in these files is in millimeters, so we need to put the correct units, and then we have to just simply select Up Vector Z and import it. Okay, this takes short time, and here we have our robot. Okay, well, at least this is the aspect of a robot. Okay, so let's, here it is. Okay, so what you have to do now is, on the one side, you have to rename the shapes you have imported. Okay, so you can identify them easily. Okay, so for instance, this shape here, this is the Arduino board. Okay, so let's call it Arduino. Okay, the next shape, this thing here, it's a Bluetooth module. Okay, so let's call it Bluetooth. Okay. And then you can go for all the shapes here, for instance, the ones here in the leg. Okay, this is you can try to find or set the names that I use for the original files if you want. But this one is left leg metal because this part is made of metal, and this part here, for instance, this is the ankle, so it's the left one, so it's left ankle, and I used to use wood, so it's made of wood, and even this small component here, this is a rivet. It's something we use to attach the metal part to the wood part, so it's let's call it left rivet. Okay, as it is. Yeah, and yeah, you can rename your files with the names you want. Okay, and the other important thing is that you have to, or ideally you would like to have colors in your parts and components. Okay, so let's select, for instance, this one. This is a servo motor, so if you click on the icon, double click there, you can go for adjust color and select the color you want. For instance, servos are usually I usually use a blue color. Okay, or you can select, for instance, that one, which is a buzzer, and this electronic usually has a black aspect, so I can just simply decrease all the colors here, or the Arduino board is red, or usually I use red for that, so I can decrease the green and the blue component, and then I have a red color. Okay, so in this step, please finish all these instructions, complete all these instructions to have the proper names on the parts and some colors, whatever you want. Okay, thank you very much. So in this next step, as you can see here, I have renamed all the components or all the objects, and I have colored them. Okay, that's something you can do by your own. Okay, now the idea is that these objects are meshes. Okay, so they are they include a complex geometry, and they are not ideal or they are not suitable to use in order to generate a proper simulation. We need more simplistic geometries in order to do that, and this is called here in the software pure shapes. Okay, and what we are going to do right now is to create pure shapes from the current aspect of our robot. Not all of the elements, but some of them. Okay, like for instance the base here, the front, this power bank. We can do the same thing for the foot, one left and right foot. Okay, and here we have the ankle. Okay, so we can create also this thing here, and also we will generate another one for the rivets and also another one for the legs. Okay, so I'm about to explain how to do that. Okay, so let's start with the easiest one, for instance that one here, which is the base of the robot. So we have to go on this option here we have on the left, which is called toggle shape edit mode, and if we enter in this mode, we have this shape represented with triangles, and we can select them just simply by clicking on Shift and select the corresponding triangles. In this case, I have selected all of them. You can see that clearly here, and because of the geometry of this shape, I would like to extract a cuboid that more or less assembles or reassembles the aspect of this shape. Okay, so I extract a cuboid and make sure that you have these two options selected. This is the default behavior, and you click OK. So as you can see, there's a shape here, which is the cuboid that I have created. Okay, so I can exit in this mode, and I will see that indeed this is the cuboid I have selected, okay, or I have created. I can rename this as robot base, for instance. Yeah, and this is just a usual way to proceed is to put the nice objects or the nice geometries in the first layers of the visibility layers, and the pure and joints, the pure shapes, objects and joints, to move them on the second row of the visibility layers. Okay, so we need to access to the icon, common properties, and set this object visible on the second row. Okay, and you can see that it's not visible here anymore, but the objects still exist if we invert the visibility layers. Okay, so this is the object we have created. Okay, so you have to do the same with the, as I said, with feet. In this case, we have to do the same with the ankle, a cuboid as well. So we can generate cuboids here. This part here will be indeed a cylinder. So let me explain how to do it. You can access to the component, and then you can click on Shift and select the triangles, for instance those ones. Okay, it takes some time. Sometimes it takes the time to select all the triangles. Okay, so let's hope it works. Here it is. As you can see, I have selected 2,129 triangles over a lot of more triangles. And in this case, I'm interested in generating only a cylinder of this part, because it will act as a, in this case, as a blocking component for this rivet here. So I extract a cylinder, okay? And again, here it is. Let me close this and see if we have it. There it is. And here it is, the cylinder. And this is something I can move again to the second row of the visibility layers and check that it's properly done. Okay, here it is. Okay, so the aim here in this step is to create, as I said, pure geometries from main important objects like the base, the front, the power bank in this case, the 2 feet, and also the ankles and the rivets, and as well as in this case the leg of the robot. This part here is particularly peculiar because if we create a cuboid from this geometry, it will be a full cuboid with a lot of material inside, and we don't want that. So what we need to do is indeed to create 3 separate cuboids. One for the front, one for the rear, and one for the top. Okay, that's something easy to do. We can create one if we go here. I recommend you to select only more or less up to this point, more or less, okay? It's approximate. And generate a cuboid. Yeah, okay. We can select those ones. No. Here it is. Okay, we can extract another cuboid. And finally, we can extract another cuboid from these ones. Yeah, that's my recommendation. No, sorry. That is. Extract another cuboid. That's my recommendation. You will see that these 3 cuboids here, let me show them in the other visibility layer, is more or less the same geometry as the original one. We can invert that. Here it is. Okay, this is more or less the expected result that you need to get for these components. They will be grouped later, so they will be as a single object, but in this case we need to create them separately. Okay, so please complete these steps, and I'll explain you what to do in the next video. Thank you. So now the idea is to, as you can see here, I have created already all the pure shapes that I mentioned in the previous video. So now the idea is that even you can check that easily. Okay, if you click on play, you will see that this robot, it's still not a robot. Okay, so it's just simply basically a set of components that fall apart, and we need to do 2 or 3 main steps. First thing is to group parts that actually have or belong to the same object, to create the joints and to establish a proper hierarchy. Okay, so in this step the idea is to group the objects. For instance, if you play and click, you will see that the front face falls apart from the body, and that's not realistic because they are actually assembled. Okay, so in order to do that, also the power bank will be attached to the body. Okay, so in order to do that, you have to select any of the components you want to group, click on Control and or press Control, and then select the other 2, in this case parts I would like to group, and you can basically right click there, and in the edit option you have group merging, group selected shapes. And now these shapes, as you can see here, the icon has changed because now it's a group shape and all of them belong to the same object. And now if I click here on the play, then they don't fall apart. At least they stay together. Okay, so we have to do the same thing with the legs, these 3 components here, 1, 2 and 3, group them, and also the same for the foot and the ankle. They are attached together, so they belong to one single object, okay? Not the rivet. The rivet goes, it goes separately, okay? And do the same for the other leg too, okay? Thank you very much. So, once you have completed the previous step, what you should get is here, as I said, you have the left foot, which is these two parts were grouped together, and also I have these three parts here grouped together. I have the rivet still, it's a single object there, and I have the same thing for the right, the leg of the right rivet, and also I have the robot. Okay, so this is the expected grouping that you will need. So now in this step we need to create the joints. Okay, joints will be related with the servo axis because they will be motorized joints. So on each servo we need to add a joint on the corresponding obviously direction. So this joint here, or this servo here, has a joint here, a vertical joint here, and that one has a horizontal one here. Also these two servos there. Okay, but also we will have another joint here on the rivet, because this part will also rotate corresponding to a free axis based on this rivet here. Okay, so let's create, or let's show how to create a joint. This is something we can easily create here from the add menu joint. All of them will be Revolute. Okay, so this is the joint. It's actually quite big, so let's modify the aspect. That's just simply an aspect, it's not that relevant. Okay, so let's put here 0 for instance and 0.5, and we have a smaller joint there. Okay, and in this case, because I can change the dynamic properties of the joint, so in this case I want this joint to be the one attached to this servo here, so I need to enable the motor, and also because it's a position control servo I need to enable the control loop enable position control. Okay, the properties there. Okay, and for this joint I'm done. I can just simply rename it as left leg, for instance. Okay, and now the idea is to place this joint right there, and the problem is that any object has its own center or reference system, but it's not, in this case this servo, the reference system is not indeed aligned to this vertical axis here. Okay, so what we need to do is to create an auxiliary object based on the actual axis of the servo. We can do that easily in the, if you follow the following instructions. So let's first move or visualize this component in this layer here, for instance. Okay, so let's invert that, and here it is. This is the component, the servo component, totally isolated. And let's create a new object based on part of the geometry of this servo here. So let's go to the toggle shape edit mode, and let's select only these triangles there and extract a cylinder. Now this object that I have created, you will see it immediately, this one here. Okay, I will show it on this second layer there, and now this servo I can undo that. Okay, great. So this is the object I have created. Okay, and this object, and also let me just visualize here the joint I created. Here it is. Okay, so the idea is that I would like to move this joint here to the center of this new object here, temporary object. Okay, so I select the joint, I click on shift, and then I select the cylinder, and then I go for the position shift translation dialog, and then make sure you're in the position 1, and then apply selection, and there you have it. The joint has moved exactly to the same center as the auxiliary cylinder. Now we have that, we can just simply remove that. We don't need that anymore. Okay, And here we have, indeed, sorry, that one. Here we have, indeed, the servo joint that we have created here. Okay, we have to do the same thing here for this axis here. So this axis will be horizontal, so you will need to apply a rotation, and we will need to do that also for the axis we have here in the rivet. Indeed, this case is even easier because we already have a component, which is that one in that case, that we can use in order to place the corresponding axis. Okay, make sure that this axis here, the ones related with the servo, have the motor enabled and control loop enabled properties checked, and the one here that you will need to create for the rivet, okay, or the ankle, will be without the motor because it's a free joint. Okay, thank you very much. So in this step, we actually would like to explain, or I would like to explain how to actually generate a proper robot. So up to now, we still don't have a robot. We have almost all elements we need. If you click on play, it will still have a weird behavior. It's not a robot, it's falling apart. And the reason is that we still need to do one more step, which is to generate or configure the proper hierarchy in order that all components don't fall apart, okay, and they are related one to each other. So in this particular robot, this is the main component, okay, this is the one I use as a parent for all the rest of components, and let's say that all, let's say, nice geometries which are actually attached to this robot, I will place them inside as child objects, like the base wood, all of them, okay, like Bluetooth, buzzer, yeah, all of them. The ones which are fixed or related with this object here, okay, for instance, from wood as well, okay, left ankle, no, this no, the servos, this servo here, it's attached to the robot too, okay, so it's fixed with the base of the robot. And let me see the right one as well, that one, yeah. And the important part here will be also that you will also make child objects of this main component, the left leg axis or joint, which is that one, so I'll drag it there, and also the same thing for the right one, that one here, okay, because these two joints will move as long as this base is moving, okay. Indeed these two joints will actually move this part here. This joint here, it's in charge of moving this part here, so I will drag this part inside the joint, okay, as a child object, and the corresponding operation for the right leg, okay. So now this object here is a pure geometry object, so I need to include as a child all, let's say, nice objects that, or non-pure objects associated or attached to this part here, which are, for instance, this horn here. I have it, let's see it in this view. So this horn here will be actually moving as long as this leg it moves. Also this horn here will move as well, and this geometry here, metal, yeah, the metal one will be a child object too, okay. So all of them will be associated to this or related as child objects of this leg object here. Then what I need to do, let's switch the view again. Now this joint here will move the servo and the foot, okay. So this left foot joint will actually move based on this part here. So if this part rotates, this axis will rotate too, okay. And now this joint will actually move this part here, the left foot cuboid, and also in that case, that one, yeah, that's the servo. Let me see, right. Okay, here we have the ankle. Yeah, that's also a part that will move together with that, and left foot, yeah, that one too. Okay, so all these two joints will actually move the foot, and there's one more joint here. This one is the free joint that it will move also based on this part here. Okay, so this joint here will be also a child of this component here, and this part will actually move the actual rivet cylinder. Okay, and this will be just simply used to block the component. Okay. Okay, so you have to do the same thing for the right leg. So this is the expected hierarchy that you will need. Let me add sonar also in here. I think the rest of components are related with the right rivet. Left rivet will be in here. Yeah, exactly. Yeah, the rest of OLED will be the robot that's related with the robot, and the power bank will be related with the robot too. Yeah, I think the rest of components are related with the right leg. Okay, so please complete the other leg, and in the next video I will explain you how to generate or simulate a sonar sensor. Thank you very much. Well, if you have reached to this step, then means that you actually have a robot. Indeed, you can. It's the first time you can play the simulation, and the robot doesn't fall apart. Even you can check that on the other view as well. So the parts don't fall apart. Everything is correct due to the fact that we have the proper hierarchy, and also all settings are properly. So if you don't see any warning here, means that everything is properly configured. Okay, ready with the joints moving, dynamic parts, and so on. Okay. So yeah, okay, so first, this is the first step, the actual robot, but this robot has or includes a sonar sensor. Okay, so in this step, I'm just simply going to explain how to create this sonar sensor or proximity sensor, and this is something we can easily create from the Add menu, proximity sensor. The type of sensor we need is a cone type. Yeah, there it is. And by default it's pointing upwards, so we can do a rotation of minus 90 degrees. This is the actual setting I have here. In x-axis, as you can clearly see that this is x-axis pointing there, and if I do the minus 90 degrees, it will be pointing forward. So yeah, that's it. And now what I need to do is to make or place this sensor in the same center or the same reference system as the sonar sensor or the sonar object. Okay, so I go for the position translation dialog, and what I have done is select first the sensor, then the sonar, and then apply the selection, and there I have the sonar. Okay, with the sensor related with the sonar. So it is quite obvious that you want this sensor to move as the robot moves, so this needs to be included in the robot. I usually include it here as part of the sonar. Okay, so whenever the robot moves, we'll move the sonar, and actually we'll move the proximity sensor. Okay, so if you click on the simulation now, okay, you will have the sensor detecting. Okay, but let's configure it in a proper way, in which is more, it's closer to the actual sensor. So let's access to the properties of the sensor, double click here, and I usually use this with this parameter. I usually set this value here. Sorry, yeah, and this one I usually select that one. And 60. degrees. Yeah, that's it. That's the common setting I usually use for this sensor. And now if you click here, you see that the sensor is actually detecting the floor. Okay, this is something we don't want. The reason is that the floor is intersecting with the volume or the detection volume we have here, and the floor has a detectable property on. Okay, so this is something we can disable. So if you go for the resizable floor, that one, and you go for this object here, yeah, and you double click on the icon, you go for the common properties, you see that by default this object here has the detectable property enabled. So we can just simply go or click on details and uncheck the ultrasonic sensor. Yeah, and now it won't be detected by ultrasonic sensors. The reason is that this floor here, the way the sensor is pointing at, it's not actually detecting the floor, because the wave sounds, the ultrasonic sounds, it's just simply reflecting on the floor, so it's not returning a wave. Okay, so it's not realistic. Okay, so now you can see that it's not detecting the floor anymore. Okay, now to make sure that it's obviously proper detecting any object you would like to detect, you need to make sure that it has this detectable property on. So for instance, let's create a cuboid here. Okay, and let's move it right there. Okay, and make sure that in order to be detectable, you need to select this property there. Yeah, and now if you click play, you will be detecting the actual object. Okay, so that's the expected behavior. Thank you very much. Hello, in this video I will explain theoretical concepts in relation to kinematic control of mobile robots with wheels using a technique known by off-center kinematic control. Therefore, the aim of the presentation is, on the one hand, to understand the concept of kinematic control and its application for trajectory tracking. I will explain some basic concepts on feedback control and specifically for mobile robots with wheels. I will explain the difficulty of their kinematic control as a result of being subject to a non-holonomic constraint that will appear in the vast majority of mobile robots. And finally, I will explain all the mathematical background related to the proposed off-center kinematic control and the closed loop structure. So first, we need to understand the concept of kinematic control. The ultimate goal is to determine a set of control actions, that is, wheel speeds that allow to reach a final configuration from an initial configuration. In kinematic control, aspects such as obstacle avoidance are not considered. That's a task typically considered in motion planning algorithms. And there are two classic approaches, trajectory tracking and path following. In the case of trajectories, the objective here is to define a set of target configurations over the time. While in path following, the path is defined as a set of desired configurations regardless of time. And the objective is to define a strategy so the robot converges to the path. So in this presentation, I will focus on trajectory tracking problems. So in this sense, I will explain some very basic concepts on feedback control systems in its most simplified version. Okay, so in a classic control loop, we find on the one hand the system to be controlled. Sometimes this is known as a model or process, depending on the context. And on the other hand, we have a controller or controller, whose objective is to minimize the error between a reference or set point and the measured output. Okay, so here I show three basic examples of control laws that we can find classically in the literature. On the one hand, there's a proportional controller or P control, which states that the wheels, in this case speeds, are proportional to the error between the reference configuration and the robot configuration. A PD control includes a derivative term that basically includes also the speed error. And finally, proportional velocity control, it has an advantage over proportional derivative because we don't need to obtain the derivatives of the configuration, but it uses a feed-forward, in this case, reference for the speed. So these controllers, they do not include any kind of integral action because the process itself, the robot, already includes this integrator by integrating indeed the model or the process equation, as you can see here, over time. Okay, so a very important concept in mobile robots with wheels is the concept of non-hologramic constraint, which is or has been explained in a previous video about wheels types and also types of robots. So in this case, in this kind of robots, we're going to deal with differential configuration. Fixed wheels indeed introduce a non-hologramic constraint. So in practice, we have to control a robot over R2 times S space, which means that Cartesian XY space together with the orientation, using a set of control actions that are defined in the R2 space, which are indeed the wheel speeds. Okay, so due to the non-hologramic constraint, this implies that the robot is not controllable in specific directions at any time instant, so only on certain directions, and therefore the control to be designed must take these considerations into account. So to understand the concept of non-hologramic constraint, we can see that the robot's base velocities, the velocity in x and y, are not arbitrary, and they do depend on the actual robot configuration or orientation, and also on the linear velocity of the robot. So on the other hand, the orientation of the robot can be modified from the angular velocity, and both linear and angular velocities can be obtained from the wheel's velocities, which can be measured with sensors such as encoders attached to the wheels. Okay, so as a consequence of the non-hologramic constraint, we cannot control without considering that not all directions are directly controllable. Okay, for instance, we cannot control lateral movement of the robot using this kind of wheels. So for this reason, the proposed control is based on the concept of off-center point. This is a point at a distance e, in this case, from the central point of the robot that we will usually place just right in front of the robot. The maths for computing the position of these points are rather quite straightforward, and they can be obtained directly from the robot configuration considering this distance e. Okay. So similarly, we can get the speed of that point. The maths related with the speed of that point is we just simply need to do the derivative of the previous equations, and you can see that it depends on the one hand, it depends on the actual speed of the robot, the speed in x and y axis, but also depends on the angular speed as well as obviously the orientation. Okay, so we can express all this in a compact notation, and indeed if we try to obtain the velocities of the off-center point related with the velocities of the wheels, we can see that in a compact form we have what is known as a Jacobian matrix. This is a Jacobian matrix that relates the speeds between the wheels and the off-center point in this case. And also we can compute the inverse relation of this Jacobian matrix to determine actually that the speed of the wheels that they should have for a given speed for the off-center point. Okay, so the actual task for the control will actually be to define this speed for the off-center point. As you can see, this matrix is rather quite simple. Basically, it depends on the orientation of the robot, and also it depends on the distance e of the off-center point, which is indeed a design parameter. So with all these ingredients, we have the following control loop. On the one hand, we have the trajectory generator here that it's responsible for generating the reference or the configuration reference and also the velocities for this reference. Also we have a module which is known as off-center trajectory here, which basically using this trajectory here computes also the reference trajectory but for the off-center point. And this trajectory will be indeed compared with the off-center point itself that can be obtained from the robot pose. And this difference is known as the tracking error. So the task of the controller will be actually to minimize or to make this error to zero. So it provides a desired off-center point velocities, and we can apply that using the inverse kinematic equations that I showed you before, and that would actually derive to the desired wheels that we need to apply to the robot. So more specifically, if you want to implement the PV kinematic control, then you have to implement the following equations. So here you can see we have the inverse kinematics, which is this expression here. We have the velocity of the off-center point, and we have also here the error between the off-center reference point and the robot off-center point. And this error will be multiplied in this case with a gain, which is Kp, and this is actually proportional control, okay? And this is the part in which we provide the feed forward of the velocity of the reference, okay? So similarly, we could also apply a PD control. The main difference here is that we must consider not only the position of the off-center point but also its speed, okay, as you can see here, okay. And this implies that we must compute the robot linear and angular velocity, but this is something we can easily do from the actual odometry system of the robot. So in this video, I have explained the kinematic control using a technique known as off-center point that can be applied to mobile robots with differential configuration for trajectory tracking problems. Thank you very much. Hello. In this video, I will explain how to implement a kinematic control to track trajectories with a mobile robot with wheels in CoppeliaSim VREP software. So the aim of this presentation is to implement PV proportional velocity or PD proportional derivative kinematic control using a Pioneer 3DX robot. This is a robot that is included in CoppeliaSim inside the mobile folder of the model browser. So search for it. And actually in the real robot, this robot includes encoders to measure the speed of the wheels and also 16 ultrasound sensors. And even some models include a laser rangefinder. So in this presentation, I will assume that the robot position is known, and therefore we can get access to that position and also the robot orientation. So in order to start, we need to create from a blank scene, a new scene. We need to create a path like the one I'm showing here. Basically following the indications I explained in previous videos about how to configure paths, okay? But in summary, the path must be closed, flat, and also pointing, the x-axis must be pointing up with the automatic orientation. So please check the properties of the path, so make sure you have the proper setting. So before you start programming, the robot comes, or the model of the robot comes with a default script, so we don't want to use that script, so you need to delete it. And then we have to create our own child non-threaded script to implement your own code, okay? So in addition, to establish the wheel speeds, you must access to the robot motorized joints and call the function set joint target velocity. And this is something we explained on previous videos several times. So basically you need to get the handles and then you need to set the target velocities, modifying these two zeros you see here with the corresponding computed values for each of the wheels. So in trajectory tracking problems, we have to track or follow a point, and this point will be actually a dummy object that we need to add to our scene, and we need to make it child of the path, as you can see there. Okay, and check or make sure that you have the follow parent path property checked. Okay, and also you can even increase the object size, so if you can see it better or bigger. Okay, so also there's a parameter which is called the offset, and this is a distance with respect to the initial trajectory point. It could be positive or negative, and this is a parameter that you must adjust depending on how you have created your own path, and basically depends where your path starts. Okay, and make sure that you just simply put it just in front of the robot with a reasonable distance, not too far, not too close, so whenever you start it doesn't need to speed up too much or just to move backwards. Okay, so yeah, okay, so also just you can implement the code I'm suggesting here to get the handle of the path, to set a specific velocity or nominal velocity to that path. That will be the speed of the point moving on the trajectory, and also to get the handle of this dummy that we will need for later use. Indeed, we can also implement the function as I show here, the get trajectory point function. The goal here is to access to the position and orientation, and also the speed of the trajectory point. So the position and orientation can be obtained with respect to any reference system. In this case, by introducing the number -1, we're indicating that the position and orientation are with respect to the world reference system. Okay. On the other hand, the speed, the API that CoppeliaSim provides to obtain the speed of an object is always with respect to the world reference system, so we don't need to introduce this second argument. Okay, so the function I'm providing here returns two output arguments, each of them with three coordinates or three values. The first output argument includes the position and orientation of the trajectory point, while the second argument returns the velocities of those coordinates. Okay, so in particular for the orientation, you have to see here that we are using a weird expression to compute the orientation. This is, or the reason behind that is because the reference system of the point attached to the path is different from the one in the wall, and we need to, or I suggest you to implement the code as I'm providing here. Anyway, you can try to check if everything is correct by printing the values of this trajectory on the console and make sure that you're getting the correct values. So, as I said before, we will assume that we have access to the true robot position, also known as ground truth position. Here we are somehow cheating. Okay, so this is because we don't actually know the actual position of the robot without using additional sensors such as sonar or laser rangefinder. In another video, I will explain how to compute that position from the robot's odometry. Okay, but from now on, we just simply need to create a dummy that we will make a child of the robot object, and we will need to place it just right in the middle of the wheel's axle. Okay, as you can see here in the figure. Okay, so the idea is that it has to be aligned with the wheels right in the middle, and the z-axis has to point upwards, and the x-axis has to point forward. Okay, so to access to the robot position, we will need to implement this simple code. On the one hand, you need to access or to get the handle of the object that I previously or that we previously created. In this case, is the robot pose, and also to create or to initialize a variable called pose that will provide us with the actual or the initial robot pose. Okay, so indeed, I put here also a function to how to get access to that pose, and it's rather quite simple. We have to get access to the object position and orientation of this dummy, and this function returns one single argument but with three numbers which correspond to the x, y, and orientation of the robot. Okay. With all these previous steps, we are ready to implement a PV kinematic control. The maths related with this control has been explained in a previous video, so I recommend you to look carefully to that video to fully understand the meaning of each of the variables. In particular, B and R are constructive parameters, parameters that depend on the robot. In particular, they are the separation of the wheels with respect to the center and the radius of the wheels. Okay, so try to obtain these values from the robot geometry itself. Okay, the parameter E is a distance that you can or we must set, and it represents the distance over we want to perform the control. This is what we known as the off-center point. And the bigger the distance is, the softer will be your control, but on the contrary, it will have lower correction capability. Okay, so the gain Kp in this case is the gain of the proportional controller, and we are providing with this controller a feed forward of the reference of the off-center point velocity. Okay. The rest of the variables that you can see here are related with the configuration of the robot, describing the x, y, and orientation of coordinates in this case. Also, we have the reference trajectory point, either for positions and orientations, but also for velocities, as you can see here. I suggest you to try to implement this kinematic control, and optionally you can also try to implement a PD controller too. Well, in this video, I have given all the necessary instructions and indications to be able to implement the kinematic control to track trajectories. In the following video, I will show how how this type of algorithm works with the CoppeliaSim simulator. Thank you very much. Hello, in this video I will show you how actually a kinematic control for tracking trajectories works with the CoppeliaSim VREP software. As you can see here, I have a scene in which I have defined a path object. I have added a robot, in this case a Pioneer 3DX robot, and I have added a dummy that I made child of the path, and this dummy is right there, as you can see here. Yeah, and this dummy actually, if you access to the properties of this dummy, make sure you have the follow parent path, and also this value here depends on the offset position that you have for your path, and that will modify the position of this point along the path. Okay. Also make sure that in your path you have properties that I mentioned before about the path. All of them are checked here. Okay, so everything is properly configured. Okay, and also I have added in this case an odometry. Here it is. The ground truth, a dummy for the ground truth position of the robot is that one. Let me just show it. Yeah, something like that. Yeah, and as you can see, this dummy here is aligned with the wheels, the robot wheels, and it's just right in the middle, and the x-axis is pointing upward, and the y-axis, or the x-axis is pointing forwards, and the z-axis is pointing upwards. Okay. Okay, so I obviously have implemented the code in order to succeed with the kinematic control. So let me just run the simulation and see how it works. You can see the robot is tracking almost perfectly, let's say, our trajectory over the time, and well, let's just simply finish till it finishes the whole loop to see that actually works. Okay, here we have. Okay, thank you very much. Hello, in this video I will explain how to implement an odometry system in CoppeliaSim VREP software. The aim of the presentation is to understand the concept of an odometry system and also learn how to calculate the speeds of the wheels from the rotation of the wheel axis, as if they had been acquired with some sensors such as an encoder. From this point we will compute also the position and orientation of the robot, but in order to simulate a realistic drift or to simulate realistic drift problems in the position orientation estimation of a robot, we will introduce a simulated wheel slippage too. So for this presentation, first, if you have not already done this so far, you need to work with a sim including a Pioneer 3DX robot. You can use the code that comes by default with the robot, or you can use the code that I proposed for the kinematic control explained in a previous video that I actually recommend you, so you can get exactly the same results I'm obtaining here. Okay. So to create an odometry system, we will need to create a dummy and place it at the base of the robot, just aligned to the wheel axis and in the center. And you can rename this dummy as odometry. And this will be actually, or will have actually the same position and orientation as the dummy we used for a previous video in which we set we get the ground tooth position of the robot. Okay, so indeed in this figure you can see that make sure that the z-axis points upwards and the x-axis points forwards. Okay, so also you can add in this case a graph to show the trace of this dummy and also to show the trace of the ground truth robot position, so you can compare both. Okay. So next we need to add the following code in syscall init function to obtain the odometry system handle and initialize the robot configuration as I indicating here. Okay, from the position and the orientation of this dummy. Then we can obtain the angular displacement of each wheel with, let's say, a perfect odometry system from the rotation speed of each of the joints. This is an internal parameter that we must get from a function which is known as getObjectFlow parameter, as shown. And the getOdometry function actually returns the left and right wheel displacements, and we must call it somewhere. This function must be called somewhere in the syscall sensing function. Okay, so we need to update these values on each simulation step. However, the previous function is not realistic, since the previous odometry system does not consider typical sources or error sources found in a real robot. In this sense, a more realistic case would be to apply the noise to the measurements or even to add a constant and small drift, let's say due to a bad calibration or wheels misalignment. So therefore, we encourage you to extend the previous function to include two input arguments, in this case representing a magnitude of the angular rotation and linear translation noises applied to the odometry system, respectively. So it means that alpha 1 affects to the rotation and alpha 2 affects to the translation. And also don't forget to include a call to the math random seed as I'm indicating here. You need to do this in a syscall init function, so that random numbers that you generate with this math library are initialized with a different seed each time you run the simulation. So to compute the position, we must actually apply the equations of a kinematic model of the robot. Here we use the wheel displacement increments provided by the previous function from the odometry system, and from these values we can obtain the arc displacement of the robot base, the line indicated in red, and also the increase in orientation. So once we have these increments, we can obtain the position and orientation of the robot by integrating over the time, okay, as indicated. So therefore, the function I propose you to implement should look like this. On the one hand, it accepts one argument with the robot configuration containing the position in X, Y, and also the orientation. And then also you must, that's the code you need to do, is you must call the odometry function and update the position and orientation based on this on the previous equations I show. And once you have that, you have to update the pose variable, and then you can also set the position and orientation of the dummy object so you can get a proper trace of the odometry system. Okay, so please adjust the noises of the odometry system so to get a reasonable and realistic behavior. Well, in this video I have explained how to implement an odometry system in CoppeliaSim VREP software. In the following video, actually, I will show you how this works combined with the kinematic control described on a previous video. Thank you very much. Hello. So in this video, I'm about to show you how an odometry system works using a CoppeliaSim VREP software. So the idea is that we are using a kinematic control to follow or to track a trajectory, as we showed in the previous video. And the difference here is that this kinematic control is not using the actual or the ground truth robot pose, but the pose provided by the odometry system. So this odometry system obviously has some drifts because they are based on depth reckoning sensors such as encoders. So the position and the orientation will drift over time, okay? And actually this is what is happening here. So indeed, in the magenta curve here, you can see here is the position that has been estimated with the odometry system. So it really believes that you are on the curve, or that the robot is on the curve. But the actual situation is that the robot is drifting apart from that position, and that's why we have this behavior here, okay? So let's play the simulation to see how it works. So you can see that even from the first or initial turn that we get an error in the orientation. And actually, if you can see here, this is the point that the robot believes it's following. So its position is about here somewhere. Okay, and you can see that this will drift over time. Okay, thank you very much. Hello, in this video I will explain a well-known algorithm that will allow you to program a robot to solve mazes with a wall-following behavior. So the aim of the presentation is to understand how to solve mazes using a wall-following algorithm and explain how this algorithm can be implemented using proximity sensors. One requirement for the maze is that it must be simple connected. That means that all walls need to be connected without isolates. So the idea is to use proximity sensors that will allow us to detect walls. In particular, we will use an ultrasound sensor to detect the walls in front of the robot and 2 lidar sensors to detect the walls on one of the sides of the robot. So the entrance and exit of the maze must be at the outer perimeter of the maze. So the algorithm for solving a maze has 4 possible stages. So at least in the way I'm proposing this. So the robot will change from one stage to another according to the conditions indicated here. So these stages are also known as states where the robot is. So actually in the first state the robot will perform the indicated action, which will in this case be following a wall, okay? So in this situation, what it can happen is that you can follow the wall on the left and the right. That's not the relevant condition here, but what it can happen is that you detect a wall in front, or you stop detecting the wall you were following, okay? So in case of detecting a wall in the front, what you have to do is to make a turn 90 degrees and then that's a pure rotation, okay? And then once this is done, then you can go back to state 1 to follow the same wall. Okay. But if it happens that you stop detecting the wall, and then in that situation, that means that you need to make a curve trying to follow the wall or trying to detect the wall again as soon as possible. Okay. And this is what is indicated with the make curve, in which the robot will rotate but at the same time move, okay, in order to move to a different cell. Finally, we can stop the algorithm by detecting a mark, usually a line on the ground that it's basically indicating that we have reached the exit of the maze. Okay. So to learn more about how to solve a maze following a wall, please access to this indicated URL here. Okay, so to follow a wall on the right, we will use proximity sensors on the right side of the robot. We need two sensors, one in front and one on the rear, and that will allow us to estimate the angle and distance of the wall with respect to the robot. So guiding the robot to remain aligned with that wall at a given distance can be done with a simple kinematic control law. This is something similar we already saw, in which, in this case, K-wall is the gain to correct the distance deviations, and E is the distance to a dummy wheel to guide the robot, and this is known as off-center kinematic control. So the distance at which the robot must stay from the wall can be known in advance if we know, obviously, the cell size. In the same way, we can consider the problem of following a wall on the left side using the left side's proximity sensors, but it's important to remark that if we decide to follow the wall on the right or either on the left, we should not change this decision during the maze solving, since we could return to the starting point. Okay, so therefore this is something we must decide at the beginning, and if we decide to follow or to solve the maze following the right side wall, then we have to keep that decision. Okay, so when following a wall, we might find a corner like the one shown, and this can be easily detected with the ultrasonic sensor, in which basically if we detect that the ultrasonic sensor distance is smaller than expected distance, then we have detected a wall. Okay, and this expected distance can be actually known in advance if we know the size of the cell and the thickness of the wall, in this case indicated with the letter tau, and the separation of the ultrasonic sensor with respect to the wheel basis, indicated with the letter delta. So in case of detecting a wall, as I said before, we must make a turn of 90 degrees. That's a pure rotation, and this is something we can pre-compute in advance. So in theory, we cannot exactly the time we need to perform this turn if we know the speed of the wheels. But actually, in the absence of an odometry system for low cost, which is the case for many low cost robots, we can just simply assume that we have measured an approximate time at a given speed that the robot needs in order to perform the turn, and whatever error we have in the end after completed this turn will be actually corrected with a wall following algorithm. Okay, so that's in principle not a major inconvenience. Another situation arises from the fact that while following a wall, this wall is not detected anymore. Okay, and usually the front sensor in this situation provides obviously a much larger distance than expected. So in this case, if the distance detected, here I put the condition for both sensors. So if the distance is detected is close to the lateral distance that we expect within a certain tolerance, then we can say there's a wall. Okay. Either if one of the sensors does not detect a wall, then what we have to do is to make a turn of 90 degrees as it will be shown. Okay. So in this case, again, the expected lateral distance depends on the size of the maze cells and the wall thickness, but also on the lateral separation of the sensors with respect to the robot central line. as you can see here, indicated by the letter delta leader. So therefore, in case of detecting the no wall condition, we must make a curve 90 degrees trying to move to a top right or top left cell with respect to the robot orientation. And indeed we can again compute or pre-compute the required angular velocities for the wheels using some straightforward kinematic relations. We can just basically also compute the time we need to perform this curve, and this will depend basically on the velocity we want to perform the curve, some constructive parameters, but also on the cell size. Well, in this video I have explained how to solve mazes using proximity sensors and a wall following algorithm for a mobile robot. Thank you very much. Hello? In this video I will explain how to implement an algorithm for solving mazes using a wall following approach with proximity sensors. The algorithm itself was previously explained in another video, but it was explained in a conceptual way. Here in this video I will explain it how to actually what I want to do is to explain how to implement this algorithm with CoppeliaSim VREP software, and in particular I'm going to use the Dio robot, a low-cost robot. So the aim of the presentation is to know how to solve a maze with simple connected walls in CoppeliaSim software. So to do this, I will explain how to program the robot so it can be solved or it can solve a maze following walls either on the left or walls on the right, and actually the ultimate goal is to explain how to implement this in an efficient way so it can be implemented in these ideas in low-cost robots using proximity sensors such as the Dio robot. So as explained in the previous video, the algorithm has 4 states. In the first state the robot must follow the wall, and then from this state we can it could happen that we need to make a turn. This is a pure rotation if we detect a wall in front of the robot, or make a 90 degrees turn if we stop detecting the wall that we were following on the side. Okay, so after these turns have been completed, and then the algorithm ensures that we return back to the wall following behavior. So actually the algorithm ends when the robot detects a mark. In this case we will use a line painted on the ground indicating that we have reached the exit of the maze. And walls will be detected indeed with leader sensors on both sides of the robot, and the walls in front of the robot will be detected with an ultrasound sensor pointing forward. Okay, and the sensor to detect the line on the floor will be actually the TC-RT 5000. Sorry. So to implement this algorithm, we have divided the problem into 2 different stages: the actuation and sensing. It is clear that actions to be taken by the robot will be implemented in the syscall actuation function, and all the conditions that allow us to move from one state to another will be indeed implemented in the sensing stage. Okay, so here I show you the code that you must implement in the syscall actuation function, and as you can see, we're using the variable state that must be initialized to 1 in the syscall init function. This is the initial state where the robot is, and depending on the state value, the robot must do one thing or another. For instance, in state 1 we must follow a wall. This is achieved by calling a follow wall function that will return the wheel's velocities. Or if we are in state 2 or 3, we must apply pre-computed values for those wheels to make the proper turn or to make the curve. Okay. So to detect the conditions in which the robot changes from one state to another, we will implement those transitions in the syscall sensing function. Here I show you the code to implement, although there are few steps needed to be completed first. Okay. In particular, the ones regarding with reading the proximity sensors, and also we need to evaluate the conditions whether if we have detected a wall in front of the robot or we are detecting a wall on the side. And these conditions must be set using the variables, in this case, wall front and wall side. They are Boolean variables. And in addition to this, here I also include the code that will ensure that the robot, when the robot is indeed in states 2 and 3, it's when it's doing the turn or the curve, the robot lays in these states at least for a minimum amount of time. And this time will be actually pre-computed according to the speeds you can compute them in a syscall init function. Okay, and these times are indicated here with the variables mean turn time and mean curve time. And at the end of the function, you also need to implement the condition. If you have detected the line, then you have to set the state equal to 4. So, in order to read the distance from proximity sensors, this is rather quite simple, and this is actually something we have already seen in several times in previous videos. Here I show you a function that will allow you to obtain the distance from a proximity sensor, and the variable maxDist is used to ensure that the sensor returns a value between 0 and the maximum distance. And this was some convenient in some previous exercises, although for this maze solving problem, this is not a relevant parameter as long as it's large enough. Okay? Ideally, set this value to the maximum distance detected by each of the sensors, and indeed this is something you can see how I configure it here using the ultrasound on the LiDAR sensor, which properties I'm using for each of the sensors. Okay, so remember that you have to call this getDistance function for each of the sensors, for the ultrasound and the LiDAR sensors, and this must be done in the syscall sensing function. And then the algorithm to follow the walls was explained also in previous videos. The main difference here is that we follow the wall only using the sensors on one side of the robot. Here you have some comments at the beginning of the function I'm proposing, so to help you to understand how this works. Okay, so on the one hand we need distance measured with the sensors, and on the other hand we use the variable direction to determine whether if we want to use the right or left side sensors to follow the wall on the right or on the left. And we also have, or we need to provide obviously some constructive parameters of the robot, such as the wheel radius and the wheel basis, and also the expected lateral distance to be measured. This is something we can pre-compute. And also we need to provide the velocities and the gain and the distance of the off-center kinematic control that will allow this wall following algorithm to actually make the robot to stay just in the middle of the cell. So the function or the wall detected function will be used to determine if the LiDAR sensor detects the wall on one side or not. This is done for one single sensor. You have to call this function for both sensors actually. And in fact, this function basically returns a Boolean variable that will return true in case that the absolute value of the difference between the measured distance and the expected distance is less than a given tolerance. And this tolerance is a value that you must adjust in this case. And the expected distance is something we saw in the previous video how to compute it, and depends basically on the cell size and the wall thickness and the separation of the LiDAR sensors with respect to the middle line of the robot. And also we have to implement, or we remember that we need to implement also a function or a condition to measure if we have a wall in front of the robot using the ultrasound sensor. And this is as simple as checking if the measured distance is below the expected distance in front of the robot. So when the robot has to make a turn, it will use a precompute or some precompute values returned by, in this case, the precompute turn function. This function returns the angular speeds of the wheels in order to make this 90 degrees turn, and also the minimum time to perform this 90-degree turn. In the case, or in this case, we need to provide the turning speed, the v-turn parameter, as well as the direction of rotation and some constructive parameters of the robot in order to compute these values. Similarly, we can pre-compute the values of the angular wheel speeds to make a curve, 90 degrees curve. In this case, we will have to provide both the speed we want to make this curve and also the direction, as well as some constructive parameters of the robot and the cell size in this case. And finally, in order to detect the mark that indicates that we have reached the exit of the maze, we will use an orthogonal vision sensor with, in this case, with a single pixel resolution that will emulate the TC-RT5000 infrared sensor. And this sensor actually is pointing towards the ground, towards the floor, and its configuration is actually the same that we use in the line tracking video. And here I show you the get line color function that you can use in order to return the value of the grayscale value of the ground we are detecting with the single pixel that this sensor has. And this value is approximately 0.1 when detecting black line. So if you detect something below that threshold, then means that you have detected the line. So in this video, I have explained how to implement the algorithm for solving mazes using proximity sensors following a wall on one side. Thank you very much. Hello. In this video, I will show you how the maze solver algorithm works. But first of all, let me show you how to configure a maze. This is a file that I'm providing in the file description. In the video description. And this file, it's a model that you can just basically load here. And this is the maze TTM model. And this model, as you can see here, this is the starting position, this is the exit position, and in order to configure the maze, what you have to do is to remove the walls that you don't want, just by doing things like that, okay, and determine possible paths for robot to stay, okay, something like that, and then maybe you want to do something like that or whatever, okay. Important to remark that this algorithm doesn't, the walls for this algorithm must be simple connected, which means that we cannot provide, or we cannot find solutions, or we might not find solutions if we provide with these isles here, okay, because the walls must be connected, okay. So now let's move to the actual demo, so in which I will show you how this algorithm works, okay. So let's first run the simulation. So here it's following the wall. Now it will detect the wall in front. Okay, now I'm doing the right wall following algorithm, but it could be also solved for the left on the left side. There's exactly the same algorithm or behavior, but on the left side. Okay, here is doing also a turn. Here is about to do a curve of 90 degrees, but that was not enough, so it realizes that it has to do the curve up to 180 degrees. Okay, this is also another curve, this is a turn, this is wall following, and so on, okay? And actually here, in this point, the robot makes this curve here, but it has taken the incorrect decision. And then at the end of this corridor, then it realizes that it has to do 2 consecutive turns and undo the path that he or the decision that he had taken, and to continue with the wall following. Okay, so let's speed up the video to see how it finishes this demo. Okay, so here the robot also, it's doing an incorrect decision because it's always following on the right. So immediately at the end of this cell here, it detects that it has to turn back again and correct and moving just also with the with the right wall and taking the correct decision here. Okay. Okay, so let's speed up a little bit more. Yeah, okay, here is just basically doing turns and curves and so on, okay? And at the end of it, it will detect the line and the robot will stop. There it is, okay? So thank you very much.
Hello, in this video I'm going to explain a well-known algorithm that will allow you to solve motion planning problems by making the robot behave as if it were a bug. That is, it tries to emulate the behavior that bugs have when moving around the environment. The aim of this presentation is to explain fundamental characteristics of bug algorithms as well as their main assumptions regarding with the knowledge about the environment and the robot. I will explain two fundamental algorithms known as Type 1 and Type 2 that use contact sensors for their implementation. We will see their differences and analyze the worst and the best case scenarios in terms of traveled distance. Bug algorithms assume a local knowledge of the environment. That is, that we do not necessarily to know all the objects in the environment in advance or to compute an offline path in the motion path planning problem. They can be indeed implemented online with data coming from sensors. Like any motion planning algorithm, we will assume that the robot position is known, and so it is the goal configuration. So we want to find the route between the robot and the goal, and if it's possible, a short one. The robot will behave like a bug, which means that it will incorporate basic algorithms such as wall following, obstacle avoidance, and some basic motion primitives such as moving forward or turning. Bug algorithms can be implemented with contact sensors, although range sensors can be also used as long as we can estimate in one way or another the geometry of the obstacle to avoid. They are complete algorithms, which means that if there's a solution, they will find it. Bug Type 1 algorithm is a complete algorithm that its implementation steps are rather quite simple. The robot moves in a straight line towards the goal until it detects an obstacle or it reaches the goal. In case of detecting an obstacle, the robot moves around its perimeter, and once it has completed the full loop, decides to move to the closest point to the goal, moving again around the perimeter. In the worst case, the robot will travel the half of the perimeter again. So then step 1 will be repeated trying to reach the goal. So in each iteration, the robot will be gradually approaching to the goal. Here you can see a sequence of the steps of this algorithm. First, straight movement towards the goal until it finds an obstacle. Then avoids the obstacle and departs from the closest point to the goal. So it first completes a full loop and then needs to find the closest point. Then this process is repeated until the algorithm reaches the destination. Type 2 algorithms poses a simpler situation that can provide even better solutions than Type 1 algorithm, but in some cases. This depends on the environment, basically. Instead of performing a whole loop around the obstacle, it departs as soon as possible, exactly when it crosses the line, joining the start and goal configuration. At that point, the robot moves again in a straight line towards the destination, just like before. Here we can see an example with the sequence of steps of Type 2 algorithm. In the simplest cases, this algorithm is generally more efficient than Type 1 algorithm. However, there are cases in which, due to the shape of the environment, the robot can enter in a loop situation as shown. Therefore, we must modify this algorithm to avoid this loop. If we know the geometry of the obstacle, we can compute the proper direction that allows us to depart from the closest point to the goal. Therefore, the direction to take will depend on this condition to guarantee that the algorithm is complete, just like Type 1 algorithm. So every time we try to avoid an obstacle, we have to depart from the closest point to the goal. To finish this presentation, I would like to analyze the best and worst cases in terms of travel distance by each of the algorithms. Obviously, the best case for both algorithms is that the travel distance is just right the distance between the start and the goal configuration. However, this is quite unlikely because it implies that there are no obstacles at all. The extreme case is where every time the robot finds an obstacle, it is just right in the middle of the perimeter of the obstacle. Generally, type 2 algorithm will have a shorter travel distance as long as the number of intersections with this obstacle is small, ideally 1. In this video, I have explained PAC algorithms. It is a well-known motion planning technique used in simple robots with contact sensors. Thank you very much. Hello. In this video, I'm going to explain how to implement BAC Type 2 algorithm using proximity sensors in CoppeliaSim, VREP, and DioRobot. The aim of this presentation is to learn how to implement BAC Type 2 algorithm. This algorithm was already explained in a previous video. It allows you to compute proper robot movements to avoid obstacles, behaving as if the robot were back, as shown in the figure. Specifically, we're going to use CoppeliaSim and DioRobot using proximity sensors, the sonar sensor to detect the obstacles or the objects in the front, but then also the lidar sensors that are pointing to the sideways to detect or to follow a wall. I will explain actually how to program the robot so it can rotate, it can move forward, it can follow walls or avoid obstacles. And additionally, I will show you how to introduce some randomness to decide whether you want to avoid the obstacles following the wall on the left or on the right. In the video description, you will find a file with environment settings that I have prepared for you, so you can adapt it for your own convenience. Keep in mind that in order to properly follow this presentation, I have already explained in a previous video all the theoretical aspects regarding with this algorithm, how it works basically. So maybe you need to check the video. And also maybe you need to check the videos in which we solve the maze using the proximity sensors for CoppeliaSim, since many of the functions that I am explaining in this video were also used there. So all these videos I'm referring to, they are included in the video description with some links. The algorithm can be implemented with the following diagram. First, the robot starts turning in state 1, trying to point to the goal. Then it moves in a straight line until one of the two following conditions are met. Either the goal is reached or an obstacle is detected. In the case of reaching the goal, obviously the robot will just simply stop. In the case of detecting an obstacle, the robot will rotate randomly in one direction, left or right, and will start performing a wall following algorithm using the lidar sensors. This usually requires a minimum rotation time, so the robot can rotate about 90 degrees. And then once the robot is following the wall, then it has to avoid the full obstacle. But first we need to make sure that the robot is on the correct side of the line. So we need to check if the line condition has been crossed or not. So once this condition is met, then it's a moment for a robot to turn back to state 1 and point again to the goal. So on the next iteration is closer to the goal. In order to implement this type of algorithm, we will use proximity sensors available in DioRobot. Actually, both types of sensors, ultrasound and lidar sensors. In order to measure the distance from these sensors, we can use the getDistance function I'm providing you here. And this function has been already actually introduced in previous videos and makes use of SimRead proximity sensor function of CoppeliaSim API to obtain the actual distance. So this algorithm needs to know the robot position, basically to know if the robot has reached the goal, or also, for instance, to check if the robot is on one side or the other side of the line. So therefore, we need to get access to the robot pose and also the position of the initial and goal configurations to perform some computations. So in the provided file, there's a dummy named robot pose that will allow us to access to the robot position. And in addition to this, there are also two other dummies, init and goal. They are named init and goal that will allow us to compute the imaginary line between them. So to access these variables of interest, in CoppeliaSim, we use the simGetObjectPosition and simGetObjectOrientation functions. Here I show the actions that the robot must perform in each of the states that I mentioned before. This code actually must be implemented within the syscall function, and indeed the state variable that you can see here in this code must be initialized to 1 in the syscall function. Also, you see some functions like to pre-compute the wheel splits to make a turn or to follow a wall. These functions will actually explain later. So also, in order to succeed, in order to implement the state machine I mentioned before, we also need to implement the state transitions. So basically, you need to implement the code I'm showing you here. So as you can see, there are some lines that require to be implemented using some auxiliary functions that I will provide you afterwards. So actually, the code I show you here must be implemented in the syscall sensing function. And the important thing basically is that variables such as pointing to goal, goal reach, object front, wall side, or line side, these variables, they must be activated depending on the robot position, the data read from sensors, and so on. Okay, so in order to succeed, you must adjust some parameters of each of the functions I'm about to explain, especially tolerances. But basically, please use common sense. So let's start with the pointing to goal function. So the purpose of this function is to return, on the one hand, a Boolean variable that indicates whether the robot is pointing at the target within an angular tolerance. This tolerance is basically represented with the red lines in the figure, as you can see. And also this function returns the direction of rotation that the robot should take in order to point towards the goal. So it will return +1 if we need to make a left turn, or it will return -1 if we need to make a right turn. So also I'm providing here a couple of functions to introduce some randomness. So this is useful when detecting the obstacle with the ultrasound sensor. So basically what you have to do is you have to call this function every time you find a new obstacle. So you need to provide a new direction, either the left or right. In this case, the init random function I'm showing you here must be just called once in the initialization code, while the select random direction must be evaluated every time you want to change your direction. And it will return basically +1 or -1 depending on each of the directions. So then we have the pre-compute turn function. So this function allows you to pre-calculate or pre-compute some angular splits needed on each of the wheels in order to perform a 90 degrees turn. And it will also return the minimum time necessary to perform this turn. So indeed, this function is identical to the turning function that was already explained in the videos for solving mazes with proximity sensors, and is actually used just when the robot detects the wall in front of it. Then we need to call this, or when we are in the state to make a turn, we have to call this function. Also, the wall detected function you can see here will return true or false based on the distance returned by the leader sensors, and in this case, if the distance of the sensors is within expected band or range, it will return true, and this depends on the tolerance parameter and also on the d-wall side parameter, that is basically the distance or the medium distance, expected distance for the sensors. And actually this function again is quite similar to the one we already saw in the video for solving mazes with proximity sensors. And here we have the follow wall routine, in which allows you basically to implement the following or the wall following control to make the robot actually avoid the obstacle. So again, this this function was already explained in the previous video. Basically, it needs some parameters to perform the proper control in order to do the wall following. This function here, line sight, is a new function, and basically it returns +1 if the robot is on the on the left side of the imaginary line between the start and the goal configuration, and it will return -1 if it's on the right side, as you can see in the figure. So this information is indeed useful whether to decide if it's necessary to depart from the obstacle towards the goal again. And finally, we have the goal reach function that determines that the robot has reached the goal. And basically what we are doing here is just simply comparing the position of the robot and the goal. And if the robot is within a given region, as indicated in the figure by the tolerance parameter, then we can say that the robot has reached the goal. Well, in this video I have explained how to implement bug type 2 algorithm in CoppeliaSim using proximity sensors to avoid obstacles. Now your task is to implement the code that I have provided and complete all missing parts, as well as proper adjust the parameters so it works as shown in the following video. Thank you very much. Hello. In this video, I'm going to show how the bug algorithm works in CoppeliaSim software. So here what we have is the robot, as you can see. We're using some extra dummies to actually succeed with this algorithm. We have an init dummy just right here, and also we have a robot pose dummy that it is exactly in the same position as the init one, but it's a child of the robot, so it will move with robot. And then we have a goal dummy that, here we have the environment I have prepared for you. So we have a goal dummy, which is that one. So the goal of the robot is to reach the goal from this initial position, obviously trying to avoid these obstacles that I have prepared here. So let's show how it works, this algorithm. Let's change the view with this top view here so you can actually see how it works. Remember that I have introduced some randomness in the code, which means eventually left or depending on this random behavior. So you can see here now it's doing the wall following, or it's in the wall following state, and it will be in this state until the robot crosses this line here. This line is just simply for visualization purposes, okay? So it's not actually used in the code. And then you can see that the robot, it's about to cross, and then here will turn, and once it's pointing to the goal, it will just move forward again. Here it is. And now could rotate left or right, you never know. Now it's turning here to the left and performing the other or this part of the perimeter of the obstacle. So let's wait to finish this this simulation to check that it works. Okay, so now basically we'll turn and point to the goal, and it will detect that you have reached the final, or you have reached the goal, and then it will stop, as you can see. Okay, so thank you very much. Hello, in this video I'm going to explain a well-known technique to solve motion planning problems in robotics that can be used in mobile robots, but also in robots with higher degrees of freedom. The aims of the presentation are, on the one hand, to introduce the classic concept of potential field methods. I will explain how to compute different types of attractive potential functions and repulsive potential functions. In addition to this, I will also explain how to control a robot based on the gradient of the potential field. Finally, I will address situations that typically produce local minima and other common problems of this technique, and some solutions will be proposed. The main idea behind potential fields techniques is very simple, indeed very simple, but at the same time it offers a wide range of possibilities. A potential function is defined by two functions, the attractive and the repulsive ones. The attractive potential function depends on the robot and goal configurations, while the repulsive function depends on the robot and obstacle configurations. The functions are designed in such a way that the robot will be attracted to the goal and will move away from obstacles as if it were a ball under a gravitational field that seeks minimum energy configuration. An attractive function must have its minimum in the goal configuration. Typically, we use quadratic or conic functions. The quadratic function can take a very high values when the robot is far from the goal, but at the same time is smooth in the vicinity of the goal. While the conic function is proportional to the distance between the robot and the goal, however, in the vicinity of the goal it changes abruptly, having a first-order discontinuity. So the conical parabolic function combines the two previous ideas, so inside behaves parabolically, that is, it depends quadratically with the distance, while outside it behaves conically, that is, depends linearly with the distance. In this case, the parameters that define the function are, on the one hand, the distance at which a function changes from conic to parabolic, and on the other hand, the constant of the parabolic function, for instance. The repulsive function is defined by two distances. The first is a distance that beyond that distance the function has no influence on the robot, and second, a minimum safety distance to avoid the obstacle. On the other hand, the parameter epsilon r modifies how this repulsive function affects the robot. So combining both potentials, we can build a total potential function. Note that computing this potential function only requires distances to the goal and obstacle configurations. This can be done very easy if a map is available, but also considering sensor information. Thus, this technique can be implemented as a state feedback control law with a known environment or as a sensor-based navigation method. It can be used for global or local path planning. So, to plan a route, we must follow the opposite direction of a gradient, because the gradient is a vector whose magnitude and direction will depend on the robot configuration, but also on the goal and obstacles. And luckily, the negative gradient will point in the direction that minimizes the potential function. Therefore, to implement the potential field technique, we need to compute the gradient of the potential function. This gradient can be seen as a force that pushes the robot. In this case, the robot's own dynamic will act as a filter, and this type of control generally is smooth, although it might have certain or some oscillations if friction is not included in a dynamic model of the robot. Another common alternative is to establish a speed control, so that the speed is proportional to the gradient. In this case, most common implementation is the steepest descent method that uses the unitary gradient vector and a step size that controls how much the robot moves from one iteration to another one with the lambda parameter. The attractive function has a single global minimum in the goal configuration. However, when combined with the repulsive function, local minima might appear in some configurations that might be difficult to predict if the whole configuration space is not fully analyzed. This happens in configurations where the gradient becomes zero, and as a consequence of the balance between the attractive and repulsive forces. The figure shows that there are some initial configurations from which the robot will not be able to reach the goal configuration. Local minima are equilibrium points. However, we can escape from such equilibrium points by adding some kind of energy, such as a little push to one side or another, that might be enough to be able to reach the goal configuration. In this sense, there are some approaches that try to exert virtual forces in perpendicular directions to the repulsive force, or establish some random movements if the robot gets trapped in a local minimum. Here we observe what happens if we apply a small perpendicular force whose magnitude increases if we detect that the robot it's moving slowly and we are still far from the goal. A classic problem that arises with this technique is facing, for instance, U-shaped geometries, which will inevitably cause that the robot gets trapped in a local minimum. In addition to this, the technique will generally present oscillation problems if the step size is too large. And similarly, in environments that are crowded with obstacles, the repulsive forces can be significantly higher than the attractive one, which can cause the robot not to pass between obstacles even if physically could be possible. In this video, I have explained a well-known motion planning technique known as potential fields. Thank you very much. Hello. In this video, I am going to explain how to implement a well-known technique for obstacle avoidance known as potential fields in the CoppeliaSim software or VREP. So these presentations have several objectives. Obviously, the main objective is to know how to implement potential fields technique in CoppeliaSim using specific method which is known as gradient descent approach. So in addition to this, I will also show some cases where the technique fails to accomplish its task due to local minima issues. So the idea is to use a laser ranger finder sensor to avoid obstacles in real time. I will show how to reach a fixed goal and also how to follow a dynamic target. Both cases implemented exactly the same technique. In the video description, I have included a link with a file in order to implement this activity. It consists of an environment in which the robot must try to reach a fixed goal, in this case a red flag. Depending where the red flag is placed, you can find situations in which the robot will reach its goal, but there might be other cases in which the robot is trapped in a local minima, as you can see in the third example. I encourage you that once it works for you in a simple scenario, try to solve more difficult scenarios like the ones shown. Also, I have left another link to a file with the purpose of showing how this type of algorithm behaves when following a dynamic target, moving around the environment and changing its position over time. Specifically, I have used an agent included in CoppeliaSim software named as Bill, so the robot will try to follow him. You can try first with an empty environment, and then also you can try a situation full of people or another including obstacles as shown. So now you know what it can be done. I'm going to explain how to achieve that. So we need to start by preparing the simulation as a scene. So we need to create a dummy that will be a child of a robot Pioneer P3DX. And it must be aligned with the wheel axis. And also the X, Y, and Z axis of the dummy must be pointing as indicated in the figure. So the X axis is pointing forward. To access to the robot position, we will implement this simple code. On the one hand, we will access to the handle of the object that we have previously created, and we will create a post variable with the current robot configuration at the initialization section of the program. This variable will also be updated in the syscall sensing function by calling the update robot pose function. As you can see, this function returns a vector with the position x, y, and the robot orientation, later needed in some of the functions to be implemented. In addition to this, we will add a Hakuyo URG0xLX laser sensor. You will find this sensor inside the sensors category in CoppeliaSim model browser. Note that there are 3 different models for the same sensor, and I have used the second one. So once you add it to the scene, the sensor appears as Fast Hakuyo in its name. So you must place this sensor just above the robot, also aligned with the wheel axis, and make it child of a robot too. Also take into account that the sensor orientation must cover the front side of the robot, as shown in the figure. So in order to access to the laser sensor data, we need to implement the getMeasureData function in the code script associated with the laser sensor. This is a function that simply returns an internal variable with the X, Y, and Z points of the laser. So once we have this function, we need to implement also another function that I named getLaserPoints, and this function must be implemented inside the robot script code. This function indeed calls the other function, so it calls the getMeasureData function to obtain laser data, but since they are in separate code snippets, we must use the call script function in order to get that information, and this is part of the CoppeliaSim API. Please note that the getLaserPoints function returns a list with the X and Y coordinates of the laser points relative to the sensor position. So the potential fields technique has been explained already in a previous video, and I'm including in the video description a link to that video I have just mentioned, just in case you don't know this technique. So if that's the case, I recommend you to watch the previous video. But here I will just make a brief summary so you can know how to implement this technique. This technique basically defines two potential functions, one attractive and another one which is a repulsive function. The attractive potential function combines a parabolic and a conic function. The value of the function basically depends on the distance between the position of the robot and the goal. So it doesn't matter if it's a fixed goal or a dynamic target. The formula is the same. It just simply changes the information, the variables. In fact, you don't need to implement the potential function. You must implement its gradient. The gradient is a two-dimensional function in this case that returns a vector, one with an X coordinate value and another one with a Y coordinate value. The attractive force function shown returns the attractive force so that the robot is attracted towards the goal. This force is actually the negative or the negative gradient, so don't forget to change the sign of the gradient function for its correct implementation. As you can see, I have included a snippet of the code you need to implement, but the formal implementation is still missing, so that's your task. The parameters epsilon p and c are must be properly adjusted. To avoid obstacles, we need to implement the repulsive potential function that depends on the distance to the obstacles. And therefore, in this case, we get those distance from the laser sensor, which returns a list with X and Y coordinates of all detected points as a set of laser beams. And we can compute the distance to each of the obstacles just simply by computing the variable d sub I on the formula. The repulsive potential is affected to the robot only if the obstacle lies between an influence distance and a safe distance, defined by the parameters qinf and qmin, respectively. Note that both the repulsive potential and its gradient include a summation term, which means that all laser beams must be taken into account. The repulsive force function returns the repulsive force relative to the robot position, so your task is to complete a missing part of the code and return the repulsive force. So you should provide values for the influence and safety distance parameters as well as the repulsive constant. Indeed, this is one of the most critical parameters, and if it's too large, the robot will be highly affected by obstacles, while if it's too small, the robot will collide against obstacles. Once the attractive and repulsive forces have been obtained, we must combine them and apply the kinematic control law that allows us to safely guide the robot towards the goal. Here I propose to use some kinematic expressions that I also explained in a previous video. I am including this link in the video description also, just in case you missed it. It's a very simple kinematic controller that computes the angular wheel speeds, and in this case the X, Y, and theta position of the robot will be obtained from the robot pose, and the attractive and repulsive force vectors will be obtained from the previous function described. The parameter P is known as the wheelbase, and it's a distance from the wheels to the robot center, while parameter R is the radius of the wheels, and parameter B ref is the reference velocity, and parameter E allows to regulate or is a distance for the off kinematic control that allows you to or affects to the control law. Okay, so in case you don't have or you don't know how to adjust these parameters, I suggest to watch the video I have just mentioned before. And the last function to implement is just a function that combines everything. So in this case, you need to, or it needs to return the wheel speeds based on the robot position, the attractive and the repulsive force, based on the previous slide. Just implement the formulas on the previous slide. So in this video, I have explained how to implement the potential fields in CoppeliaSim VREP. In the following video, I will show how this works in two different scenarios. Thank you very much. Hello, my name is Leopoldo Armesto, and in this video I will show how potential field techniques works in an implementation that I have prepared in the software CoppeliaSim VREP. Okay, so in this case, what I have is a Pioneer P3DX robot. Let's zoom it. Here it is, and basically I have added first a dummy here, just aligned with the wheels of the robot, as you can see there, and the x-axis is pointing forward, which is this direction, and this will allow me to get the robot position. But also I have included in this case the main sensor, which is this Hokuyo fast Hokuyo laser sensor, which is also pointing, the X direction is pointing forward, okay, as you can see there, and it's also aligned with the wheels, okay. In the environment, I have prepared several obstacles, like these plants here and these obstacles there, and also I have included a goal that the robot must reach, which is right here. It's just a flag, as you can see, which is actually is not cannot be seen with the laser, because I have disabled some detectable properties in this case, and corresponds to this object here. Okay, so let's zoom out and see how this potential field works. Okay, so let's start the simulation, and you can see that the robot is moving. It's basically detecting obstacles with the laser scanner, it's avoiding them. Okay, so it's working properly. And there might be situations in which, if you try to execute this kind of simulations, if you place the flag in a different configuration, probably just here, just behind one of these obstacles, the potential field techniques get trapped in a local minima, and probably the robot doesn't know how to solve it. Okay, so it works in some situations, but it might fail in another situation. Okay, and you will see that in this case the robot almost gets trapped here, because it does not know how to in this case avoid this obstacle, but it's slowly turning, and then it realizes that it has a gap here, and then it's able to move towards the flag. Okay, there might be, I suggest you to try scenarios in which basically the path that the robot must follow is just a straight line that must oscillate or make smooth turns to avoid obstacles, but otherwise it will get trapped in a local minima. Okay, thank you very much. Hello. In this second video, I will show how this potential field method works with a dynamic target. In this case, the code is exactly the same as the previous one, in which we have to reach the red flag, but the only difference is that now we have to follow the build character, which will move randomly here in the environment. And this is a character that has been created by CoppeliaSim, and the behavior is not that intelligent, but yeah, it avoids obstacles and turns randomly. Okay, so let's play or start the simulation and see how it works. Okay, So in this case, this build character is moving in the environment and it's getting close to this corner. Okay, so probably will because of the direction, we'll probably do some weird things here. Yeah, that's it. Let's see if it's able to escape from this trap we have set. Okay, looks like now it will be able to escape. Yeah, okay, that's it. There it is. And now the robot, as you can see, it's just simply following the character. Eventually, it's, as you can see here, it's avoiding obstacles. So it's not only following the character, but also avoiding obstacles as well, okay, as you can see. Okay, so thank you very much. Hello. In this video, I'm going to explain a well-known algorithm that will allow you to solve local motion planning problems, moving the robot safely around the environment while trying to reach a target configuration. The aims of this presentation are, on the one hand, to understand the fundamental characteristics of the vector field histogram algorithm and its variants, VFH plus and VFH star, and differentiate them. I will explain how to build primary, binary, and masked polar histograms from sensor data, and also how to obtain candidate directions and to know how to choose the best one under a given criterion. Throughout the presentation, we will see that the algorithm contains an important set of parameters that we will have to tune properly to work, such as thresholds, value sizes, cost function weights, and the amount of prediction steps. Tuning these parameters is not that intuitive unless you know what you're doing, and it depends on the environment of the robot. The VFH or vector field histogram technique assumes that we can build a 2D occupancy map or a cell histogram that incorporates unreliable measurements from range sensors such as ultrasound or laser. If not, we can always use raw sensor data. The main idea is to reduce this map to a polar histogram based on a preliminary ideas known as virtual field force. Subsequently, values are detected in the polar histogram using a threshold, which means that those sectors of the histogram that do not exceed the threshold value are considered as free sectors. This threshold is a critical parameter in the algorithm and must be properly tuned. Once values have been found, which are nothing than a set of sectors below that threshold, the one that is closest to the target direction is selected, and within that valley, a direction to move according to the valley size is selected, distinguishing if it's a wide or a narrow valley. The VFH technique introduces some improvement over the previous technique, incorporating binary polar histogram, which uses two thresholds with hysteresis, which improves the smoothness of the resulting motion planning. In addition to this, it also considers the robot size in order to build the primary polar histogram to avoid implementing a low-pass filter of that histogram. It also includes the concept of unreachable directions, considering that the robot has a limited turning radius due to the kinematic or dynamic constraint. Those directions cannot be reached if they have to go through directions that will collide with an object. Finally, it also improves the decision criterion of selecting the correct direction by incorporating a cost function that allows to define a behavior. And a couple of years later, the VFH star technique was introduced, which includes as main novelty the fact that it makes predictions for n steps to build a tree and uses the A-star algorithm to compute an optimal route. The fundamental idea is that prior to making the decision of which is the best candidate direction to choose, the VFH star algorithm simulates those candidate directions and obtains new robot positions, and reevaluates the VFH plus algorithm. based on those new positions. After n steps, a tree is built with candidate directions, and the A-star algorithm allows us to choose the best one in one step, let's say, direction. That minimizes the tree. So in order to implement those techniques, we need a first step, which is basically to build a cell histogram whose values are updated based on the range sensor measurements after several passes, and they will provide somehow a certainty of the cell being occupied. This process can be improved if we use occupancy maps, which provides the likelihood of each cell of being occupied. The 2D cell histogram is converted into a polar histogram, that is a one-dimensional histogram. In this process, the size of the robot is taken into consideration, which avoids having or to use a low pass filter to smooth the polar histogram. So for each cell, a magnitude is computed depending on the cell distance to the robot and its occupancy likelihood, and then the cell magnitudes are accumulated on their corresponding polar sector, and the size of the sector is a fundamental parameter of the algorithm as well. Here we see some of the formulas used for building this polar histogram. As mentioned, we must first obtain the cell magnitude, which depends on the cell distance to the robot and its likelihood of being occupied, and some parameters related with the active window size. Each cell has an associated influence region depending on the robot size, and we usually add even a safety distance to this region, and this defines an angular region which is denoted with the variable gamma and determines if the cell magnitude are accumulated for a given sector K. The binary polar histogram uses two thresholds to determine which sectors are occupied and which of them are free. It transforms the accumulated values into ones or zeros depending on whether they are above or below these thresholds. Indeed, in case of being between the threshold, hysteresis mechanism is used so that the previous value or the value that we had in the previous iteration is used. And the last histogram we need to build is the masked histogram. This histogram takes into account the fact that the robot has some kinematic or dynamic constraints, and therefore there's a minimum turning radius. This implies that if, in order to reach a free sector or a sector that was classified as a free in the binary histogram, if we need to reach, in order to reach that sector, we must necessarily go through another sector that might be locked, then in that case, those sectors will be also blocked. And here I show the binary histogram and the mask histograms. And as you can see, the red zone in the mask histogram are marked as forbidden directions, because in order to reach those directions, the robot must necessarily pass through the orange region. And because of the minimum radius, which is depicted in the green circles in the figure, this cannot be possible without colliding. So once we have the mask histogram, we can detect the valleys, which are basically a set of sectors marked as free sectors. And we made a distinction between what we call narrow valleys and wide valleys. Narrow valley represents a region in which the robot can pass through, but is surrounded by obstacles, and therefore there's only one possible direction, which is just basically pass through the middle of the valley. And on the other hand, we have a wide valley, which represents a region with obstacles far away from the robot. And in this case, we usually can take the decision, or the candidate decisions to make are to move through the left or the right edges of the valley as candidate directions. Although it could happen also that the target direction is within the view, within the valley, and in that case, we also consider that that direction is also a candidate direction, obviously. And among all possible directions, we must select the best one. And for that, this the VFH plus algorithm defined a cost function that we need to minimize and considering aspects such as target distance, robot orientation distance, and previous direction distance. The weights of these three criteria allow us to implement different behaviors in the algorithm. The VFH plus algorithm uses a tree with candidate directions to determine the best direction to make based on a prediction. It builds a tree with n steps. Each node of the tree represents a robot position that the robot would reach in case of taking or a given candidate direction. In addition to this, a discount factor is introduced so that future decisions have less influence than immediate decisions. In the figure on the left, it's shown how the algorithm results vary depending on the amount of prediction steps. So this is an important parameter of the algorithm. And on the other hand, the figure on the right shows the tree with all possible directions, and the one that the algorithm A star has determined to be the best route is depicted or highlighted in black. Obviously, if we are able to provide good predictions, the algorithm performance will be significantly better, avoiding to get trapped, as usually happens with pure local motion planning algorithms. In this video, I have explained algorithm based on the VFH method, vector field histogram method, used in motion planning techniques for mobile robots equipped with range sensors. Thank you very much. Hello. In this video, I'm going to explain how to implement the VFH plus algorithm using a plugin for CoppeliaSim. This is a plugin that I have created to demonstrate how this motion planning algorithm works. In the video description, I have included some information about how to get this plugin, and I also recommend you to watch the explanatory video about the VFH plus algorithm as indicated in the video description if you're not familiar with this algorithm, since I will assume that you know how it works. So the aims of the presentation are, on the one hand, to explain how to configure CoppeliaSim to be able to use the VFH plugin and to be able to use such plugin to avoid obstacles trying to reach a goal. I will explain the plugin's API, so that's it, the set of functions that you need to use in order to make it work. And particularly, I will describe the parameters that are required to make this plugin to work properly. As also, I will explain some of the return data so you can use it to understand how this plugin works. So we will start by preparing the simulation scene. So we need to create a dummy that will be child of the Pioneer P3 DX robot, and it must be aligned with the wheels with the X, Y, and Z axis pointing towards or as indicated in the figure. So to access the robot position, we will need to implement this code. On the one hand, we will access to the robot handle of the object that I have previously created, and we will create a pose variable with the current robot configuration or pose. And this variable will be updated in the syscall sensing function, and just simply by calling the update robot pose function. And as you can see, this function returns a vector or a table with the position XY and the robot orientation. Later, we will need this variable in some of the functions to be used. In addition, we will add also a Hikuyo URG04LX laser sensor. You will find this sensor inside the sensors category of the CoppeliaSim model browser. Note that there are 3 different models from the same sensor for the same sensor. So I have used the second one. So once you add it into the scene, the sensor appears as a fast Hikuyo. You must place this sensor just above the robot, just on top of it, and you need to make it child of the robot. So whenever the robot moves, the sensor will also move as well. Also take into account the sensor orientation as shown in the figure, so we can cover the front side of the robot. In order to access to the laser sensor data, we need to implement the getMeasureData function in the code script associated with the laser sensor. Okay, so there's a script associated with this laser sensor, and we need to access to this script. So this function actually just simply returns an internal variable with the X, Y, and Z data points of the laser sensor. And then we need to implement the getLaserPoints function inside the robot script code. This function indeed will call the getMeasureData function to obtain laser data. But since they are in separate code snippets, we must use the callScript function on the CoppeliaSim API to get such information. The getLaserPoints function will actually return a list with X and Y coordinates of each of the points returned by the laser sensor. So CoppeliaSim allows you to create your own plugins. And you need to compile those plugins using Qt. It's a environment software for developers. So after compiling this plugin, the dynamic libraries that are generated in the once compiled, you need to copy into the CoppeliaSim binary folder. You need to copy the results of the compilation. In Windows, you need to copy the DLL file, while in Linux and Mac OS, you need to copy the SO or the dylib file respectively. Okay, so you need to copy the dynamic libraries inside the binary folder of CoppeliaSim. Once copied, in order to check that the plugin has been detected properly, after starting CoppeliaSim, you can see in the console message a message indicating that the plugin has been successfully loaded. Okay, so please check that it's working properly before going on. So the plugins API I have created, it's for implementing the BFH plugin algorithm. It's rather quite simple. It has an initialization function that you must call inside the syscall_init function that will be in charge of allocating all required memory. It also has 3 functions that will allow you to obtain polar histograms, desired movement direction, and also the angular speed of the wheels to be applied. And these functions will normally called within the syscall actuation function. And finally, there's a function to free all previous allocated memory that will be called in the syscall cleanup function. Here I detail the input and output arguments of each of the functions. Okay, so let's start with the init function that accepts 2 input arguments with the algorithm parameters. Here you can see that the required order of the parameters that the function is expecting. And also I include a brief description on them, and also indicate the expected units of each of the parameters. Later I will explain what each of these parameters they represent. The algorithm assigns a default value for each of the parameters, so you can even provide an empty list for each of the parameters, and then you will use in the default values. In case of an error, the function will return -1, otherwise it will return 0. The getHistogram function returns the polar histograms computed by the algorithm. That is the primary, the binary, and the mask histograms. It needs data from rate sensors. In particular, this function is prepared to process data from a laser sensor, although it is also processed, or it's prepared to process data from ultrasound sensors type. Although this feature is not described here in this video. So if no sonar sensor is available, please provide an empty list. So indeed in the laser scan input argument, we must indicate a sequence of XY points detected by the laser sensor, which is actually the information that was returned on the functions previously described. So this function returns the primary, the binary, and the mask histograms. These are indeed tables with information from each of the sectors of the algorithm. The binary and the mask histograms return a table with Boolean variables, being true in case of a sector is occupied and false if it's free. Only the mask histogram will be used to determine the desired direction of movement, while the other 2 histograms can be printed in the console, and that will help us to understand how to tune the algorithm properly. The getDirection function evaluates the mask polar histogram and determines the desired direction of movement. So for this purpose, you need to provide the position of the robot. This is a table with the position and the orientation as we explained before. And also we need to provide the position of the target. The function returns 3 arguments. The first one is the desired or selected direction of motion. The second one is the target or where the target direction is pointing to. And the third one is a table or a list with all candidate directions found in the mass histograms. All these values represent actually angles with respect to the robot orientation. And only the selected direction will be used to compute the actual motion, while the other 2 output arguments can be used just simply to display internal algorithm results. And finally, the getMotion function allows you to obtain the angular speeds of the robot wheels. This requires the nominal linear speed, the selected direction, and also the robot pose and the target position. Here, I explain some of the parameters that are required by the plugin. The laser scanning angle determines the field of view of the algorithm, so all possible directions that we will compute within this algorithm have to be inside or within the range of this parameter. And also the sector angle will determine somehow the number of sectors that the algorithm is using, and hence the size of the histograms. The safety distance is used to enlarge laser detected points, so they have a possible influence on neighboring sectors, while the stopping distance determines the region from which the robot must stop if the target is within that region. And the window size allows you to determine the size of the health histogram. This cell histogram is actually used to build the primary histogram. And a fundamental parameter is also the cell size, which determines the resolution of that cell histogram. Additionally, the algorithm uses 3 parameters that will have influence on the number of candidate directions that you obtain in the mass histogram. So on the one hand, we have the binarization thresholds that we use to determine what sectors of the primary histogram are considered to be free or occupied. And on the other hand, we have the minimum number of sectors that are required, so we consider the valley to be a wide valley. Also, the weights used to determine which is the best candidate direction, the one that minimizes the objective function, and this is actually the one that affects to the final decision of the algorithm. And these weights are associated to the distance with respect to the target direction. Another one is a distance with respect to the previous taking direction, and also with respect to the current robot direction. So, most of the cases, it is interesting to visualize some of the results of the algorithm. And here I just simply show you a code that I use to draw some lines to represent 3 sectors, also the selected direction and the target direction, as well as some candidate directions. This visual information can significantly help you to understand what is happening in particular situations. So to draw these lines, we use the drawing object function of CoppeliaSim API. That basically, if you copy this code, it will return the handles of objects to be drawn. And also, it is expected we remove these objects at the end of the simulation. Here I include the draw sectors and draw sector functions that will allow you to draw these lines using the information obtained from the algorithm, such as the directions and the mass polar histogram. It needs some extra variables that we need to provide, such as the handle of the laser sensor to obtain its position, and also some parameter of the algorithm, such as the safety distance and the sector angle. I have underlined those variables and parameters we need to provide with different colors to properly run this code, so you can identify them and you know how to make it work. Okay, so in this video I have explained how to use a plugin implementing the VFH plus algorithm in CoppeliaSim. In the next video I will show you how it works. Thank you very much. Hello, in this video I'm going to show how the VFH plus algorithm works using the plugin I described it in my previous video. And the idea is to show you how it works, but first let me show you what we have. We have a robot, a Pioneer 3DX robot, and we have a laser scanner just on top of the robot. And we have also a dummy here that we use to get or to access to the position and orientation of the robot. So the algorithm uses the laser scanner to detect objects in the environment, and the idea is that we want to reach this flag here, which is our target. Okay, so let's run the simulation and we will see how it works. Okay, so first you will see here these green lines represent the mask histogram, which are basically representing those directions that are considered to be free of obstacles. And then you also have in cyan, you have candidate directions that depend on what we have in the mask histogram. We might find several candidate directions. In black, we have always a direction pointing towards the target, which is our desired direction, but this is not always possible. So that's the only direction that we actually take is the one which is in blue, this short direction here. Okay. So as you can see, it is not always possible to move towards directly the target direction, although there are situations in which it's possible because the free space is actually, or the target direction is actually available in our mask histogram. Okay, so as you can see, this algorithm actually is performing pretty fine because it's trying to solve more hard situations that we was able to do with artificial potential fields with a pure reactive algorithm. And you can see that in most of the cases, what we're doing, we're just basically surrounding the obstacles. Okay, so because there are two possible, in this case, for instance, there are two possible candidate directions. One of them is closer to the target, which is why we are selecting that one clearly instead of that one. Okay, and once we pass to this obstacle here, we will be in a situation in which our target will be actually in our field of view. And then in that case, you will see that we will have another candidate direction directly pointing towards the target, which is actually the one that will be selected. Okay, so you will see that very soon right now. So here is turning, and now you can see there that clearly we have this one is pointing towards the target and is the one that we are selecting. Okay, and that's how it works, how it's expected. The flag actually is not detected, and it's not collatable, so it's just simply for indicating where we have to go reach or where's the destination, and once it's reached, we stop. Okay, so thank you very much. Hello, in this presentation I will explain how to obtain occupancy grid maps typically used in mobile robots with range sensors. The aims of the presentation are, on the one hand, to understand the concepts associated with Bayesian fusion and how it can be applied to map building problems using occupancy grid maps. In addition, I will explain how to obtain sensor probabilistic models, and particularly the ones related with range sensors such as laser and ultrasound sensors. Finally, I will explain how to efficiently implement the map building process using log-odds ratio probabilities. Let's start with a brief summary of Bayes' rule. This rule postulates that given a sample space with disjoint events, AI, the probability or likelihood of an event AI knowing that information B has happened or has been acquired corresponds to the relation between the probability of AI intersecting B and the marginal probability of B. The law of total probability transforms such marginal probability into a sum of probabilities. Bayes' rule allows to compute the posterior likelihood of an event after acquiring new information based on our prior likelihood for such event. For the specific case in which the sample space is binary, which means that there are two only possible events, for example, heads or tails, occupied or not occupied, open, closed, in that case, the formula of the Bayes rule simplifies to the expression shown. Since we only have two possible events, the probability of one event is just the complementary of the other one. This formula can be expressed in a recursive form, which means that the posterior probability depends on the prior probability in the previous iteration. Sub-index k denotes the time instant with the available information. Let's see a simple example that will help us to understand the application of Bayes' rule in case of detecting whether the door is open or closed. Suppose the robot detects a door with a vision sensor, and after some image processing, the vision sensor provides a 60% chance of detecting that the door is open. The initial probability that the door is open or closed is 50%, which represents that our initial knowledge is null. Suppose that we observe on several occasions the same situation, and in all of them the camera returns a probability of 60% of being open. As you can see, after the first measurement of the probability is 60%, which corresponds exactly to the probability that the sensor has provided, because our initial knowledge was 50% of being occupied. After several measurements, the probability increases despite of the fact that the sensor always provides the same probability. This highlights the importance of the Bayes rule, since it's using the prior knowledge to obtain new knowledge after incorporating the measurement. Under this premise, the probability will increase and will tend to 1, which is 100% of being occupied. Occupancy grid maps are nothing more than cell maps with an occupancy probability, being the probability of each cell independent of any other cell. This probability is a value between 0 and 1. Robot sensors will provide a likelihood for each cell of being occupied. Over time, since sensor measurements will include some uncertainty, the recursive Bayes rule will provide a filtered estimation. The appearance of a map may change over time, incorporating the presence of new obstacles. And in order to build a map, we are required to know at least the robot position, and estimating such position is out of the scope of this presentation. In this figure, I show an occupancy grid map, how it looks like. In this case, I have used a color scale in which the white color means that it's 100% occupied, while the transparent color means that it's 100% free, unoccupied. This map can be used for motion planning purposes, for instance, but even also for locating the robot position. Given their flexibility to represent a wide range of obstacles of any shape, they are widely used in mobile robotics. So, in order to build a map, it is essential to have a probabilistic model of the sensor that transforms the sensor measurements into probabilities, which depends on the sensor type. For instance, in the case of a rain sensor, it is expected that the probabilistic models return a probability above 0.5 near the cells that are close to the heating cell. That's the cell that we have detected the obstacle. While it will be lower for the rest of the cells. The important thing is that the sensor should never provide 0 or 1, since this means that we have a total certainty that the cell is being occupied, it's occupied or not occupied, and that will imply, regardless the sensor values we get later, that will imply that the cell likelihood won't change. The algorithm gets stuck. The tensor model is something we can decide. It can be obtained from many different ways, and it can be also obtained, let's say, from an experimental model. Here I propose some ideas that I consider to be reasonably suitable for building maps. Considering that the sensor has some uncertainty associated to the measurement, it seems reasonable to use a Gaussian that describes the probability of a cell being occupied for a given measurement. The main problem of the Gaussian model is that the probability beyond the measurement distance decreases and tends to 0, which will inevitably decrease the likelihood of those cells, even if they are behind the obstacle. One way to avoid this is to include a memory effect, so those cells tend to 0.5 instead of 0. If the sensor provides a probability of 0.5, the cell likelihood will not be modified after applying the Bayes rule. In addition to this, for shorter distances, the Gaussian model also tends to 0. This is fine if there are no unexpected measurements or objects in our environment, but it might happen that we have some kind of unexpected object, then we might consider to truncate the Gaussian to a minimum value to avoid that the cells have a very, very low value over the time. A representation that provides many advantages for a map building problem is the so-called log-odds ratio, which is defined as the logarithm between the ratio between likelihoods. In this representation, a probability of 0 implies a log-odds ratio of -infinity, while a probability of 0.5 provides a value of 0, and a probability of 1 implies a log-odds ratio of +infinity. The advantage of this representation is that Bayes' rules update is basically transformed into a sum between two numbers: the prior likelihood, that's the value of the cell, and the sensor likelihood. Thus, updating the map implies just simply to take the previous cell values and add up the sensor probabilistic model in the log-odds ratio representation. Here we can see the saturated Gaussian I mentioned earlier, how it's transformed into the log-odds ratio representation. Only the values that are above 0 will be those that increase the probability of being occupied, while the values that are below 0 will decrease the probability. A value of 0 will not modify the value in the previous iteration, and therefore those cells can be ignored. Implementation of this algorithm is actually quite straightforward. For each sensor, we must obtain the cells that are affected by a given measurement, which in case of range sensors, we can pre-compute locally for a given beam orientation. Let's say, for instance, a laser sensor has a very precise beam, and rays or the beams are treated as a ray, and therefore we have to do the ray tracing to find the cells that are affected by that beam. But sonar sensors usually have a much wider beam, like a cone-shaped beam, and therefore we have to find which cells are affected by that measurement. So in the end, for each cell, we need to compute the distance relative to the sensor position, and since we are building a local map for now, this can be known in advance. In the image, I actually painted in red the cell that corresponds to the position of the sensor, while I have painted in orange the cells that have been affected by that measurement. For each cells, we need to get now the likelihood of being occupied, and then we can do that by just simply consulting a lookup table. Here I show some a very basic example with very few values in the table, but obviously the resolution can be increased and obtained with more precision in order to obtain interpolated values. These values are actually obtained from the formulas I've shown before. Also notice that in the Bayes rule update, I have included some saturation functions so that the values are always between a minimum value Lmin and a maximum value Lmax. This will be a truncated likelihood, but the advantage is that in case we have some or we are moving in dynamic environments, the changes will the changes of the map will reflect much faster, since we're avoiding the integration of those values over time. In this presentation, I have explained how to build occupancy grid maps from probabilistic sensor models using Bayes' rule, and some tricks for its efficient implementation. Thank you. Hello. In this video, I'm going to explain how to build occupancy grid maps using CoppeliaSim and the Grid Map plugin for CoppeliaSim. This is a plugin that I have created to show how to build occupancy grid maps. In the video description, I have included information about how to get this plugin. I recommend you to watch the video explaining about occupancy grid maps if you don't know how they work, particularly because I'm going to assume that you know about occupancy grid maps when I talk about the parameters of the plugin. The aims of the presentation are, on the one hand, to explain how to configure CoppeliaSim to be able to use Grid Map plugin and to build maps of an environment. I will explain the plugin's API so that you know how to use it, and particularly I will describe the required parameters to make it work, as well as the information that the plugin provides to you. To start with this lab session, we will start with from the results that we obtained from a previous lab session about performing the tracking of trajectories using the Pioneer P3DX robot. In the video description, I have included a file with all necessary elements to carry out the trajectory tracking. I also include a link to the video where I mention all the maths behind the trajectory tracking implementation provided in the script. The purpose is to build a map of the environment as the robot moves along the path. As a consequence, I also provide the functions to read data from the laser sensor. Bear in mind that in this video, the robot's movement is totally independent from the laser data. What you do with the map that you have built is something that we will see later in other videos, such as, for instance, using it for motion planning or avoiding obstacles. So, in order to build a map, the robot must move through a suitable environment. You must therefore build an environment and modify the route so that the robot moves around the environment. My recommendation is that you use part of the elements that CoppeliaSim includes, such as office objects and many others, to build the environment and adapt it to your own convenience together with the route, so that the robot can detect all elements in the environment with the laser sensor. Here I show you an example of what I have created for this purpose. Yours can be even simpler. Here I show how the plugin that I'm about to describe how it works. Okay, as you can see, the robot builds a map incrementally as long as it moves from room to room. The cells in the map that are drawn in black are occupied cells, while the cells or the free cells are painted in white. The cells that do not have any, or we don't have any information, are colored in gray. Keep in mind that the laser sensor, as it works in CoppeliaSim, only returns points if an object is detected, which means that if the object is below the maximum distance associated with this laser sensor, then we will get a point. Otherwise, we don't get any information about the environment, and therefore this point or this information is not included in the map. And that's why you can see that despite of the robot is moving on a big area, the map is not updated. After after a time, you can see that we could be able to successfully build a map. Now I will explain how the plugin works. As you probably know, CoppeliaSim allows you to create your own plugins that you can compile with Qt. After compiling the plugin, a dynamic library is generated that you must copy into the folder that contains CoppeliaSim binary. In Windows, you will need to copy the DLL file, while in Linux and Mac OS, you must copy the SO or dylib file, respectively. Once copied, you can check that the plugin has been detected properly if after starting CoppeliaSim, the console shows the indicate message. The plugin API that I have created is rather quite simple, and it has an initialization function that allows you to allocate memory that must be called inside the syscall init function. By default, the map will be an empty map, although you can load an existing map from a BM or bitmap file that you have previously saved or created. If you load the map, you have to take into account that when you created that map, you have to also use the same parameters during the initialization of the map, because there's no metadata, such as, for instance, the cell size, saved in the bitmap file. The update map laser will allow you to update the map based on the information that we receive from the laser sensor and its position, obviously. After finishing the simulation, you must release the allocated memory by calling the release function at the syscall cleanup function of the CoppeliaSim script. Before that, we might be interested in saving the map using the save map function to use it, let's say, for later use. The plugin also includes two auxiliary functions such as getMap and getPoints. The first one returns the occupancy grid map, and the second one returns the points of the cells that are occupied. Both functions can be useful for later purposes such as motion planning or avoiding obstacles. Next, I will explain the input and output arguments of each of the functions. So let's start with the init function that accepts two input arguments. The first one are the parameters of the algorithm, while the second one is an argument that allows us to control if we want to display the map in a separate window or not. Here I indicate the order of the parameters that this function expects, as well as a brief description of them, and I even also indicate the units of each of the parameters in case they have units, obviously. On the one hand, you need to provide the parameters that define the size and the resolution of the map. You also need to provide parameters that define the minimum and maximum probabilities for each cell in the map. And also you need to provide parameters that determine the maximum distance that you will use for your laser sensor, as well as its accuracy, its precision, because we use that for ray tracing to know which are the affected list of cells for a specific ray. The last set of parameters, as you can see, are related with the probabilistic model of the sensor, and what I recommend you is to watch a video explaining about occupancy grid maps, as I said before, if you want to have a better understanding on how these parameters work. Okay, so on the other hand, also the release function does not accept in this case any argument, so you just simply can call it with the parentheses, and this usually it's called to free the memory reserved by the init function, and this has to be done in the syscall cleanup function as mentioned before. The save map function allows you to save the map results in a bitmap file. Then this map can be retrieved and used when you use the load map function. In both cases, what you need is the file name to load or to save with the bitmap associated to that bitmap file that you are going to use, and this is usually located in the plugin binary folder. The get map and get points functions allow you to obtain information about the map, and they can be used for, as I said, for many other purposes. So the get map function returns a map, which is just basically a matrix or table in a matrix form with the values of the cells of the occupancy grid map. If you provide the input argument, the p threshold input argument, then the return map will be a binarized map. So we use this threshold to binarize, and then the values of the table will be values with true or false, being occupied or not occupied. Moreover, also the get points function returns the coordinates of occupied cells. In this case, both functions, they use this threshold, and this should be a probability between 0 and 1, but obviously it is expected that this value is higher than 0.5. Finally, the update map laser function is the one that does all the dirty work in order to update the map based on the laser information and its position. This function must be split or typically used within the syscall sensing function once you have your laser update. Well, in this video, I have explained how to use CoppeliaSim grid map plugin in order to create occupancy grid maps. Thank you very much. Hello, my name is Leopoldo Armesto, and the aim of this video is to help you to identify links and joins in serial robot manipulators. So in order to do that, I have prepared 3 simple demos based on the IRB140 robot from ABB, the UR3 robot, and also a scalar robot. These are models that are available in VREP, but I have modified them and adapted so you can it can be used for this purpose to identify links and joins. Okay, but so let's start with this robot. So we have the base of the robot, which is the fixed link. It's named link 0, and then we have this joint here. It's a vertical joint, as you can see, that will be in charge of moving this first movable link, which is link 1. It's painted in red. And then we have joint 2, which is that one here. It's a motor that it's horizontal. I mean, the axis is horizontal, and it's in charge of moving this second link here, the colored in green. And then we have joint 3, which is that one, okay. And we'll be move this joint, this link here, which is the one in yellow, okay. And joints 2 and 3 are usually horizontal, and the first 3 joints of the robot are, or this robot in particular, are designed to control the position of the wrist point of the robot. The wrist point is a point right here in the middle in which joints 4, 5, and 6, these joints 4, 5, and 6 intersect in a point here. This is called an inline wrist, and this is the wrist point, And it's very important because with the first 3 joints, we will be able to position this point here. But with the other joints, we'll be able to rotate and orientate the tool here. Okay, so let's joint 4 will be a joint here that will be actually in this position will be aligned with sorry, not aligned, but in this position is horizontal, yes, and will be in charge of moving this link 4 here. As you can see, joint 4 will move this joint link 4 here. And then we have joint 5 that will move the blue one, which is link 5, and then joint 6 will move the end effector link, which is that one here. Okay, so let's run the simulation and to see how this works to control the joints manually. So we have the first joint that is used to orientate the robot arm. Then we have the second and the third joints that will be able, together with the first one obviously, to control the position of the wrist. And then we have joint 4, which is moving this link here, yeah, joint 4. And then we have joint 5, which is that one. And yeah, and then we have, if we zoom, you will see it, we have joint 6 moving the end effector and the tool. Okay, so this is for this robot here, but now let's move to a different robot, which is, or very similar robot indeed, but it's the UR3 robot. It also has 6 degrees of freedom, and in this case there's a slight difference that I will mention later. Okay, so let's start with link 0, is that one here. Then we have the joint 1 is the vertical one. Then we have the red link here is the link 1, and then we have two horizontal joints, joint 2 and joint 3. And joint 2, it's in charge of moving this link here, the green one, and then joint 3 will move the yellow one. And now then the difference with respect to the previous robot is that joints 4 and 5 intersect, but not the 6th joint. Okay, and that makes slightly the inverse kinematic of the robot makes it slightly different. Okay, but as you will see, you can obviously you can control it as well. Okay, so the idea here is that joint 4 will move this link 4 here, joint 5 will move this link here, and the last joint will move the end effector. Okay, so let's play the demo and let's see how it works. So this is first joint, this is the second joint, the movement of the second joint, this is the third one, fourth one, this is the fifth one, and then if we have, yeah, and then we have the last one, which will be in charge of controlling the orientation of the tool. Okay, and now to end this video, I would like to show as well a scatter robot. This robot here has 4 joints. 3 of them are revolute joints and 1 prismatic joint. Okay, and here we have the first link, which is link 0. It's the base, is the fixed one. And then we have 2 joints, which is joint 1 and joint 2. They are vertical and they are in charge of controlling the XY position of the end effector here. And joint 1 moves links 1, which is that one, and joint 2 moves link 2, which is that thing here. And then we have a prismatic joint here with here a link that will be moving in and out. And then we have a 4th joint which will be in charge of rotating the end effector, which is this suction pad here. Okay, so let's see how, let's run the demo and let's see how it works. Okay, so we have the first 2 joints will be in charge, as I said, to control the XY position. The third joint will be in charge of controlling the Z position. And the 4th joint will be just simply in charge of controlling the orientation. And this is sometimes useful when you want to insert components. Okay, so in this video, what we have seen is I have prepared demos, a set of demos to help you to identify links and joints in serial robot manipulators. Thank you very much. Hello, my name is Leopoldo Armesto, and in this video I would like to explain you how to control a robot with a parallelogram structure, like it is the case of the UARM robot, that it is available by default in the CoppeliaSim model browser, but I have made some modifications so you are able to control it using the inverse kinematic module. And the idea of the video is to explain what type of links and joints do we have in this type of robot, how they're configured, and particularly how we configure the inverse kinematic module so that we can implement, in this case, closed chains like the ones that appear in this type of parallelogram robots. Okay, so let's start by just simply first describing which are the links and joints that we have in this robot. So we have the first joint, the first link that we have is the robot base, is the fixed one. It's link 0, and then we have a vertical joint here, which corresponds to a motor that this robot has inside here. And this joint will move the link 1, which is the one I painted in red. And then from here, what we have is, we actually have two joints mainly. Well, we have three, but we have two joints. The first one corresponds to this motor here. It's a horizontal one and will be in charge of moving this link here. The third joint, this one here, will be indirectly moving this bar here, but in the end will, because of this mechanism here, will move this link here, which is the third link. Okay, we will see how this works. Okay, but let's basically describe how this works. Okay, and because of this mechanism, this parallelogram mechanism, when we move these two links here, this is the end effector that will be always moving according to these two links and always in a horizontal position as it is designed in this type of robots. Okay, so let's try to understand how this kinematic hierarchy works for this type of robot. So let's start with the first link is the first joint and link is rather quite straightforward, but let's start with the second joint here. It will move the second link, and now what I would like to do is to close a kinematic chain so that this bar here it's always attached to the first link. So what I do is I have a joint here, I have a link that will move according to this joint. I have a dummy that I will explain later, but I have another joint here, and depending on this joint I have another link, and then at the end of it I have a dummy. This dummy is linked with a dummy that I have attached here that depends on the link one. It's through a joint, an auxiliary joint. So these two dummies are on the same position, but one of them it's controlled with the motor 2 or the second joint, while the other one will be attached to the first link and it's just simply freely rotating with this joint. So the idea is that CoppeliaSim is able to compute the correct values for the angles for these joints so that whenever we move this second link, the structure always is attached here to the first link. Okay, so that's the idea. And in order to do that, what we have to do is just simply double click here on the dummy and select in this case which dummy you want to link it. And in this case I link it with sorry, I link it to this dummy here. And the link type I selected is the inverse kinematic tip target type. And that's how we have selected or how we have configured this relation. Also, we have on this side, let's see it from this side. So again, from this link here, whenever this link here moves and rotates, remember we have a dummy here that I said that I will mention later, but also we have another joint here, which is that one. With this joint, we have that whenever this joint moves, that we can move this link here, this is the third link, and then we have another closed kinematic change here. So This is another joint, auxiliary joints. This is another link. This is another joint, and this is the last link. And in this case, what I've done is I have a dummy just right here that depends on this kinematic chain, and another dummy that depends only on the orientation of this motor here, this joint. Okay, and these two dummies are also linked. So whenever I rotate this dummy with this motor, what I would like to do is the software to compute the correct orientation for this dummy here, and indirectly compute the proper positions for the joints so that everything matches here. Okay, so actually the third joint will be indirectly moving the third link, as I said at the beginning. Okay, and with this motion and together with the second joint, this bar here will change the orientation, and this bar here also will modify. The orientation of this link here will be modified. So indirectly, now what I would like to do is to close this kinematic chain here. Okay, and to do that, what I have is this joint here, yeah, which depends on the third link, this joint here, and then I have the end effector, which is the fourth link here, and then I have another joint, and then I have this link, and then at the end of this link I have the tip of it, which is linked with the one I had and the one I mentioned at the beginning, which depends on the third auxiliary link here, as you can see. Okay, so in order to make this simulation work, we have to make sure that the joints are in the proper mode. So the first, second and third joints, the ones with the motors, are in passive mode. As you can see here, they are in passive mode. The 1, 2nd and third are in passive mode. The rest of links are, well, the fourth as well, because it's a joint. I haven't explained it, but it's a joint to eject this tool. But the thing is that, to rotate this tool. But the thing is that the first three joints that are the ones I'm interested in are passive joints, and the rest of joints, the auxiliary joints, are all of them in inverse kinematic mode, which means that the software will compute the position of this joint by its own, okay, with the inverse kinematic module. So as you can see, this is inverse kinematic, this is inverse kinematic mode, inverse kinematic mode, inverse kinematic mode, and so on, okay? And once we have the dummies linked and we have the joints in the inverse kinematic mode, then what we have to do is to configure the inverse kinematic module so that the software solves all the problem for us. So in order to do that, we go for the calculation modules, we go to the kinematics module, and then we have to create a new ICA group. In this case, I have created already, and I have configured it in this way. As you can see, I have checked the mechanism is redundant. I have set as the calculation method the DLS, which is one of my preferred methods. I have configured 100 iterations and this damping parameter here. And then I edit the ICA elements. And then I added 3 tips, the ones dummies with the A. And as you can see, all of them depend on the UR link 1, because all of them depend on this, the movement of this link here. And the first one, it's constrained in the X, Y, and Z position. The second one, it's a special one because I have also selected this gamma position, because the second one is this dummy I have here. That one I have in here. I have selected the gamma here because I want this joint here to be moved that will rotate this dummy, and the orientation of this dummy is important so that it's forced to be the same of this one, and indirectly will move this bar here. And the third one, which is that one here, the third one is that one here, only has the constraints X, Y, and Z, so it's only constrained in position. It's free in orientation. Okay, so with that, what we have is also created a script that I will add to the description of the video, because this yellow font that we have for the user interface is not easy to see. So I will copy paste this code in the video description, and that's just simply to create, as you can see, a user interface, a very basic user interface, so we can play around with the joints. So if we move the first joint, you can see how this robot works. It's just simply these first joints. It's useful to orientate, obviously, the robot arm to the correct direction. This is the second joint that is actually moving this second link, remember? And as you can see, as long as I move this joint, the rest of the structure, this parallelogram structure, moves accordingly, thanks to the inverse kinematic model configuration that we have set. And then the third joint indirectly will move this link here, which in turns will move this link here. Yeah, as you can see. No matter what, but always the end effector is horizontal thanks to this parallelogram robot structure. Okay, so thank you very much. Hello, my name is Leopoldo Armesto, and in this video I'm about to explain how to configure a Delta robot to make it work with CoppeliaSim. So the idea of the video is to help you to identify links and joints of this type of robots, how they work, and also its hierarchy. So we are also going to talk about the inverse kinematics model of CoppeliaSim, so this kind of robot can work. Okay. CoppeliaSim actually is a software that by default, using the hierarchy structure that I explained in the previous video, only allows you to create serial link manipulators, but with the help of dummies, which are just simply objects that we will place in specific places, we will create some kinematic constraints that will ensure that there's a constraint, in this case of position, so the robot behaves as a parallel robot indeed. Okay, so let's start by describing how this robot is made of. And this is link 0. This is the fixed link. This is the first of all links. And then we have 3 arms. As you can see here, we have 3 arms. And they correspond to each of these joints. So this is joint 1, joint 2, and joint 3. 1, 2, and 3. And from here we have 3 arms, as I said. And at the end of it, what we have is a platform. That will be the end effector of the robot. Okay. You can see that right now the platform is not properly positioned, or the arms are not properly positioned corresponding to the platform, but don't worry, we will solve that. Okay. So the thing is that let's try to understand first the hierarchy of these 3 arms. As I mentioned, we have a revolute joint here, which corresponds to these servo motors that will make this link here rotate. And then we have another link here. It's the green one. Let me just occlude for now the joints. So this is a second link that will be able to have displacements left to right, and also it will be able to rotate because here we have a cylindrical joint. So in order to implement this cylindrical joint, in VREP we don't have such type of joints, but we can do it by just simply combining, let me show it again, prismatic revolute joint. Okay, so this is the prismatic joint and this is the revolute joint, all of both of them on the same coordinates, and this will allow this link to shift and rotate. This is exactly what we want here. And then we have, from this link here, we have 2 spherical joints, the one on the left and the one on the right, as you can see. And then we have 2 actually bars or 2 links, the left one and the right one. Yeah, and that's actually our serial manipulator here, as you can see. Okay, and this arm finishes just simply with those dummies that you can see here, those ones here, this one on the left, this one on the right. And as I mentioned, they should be positioned here, but for now they are not. So it is that we're going to establish a relation between an inverse kinematic relation between this dummy here and this dummy here. And also we are going to do the same here with this one here, sorry. This one here, okay, that one there and that one here. So the CoppeliaSim software solves the inverse relation that we want, okay? And okay, so now what I need to explain is about the platform. So the platform, we have, as I mentioned before, 3 prismatic joints here that will allow me to freely move the position of the platform. We have a tip. This is exactly the position of the platform that we want to control. And in order to do that, what we have is also another dummy, but this is fully independent. It's in the wall, it's in the scene, and it's the reference point, which means that the idea is that we want to move the reference point here, this dummy, we want to control it, and we want to make sure that this tip here that depends on the platform moves correspondingly to this reference point here. And because we have these joints here, obviously if we move the reference point and they are linked to the tip, then these 3 joints will be used to position the platform. So the platform will be moved, and the values for these 3 joints will be computed based on how we move this reference point here, okay? Always in the inverse kinematic relation, as I'm about to explain, okay? So this is the platform, and then the platform has actually has exactly the same. Let me just hide this first. It has 3 links, as you can see here, 1, 2, and 3. That will be the bars here below for those arms, and obviously these links also have these prismatic and revolute joints that actually they act as a cylindrical joint, each of them. And then the links have 2 dummies, as you can see, one on the left and one on the right. So now the goal is to make all the proper connections for the inverse kinematic module to work. So it's quite easy actually. So as you can see from the names, is what we have to do is double click here on the dummy and create a link. So we link it, this one here, we link it with its corresponding target dummy. And once we do this link dummy, you can see here a red line. That means that both dummies are linked. And the type of link, we were going to use the inverse kinematic tip target link type, okay, by default. So we have to do the same thing with the rest of links. So this one will be related with that one. That one will be related with that one, and you can see here also in the hierarchy scene that these connections are created, okay, indicating that both dummies are linked. So that one will be related with that one, and that one will be related with that one, and that one here will be that one. And then the last one we have to do is the reference point and the tip. Okay, so we have all the connections that we want. And now, one thing is to have the connections, and the other one is to know how to solve them. So in order to do that, we have to use the inverse kinematics module that you will find in the tools menu in calculation module properties, and then you have the kinematics. So what we have to do is add a new inverse kinematic group. And because of the configuration of this mechanism, I select the mechanism is redundant, and then I have the DLS calculation method. This is why I choose that one. On how these methods work, it's a topic for a different video, okay, but for now I'm happy if you select, for instance, 100 iterations on these damping parameters. This is the usual configuration I use with this method. And then we have to actually set the constraints that we want. Okay, so the idea is that we select the inverse kinematic elements that we want, and here we have to select all the tips that we want to be part of this inverse kinematic group. So we have to select this one here, the tip, and as you can see, by default, this one already, obviously, it knows that this one here is linked with the corresponding target here, okay? And we have to select the base. By default, you have the wall, but in this case, I think it makes sense that if you minimize everything here and you see that both links depend on link 0, the actual base should be link 0. Okay, and we have to do the same thing for the rest of dummies. So let's add that one here and select link 0, and let's add this one here, select link 0, and that one here, select link 0, and then we have the third one left and right. Okay, I'm sorry, this is link 0 and this is link 0, yeah. And as you can see also, it is important to set the constraints. In all the links I have set up to now, we have the X, Y, Z constraints, which means that these both dummies will be forced to have the same X, Y, and Z position. This is exactly what we want in order to make sure that this bar here goes to this position there. Okay. And also, in order to finish with this presentation, let me just simply add the tip join also, the tip dummy, and this one will be ready with the wall because the reference point is in the wall. Okay, so this is everything we have to do in order to set the proper inverse kinematics for this robot. And now I'm going to run the simulation, and as you can see, as long as I run it, the inverse kinematic module has already placed the bars on the corresponding position. Also, I have a script here in which I have put just simply the control of the reference point, so to show you how this robot works by moving the corresponding position of the reference point. Here, what I'm changing by moving these sliders, in the video description I give you the code for this script. Okay. What I'm changing in by modifying these sliders here is just the reference point's position. The rest is done by the inverse kinematic module. Okay, thank you very much. Hello, my name is Leopoldo Armesto, and in this video I will explain how to compute the workspace of a 6 degrees of freedom robot arm, such as the case of the IRB 140 ABB robot. The idea is that we will use CoppeliaSim in order to generate such workspace, but then later we will move into MATLAB to compute the boundary for the workspace and save this boundary into a file, and then add it or read that boundary file in CoppeliaSim and check if a candidate position that we would like to reach with the wrist of the robot, it's inside of the workspace, so we can freely move inside this workspace. Okay, so let's explain what we have here. We have the ABB IRB 140 robot, as I said, but I have just simply simplified the robot, so I just keep only the essential elements that I would like to use for this simulation. These are a set of shapes that, as you can see here, are hidden in the default layers that are simplified shapes. If you want to see what they are, it's just simply a simplified mesh of the actual robot. Okay, these shapes here, and then we have the visible ones, which are the ones you're seeing here. All of them are static shapes, which means that they do not have any kind of dynamics and they are not respondable. Okay, so they are just simply purely kinematic simulations. And in particular, the ones which are hidden, I have enabled the collidable property here, as you can see, but the ones with the visible ones are not enabled. Okay, you can see that that one is collidable, but that one is not collidable, and so on. Okay, that's important because the idea is that I would like to generate the workspace of the robot in such as that I would like to detect the collision of the robot with the ground floor, or even any kind of object that I have here, or even I can add a tool here and include this tool as part of my computations. Okay, so this is a very specific case, but once you have it, it will help you to know if, for instance, a candidate point is inside your workspace, or let's say if you want to generate a path that can be reached by the robot, then it's worthy to have visually this workspace and some computations that I will show. Okay, so Now I have explained what we have here. Let's move to explain what I have configured in this simulation. In particular, I have a collection. A collection is a set of objects that belong to a single list that allow us to select or compute collisions as a one. So they are treated as a one single object. And the idea is that you have to you have to add or create this collection. The name of the collection is just simply collection. That's the default name. And in theory, you have to select this tree of selected object, and then this object selected, and then click add, and then we'll add these elements here. And if you want to make sure that everything is fine, you can visualize the selected object, and here you can see that all objects inside are part of a collection, and that's what we want. Okay. Then later also we have the wrist dummy. This dummy here, it's just here in the middle. Is actually in the wrist of the robot. It's just here in the intersection of this joint here and this joint here. There's the wrist. It's positioned there. And the idea is that we would like to compute the workspace for all possible configurations of the wrist that are free of collision, as I said. Okay. So in order to do that, what we have to do is we have to go to calculation module properties here, and we have to create two collision objects. First one, it's using the collection I have selected, or I've shown before, and it's checking the collision against all other entities in the simulation. And that's what I named as robot collision. That's just simply a name. And then the second collision object I have configured is this one here, which is the IRB 100 underscore link 7, that one here, that will also check the collision against all other entities, particularly if it's colliding with the robot itself. Okay, so now we have the collections here. That, remember these names, robot collision and then effector collisions, because these are the names that we are going to use in our simulations. And now let's see the script we have here for this example. The first part of the script, as you can see here, what I'm doing is just creating a file to write a set of data, and the name of the file by default is irb140 underscore workspace.xyz, and this file will be stored and once the simulation is stopped, will be stored in the CoppeliaSim binary folder. Okay, so you can look there and see the contents for that file. Okay. Then the script basically gets some handles, as you can see here, the joint handles, and also it's querying which are the interval of the limits for each of the joints, and also gets the risks handle, and also gets the handles for the collision objects that I showed you before, and they are named here as call check 0, call check 1. Then what I do is I generate a sweep of possible configurations with the robot, and that's the important part in which you can configure how precise or not you want to be in your computations. But the idea is that I have created a function which is called join sweep. It's just here. Okay, and this function basically what it's doing is it's starting on a specific a joint number. In this case is the second one to the third one. This is the final one. I want to do the sweep, and this is the initial value of the table, and this is the return value with filled with configurations for that table. And what I'm doing is I'm setting all possible configurations here depending on the amount of steps I want for each of the joints. In particular, I would like to do the sweep only with the second and the third joint. These are this joint here and this joint here, because the first one, it's just simply the joint that it allows me to point to a specific direction. So, but I'm interested in computing the workspace on this plane for a specific Q1 angle. And so I would like to do the sweep with these two joints, and then for each of these configurations I have here, so these curved configurations I have here, I also would like to test all possible orientations of the end effector. So that's why I do also the joint sweep using joints 4th and 6th using this accuracy here. Just simply to mention that the amount of steps, the actual amount of steps is always adding up one more. Okay, so for instance, in the case of the 5th joint, we're actually testing 3 possible orientations, which means that the end effector is pointing, let's say, straight downwards to the left or to the right. And then we have 9 possible orientations for the 4th joint, which will just modify the orientation of the end effector. Okay. So in the end, we will have a set of configurations here in QRIST and QEnd, and then we do here in the actuation code, what we do is just basically to set the positions of the joints to such configurations in a way that for each of the possible configurations for the wrist, I check all possible orientations of the end effector, and then I check if there's a collision in that specific position. If there's a collision, these values will they will return 1. So in any case, if we detect a collision, we just simply reset the counter for the possible orientations and move to the next possible wrist position, which means that, okay, we will discard this configuration. But if everything is okay and there's no collision, then we will in the end add a new configuration, and we just simply get the position of the wrist, and this is what we store in the file with the tabs as a separation for each of the positions, and also I add the configurations Q1, Q2, and Q3 that generated that position, just in case. Okay. At the end, I stop the simulation and obviously I close the file. Okay. So if we run this simulation here, let's see what's happening. The robot is doing the sweep, as I mentioned. It's doing a lot of computations trying to see if there's a collision or not. For now, there's no collision here, but there are situations in which the robot will start colliding itself, and then we restart with a new configuration and so on. Okay, so we can speed up these things here and wait until it's done. But okay, you can imagine that at the end of the simulation, we will have the file that I mentioned before. Okay, the one that will be inside the CoppeliaSim binary folder. Okay, so for now, let's stop, and now let's move to MATLAB, in which I have prepared a script too, in which we just simply need to load the file that we have generated. We keep the first and the third column, which are the X and Z, actually the X and Z coordinates, and with this code here, we generate the XZ boundary of all these possible points that I have generated with the file that I have here, the XYZ file. Okay, and then I just simply plot the points, and then I also do a Delaunay triangulation and store that in a STL file, so I can import it inside CoppeliaSim. Also, I'm interested in saving in a file these XZ coordinates here, that the boundary that you will see in a file, so I can use them also in CoppeliaSim. Okay, so let's run the script, and you will see that the results are rather quite simple. So that's actually our configuration, or the workspace that we have created with all possible configurations sweep that we have been created. At the beginning, all these points were filled here, a lot of points that were valid for free of collisions, but we only have taken the boundary. Okay, and that's this thing here filled with triangles and everything. That's what we have stored in the STL file, and the boundary points, that's what we have stored in the TX file. Okay, so now what we have to do is we have another file in which I have already imported, as you can see, this STL file here, which is the workspace of the robot. Okay, that's a file, but let me just exactly show you what, if you import yours, what you will get, because it's not exactly the same. Well, that one is fine. let me just simply show you what you have to do is you have to import the mesh. And if you go for the folder, and that's a file that MATLAB has generated, okay? And if you go to that and just import it, you have here the mesh, okay? But as you can see here, we have a lot of things that were not part of the workspace. Remember, in MATLAB, we have the boundary. This part here is empty, okay? While here is filled somehow, okay? That's because of the Delaunay triangulation. If you go for it, if you take a look to the triangles, we can see here that we have a lot of triangles that we don't need. So we can manually remove them, okay? That's a step, but relatively quite easy to perform, okay? So you have to remove all of them that you consider a part of the boundary, okay? Once you have done that, let's say yes, then you will have the proper shape, okay? In my case, let me just remove that one and enable again that one. In my case, this is what I have obtained, okay? But that's just simply a shape that I use. In my case, I only use it for visually check if a trajectory is inside the workspace and on, okay? But now what I would like to explain is what we can do with the actual boundary. Remember that we have saved a file with boundary points, and the idea is that we want to implement a function that checks if we are inside this polygon, and if we are inside, then we are free to go to that position with the inverse kinematic module, because we'll be part of our workspace. But if we are outside this polygon or workspace, then means that this configuration could generate collisions with the ground floor, with the robot itself, or whatever, okay? So I have implemented a script in order to do that. So the only difference here is that the first joints here, I put them in inverse kinematic mode that are being controlled by CoppeliaSim, okay? These three first joints are being controlled by CoppeliaSim, and what it's doing is, as you can see here, these two dummies are linked. So I will move the reference point of the wrist, and then the idea of the inverse kinematic module that it will compute the correct angle so that the wrist is at the correct position as I specify. But before moving the reference point, I would like to check if that point I would like to move, it's a safe point and it's inside the workspace, okay? And this is what I have here in this script here. First thing, I have a very simple user interface in which I have three sliders to control the X, Y, and Z position of the reference point I would like to move, okay? That's something we have seen in previous videos, and since you have the code for this script, you can learn how to use it. The main difference is that here, these values I have from the sliders, I have a candidate point, and then I call the inside workspace function. That will check if it's inside the workspace, then it will return true, and then I will actually set the position of the reference point to the indicated position, okay? I do this for the X, Y, and Z coordinates, okay? So before going to inside the workspace, let me just simply explain you what I have here. This part of the code, this part of the code is reading the TX file that I have generated with MATLAB. This file should be inside again the CoppeliaSim binary folder, so we can read it. Otherwise, we have to indicate the folder, okay? And it's reading each of the lines of this file and storing the variables in the WS, the workspace table here, with the points belonging to the boundary, okay? And then basically here I'm just simply getting some handles to properly move the things and so on, okay? But nothing more, okay? So in this function here inside workspace, I'm just simply checking, this is quite standard math, to check if a point is inside a workspace, a polygon. And then for that I do a for loop for all possible segments of that polygon, and then I check if that's correct or not, okay? and if it's inside the workspace, then I return true. Okay, so we can see how this works. Okay, let's see how this works. Let me just simply first, okay, here we have the set position. I'm moving upwards, as you can see. I can move in X forward and backward, and as you can see here, I'm not able to move even backwards because, let me, here it is. That's because of the inverse kinematic module. Okay, I'm not able to move backwards because of my inside workspace function. It's saying that it's not true, and then I'm not allowed to move to that position here. We can see also check, or we can check here, for instance, let's move here. Now I can move downwards, but then I can't move upwards, as you can see. I'm not allowed, okay, to move upwards. And even if I do that, sorry, here, yeah, there is, here, clearly I cannot move upwards. And I can move forward, but not farther than that, okay? So as you can see, it's working as expected. Okay, great. So thank you very much. Hello, my name is Leopoldo Armesto, and in this video I will explain how to compute the 3D workspace of robot, in particular the IRB 140 robot with CoppeliaSim, but we're going to compute this workspace as a 3D volume because this video is a continuation of a previous video that I include in the video description. Associated to that, we also have some files that I also include there. That the purpose of the previous video was to generate or to compute this workspace, but as a 2D plane. But now here in this video, we're going to compute this workspace as a 3D volume. So will help us to determine if any trajectory that we try to plan with this robot is within or not that workspace, and therefore if it's feasible or not to compute or to achieve that trajectory. Okay, so the idea of is to use CoppeliaSim, but also softwares MATLAB and Mesh Mixer, so we can compute this 3D volume of the workspace. So in order to proceed, first thing you have to do is to run this example here that is provided, as I said. That includes just a demo that it's computing all possible positions of the wrist, which is a point here, that are not in collision with any other object in the scene, particularly the floor and the robot itself. So all possible positions free of collisions are registered in a file with all those coordinates, and we are just simply performing a sweep with the joints 2, which is that one here, 3, which is that one here, also the 4th and 5th joint. Okay, if you run this code, you will see how it works. You can see that it's just simply performing many movements and computing if this if the wrist position is in collision or not, and if it's not in collision, then we register that wrist position, and then we save that in a file. Okay, this was already explained in a previous video, so I'm not explaining the details on how to do that. Okay, this is provided. So once you have, as you can see here, once you have the output of this simulation is this file here, once you have that, you have to move to MATLAB. Then you have to simply load the file. The idea here, I will just simply run it first, and then I will explain how it works. Okay, so let me just simply run it, this script here. Okay, here it is. So the idea is that we have a 3D, or we have a 2D workspace with the coordinates of X and Z. So the X, Z coordinates, but we have split this workspace in two workspaces. One which is with positive X, and the other one with negative X, as you can see here. Okay, and this is done up to this point here. Okay. And then we have turned or flipped this workspace and combined them, both of them. So this is a new polygon with all points of the contour of this polygon contains all possible limits of my workspace that I would like to do a sweep. And for that, what I have to do is just simply do a rotation of this plane here over the coordinate Q1, the vertical one of the robot, that will generate this volume here, as you can see. Okay, let me see, there it is. Okay, and this is, in order to do that, what I do is to create a poly shape with this polygon here, and then I create a second poly shape here, which is that one but with the X flipped, okay? And then I do the union of both of them, and then, well, this is just simply for representing all these polygons, and then what I do is just simply to create this sweep of this workspace here, contour, and I will do that from -pi to pi 100 plus 1 times, so I get in the end a mesh that I represent. And this is done with this sweep workspace function here. It just simply needs the coordinates xz and the amount of points that you want to perform the sweep. So it generates the vector with all possible angles from -pi to pi. And then here basically what it's doing is just rotating the points, so are the vertices of the mesh, and constructing a connectivity list with all possible combinations of vertex, and at the end returns the triangulation or a triangulation that I am representing. Okay, but this triangulation is not optimal, so in order to fix this triangulation, what I'm proposing is to use Mesh Mixer software, that one here, and to fix or to improve the resulting file that I save here. Okay, so I just simply need to import the file, which is that one here, and as you can see, this is the volume that I have created that contains 37,000 vertices and 74,000 triangles. So I would like to optimize that. So I just simply need to press Ctrl A to enter into this mode here, and to improve this mesh, I will remesh. Okay, and that's performing some computations here for remeshing this volume, and if I accept, you will see that the amount of triangles here, the vertices and triangles, has been significantly reduced, and that's much better. Okay, so at the end I just simply need to export and save it. In this case I have already saved it with a different name, which is that one here. Okay, and you can see that the file size is smaller, and therefore it's optimized. Okay, then what you have to do is, then again back in CoppeliaSim, what I have done is I have just simply imported the mesh, okay, and put it here. So this is the mesh that I have imported. I have also created or added some opacity here so we can see the robot itself. So now we can also, I have defined the path. You can define yours, but the thing is that this path has been on purpose created so that some points of the path are outside the workspace. So if I try to, with the inverse kinematic module, if I try to force that the wrist of the robot is following a dummy, or in this case a point belonging to that path, then whenever this point is inside the workspace, the inverse kinematic module will work fine, but if it's outside the workspace, it won't be able to reach that point. Okay, so we can detect that by just simply here, what I have done is in this mesh I have set the collidable property, so make sure it's collidable. And also I have created another object which is located exactly at the wrist position. It's just a very small sphere here, which is also collidable, and I have just removed all these respondable and dynamic properties. It's just simply an object I would like to check if it's colliding or not with my 3D workspace. Okay, and it's a very small sphere here that will indicate that I'm moving just on the boundaries of my workspace. So in order to do that, what I have done is in the Tools menu, the Calculation Module Properties, I have created a collision object which checks if there is a collision between the collidable wrist, that sphere I mentioned before, and the 3D workspace, the mesh that we have created with MATLAB. And if we detect a collision, then the collid, which is the 3D workspace, will turn red by checking this option here. Okay, and then also, as you can see here, we have the target, which is the point that I would like to follow. This target has the follow parent path option enabled, so it will follow a point on the path, and it will just simply, and it's connected, the inverse kinematic is linked to the wrist. Okay, so the inverse kinematic module, it's in here. The inverse kinematic module, I have added a new IK group, set this DLS method with 100 iterations, and edit the elements, and added a tip with the wrist, and just simply set to follow the X, Y, and Z constraints of this target. Okay, so the idea is that if you put the joints in inverse kinematic module, the three first joints, okay, joint 1, joint 2, and joint 3 in inverse kinematic module, the software will compute the appropriate angles for those joints so that the wrist is following the target. And just the last step is just simply to add a velocity to the path so that the target is moving, okay, because otherwise it's stopped. Okay, so if you run this simulation, you will see that whenever the robot is inside the workspace, everything is fine, and the collid in this case is white, but if it's outside, it's colliding, and then it turns red. And also you can see that if you take a look here, this point red was the target point, and the wrist point was actually not following, as you can see here, not following the target if you're moving outside the workspace. Okay, so this method will help you to try to define or to design your trajectories within the workspace of the robot. Thank you very much. Hello, my name is Leopoldo Armesto, and in this set of video tutorials I will explain how to create a low-cost simulation for a low-cost robot based on the knee arm robot. It's a parallelogram robot, as you can see here, and we have several goals, long-term goals for this set of video tutorials, but the short-term goal I will show you right now a demo how it works for the individual joint control. But in long term we have also more tutorials like computing the inverse kinematics, computing the workspace of the robot, and more. Okay, so let me just simply click here and play, and let me show you what we will do in this set of video tutorials. We have an interface for individual joint control in which we are creating a dynamic simulation for controlling the robot. As you can see here, it has 3 joints and one more for one motor for the gripper, and that's how it works. And then we have also the possibility to open and close the gripper, as you can see. Okay, thank you. Hello, my name is Leopoldo Armesto, and in this video I will explain how to create the knee-arm robot in CoppeliaSim in order to simulate this robot. So let me first introduce this robot. It's a 3 degree of freedom robot with a gripper. that their design is available in Thingiverse, so you can download it and import the files. Actually, the design that you see here, it's an adapted version, a modified version that I made some slight modifications in order to allocate the electronics inside the robot, so everything will be inside the robot here, so we can easily control it, okay, including the Arduino electronics with the Arduino Nano, and also a small power bank with a battery, a lithium-ion battery. So let me first explain which is the procedure that I have followed in order to get into or to get to this step first, okay? So my design was to start with this design you see here in SolidWorks, in which I use this, obviously this software, in order to design the robot and do all the necessary modifications, okay, to, let's say, the precision of millimeter, because this is obviously software for designing, in this case, or can be used to design this robot here. And then what I have done is I have exported all these components here into STL files, and then with those STL files, then I can go to CoppeliaSim and import them. Okay, there's a slight problem. Let me show it to you here in this new sim here. So first, let's try to import a mesh. Okay, if we import the meshes, all the STL files that we have for the robot, then we have really a huge amount of files with a lot of details, extra details for the scaling. Let me just put 1 millimeter, okay? So this is actually what you should do when you start to design a robot with your STL files. And as you can see, it takes a time because there are some complex geometries here due to the STL files, okay? Some of them actually are really, really complex, and we don't want them to be such complex. So I have done a process in which I have simplified some of the geometries, particularly the screws, and also the electronics, the power bank, everything, okay? Particularly those electronics, I have simplified them. So let me just briefly summarize what I've done. Okay, so let's start, for instance, with this screw here. There it is. If we enter into the shape edit mode, then we have the screw. Then what I have done is just select, let's say, I want to decompose this geometry into two simple cylinders, one for the head, and this is one cylinder. And once I have created this cylinder, then I remove all the triangles I have selected. I didn't mention it, but in order to select the triangles, you have to hold on the shift button. And then with the rest of the triangles, you select them. There it is. And then you create another cylinder. And if you do this carefully, it's not the case. This is, let me just repeat again. The reason is, let me just do it again, is when we remove that, we leave some triangles. Let me do it like that. The reason is that we leave some triangles. We can see it here, but yeah, let me try it again. Okay, and now remove this. And to make sure, let me just simply hide this part here, this component here. Let me just hide it to have a better or a clear view. Yeah, it doesn't matter. Yeah, okay, yeah, there it is. And now let me just hide that one, the one I have created, the cylinder, for temporarily. Let me see. Yeah, that's the reason. When we selected the cylinder, we left some triangles here. Okay, so that's what we have to clear. Oops. So you have to clear all these triangles There is. Sometimes it takes more time than. There it is. Okay, now we have more or less clear all the triangles. Then we can select the remainder of triangles. Let me just, there it is. Then we have all these triangles we have here, and then we can extract a cylinder with a reasonable size. Yes, you can see. Okay, yes. And now we can remove the original shape. We don't want it anymore. And then we have this cylinder that I created first. Let me just show it again. There it is. And then we have two simple cylinders, which is much better for the simulator in order to carry out the simulation with instead of the whole complex geometry of this screw, which in terms for us, it doesn't really affect too much. Okay, I mean in the aesthetic aspects. So then we simply can group them, edit, group selected shapes. So we have one screw, and then we can call this screw. Yep. And then this is actually the process that I have followed, as I said, in order to simplify all the geometries that I consider that will be necessary to be simplified. So this is what I have done already in this step here, and actually I'm providing you with this file with all the necessary simplifications. Okay, so and the thing is that now what I want you to do is to create the actual joints of the robot. Okay, because right now they are only just simply parts and components, but there are no joints. Okay, they are just simply elements that we can move, but there's no joint that ensures that both of them are linked together. Okay, so your first step is actually to create the joints of this robot. So first we need to analyze or understand how this robot works. Okay, clearly you can see here this will be joints, these things here will be joints, and this thing here will be joint, this one here as well, this one here. Okay, but some of them are just simply spacers, screws, something that just fixing elements that they are not they are not moving at all. Okay, so you don't need to add a joint on every screw, obviously. Okay, and this robot in particular has 4 servo motors. The first one is this one here below. Yeah, and if you want to see how or what we have here inside, let me just simply first try to occlude all the elements that I have here. There it is. Okay, as you can see, this servo motor has a screw there. Okay, and this is the actual rotation axis. So we have to find out which are the rotation axes for each of the joints, and we need to create a joint. All of them will be revolute joints, that one here. And then let me just move the joint so you can clearly see what's happening here. So the task will be just to place the joint just right there in the middle of the screw. So first let's try to find out which is the name of this screw. It's self-tap screw 9. So let's select the joint, then select with the control, select the screw, and then let's copy the position of the joint corresponding to the one of the screw. Okay, and the joint, as you can see, is really, let's rename it as joint 1. And this joint is actually quite big, so let's reduce the length and the diameter. Yeah, something like that. More reasonable, yeah. And usually joints will be placed in the second row of the visibility layers. So they will be in this visibility layer. So they will be visible from whenever you activate the second layers, you will clearly see the joint there. Okay. Yeah, so now your task will be to create all the joints of the robot that you need in order to create a proper robot. So let me just simply mention that. This first joint is the joint 1, that's correct. This servo motor here is servo 2, so this is joint 2. This servo motor here is servo 3, and this is joint 3. And this is the gripper, which is the servo 4. Yeah, so it has to be joined right there. Yeah, joint 4. But the name of the rest of the joints is not that relevant. You can just simply assign whatever name you want. Okay. And remember that you have to create the joints on the proper position and orientation. So for instance, if you want to create a joint there, you just simply have to create another joint there, select, as I said, the corresponding screw, move it to the corresponding position, but also remember that sometimes we might need also to assign the correct orientation. So this is the actual axis. Okay. And then this joint here will be again with a smaller length and diameter, and there it is. Okay. Okay, so your task for this first step that I want you to achieve is to create the joints of this robot. Thank you very much. So once we have completed the first step I mentioned before, as you can see here, I have all joints created. All of them are in the hidden layer, so that's why we can't see them right now, but they are here. Okay, as you can see. And we have, remember, particular interesting joints are joint 1, which is the one corresponding to this motor here. And then we have joint 2, joint 3. So it's joint 2 and joint 3. And also joint 4, which is the one here for this motor here. The rest, the name of are not that important, okay? Also, I would like to mention that I have created duplicated joint here in this axis, particular axis here, because as you can see here, there's a joint for moving these two parts. Okay, there has to be a joint for moving these two parts, and there has to be another joint to move these two parts here. So that's why I created this joint here, which is exactly in the same place as this joint here, as you can see. Okay, and I will use them independently. Okay, also very important to mention is that all joints need to be in torque force mode. Okay, and only the joints 1, 2, 3, and 4, okay, need to be enabled and position control, because they are actually joints related with the servos. Okay, so joint 1, joint 2, joint 3, and 4 will be position control. Okay, these are the parameters for the PID controlling the servo, so it's up to you to tune these parameters if you want to adjust the speed, the maximum speed of the servo and so on. Okay, but by default it's working fine. Okay, and the rest of the joints will be, all of them will be in force torque mode. Okay, so once you have this step, now you have to create, or the idea is to create dynamic shapes with pure objects. Okay, and for that, in order to do that, we are going to create it from the actual geometry we have in the robot parts. Okay, so this is something we already have seen. It's a tedious step, but it is a necessary step, because otherwise the simulation might be very, very slow. Okay, and we don't want that. We want to have a fast simulation. So in order to do that, we can enter into the edit shape mode in order to extract pure shape geometry, like a cuboid, cylinders, and things like that, from the triangles we select. Since we don't have select anyone, we don't have any triangle selected, then we can just simply invert the selection and extract cuboid and say, okay, here it is. Okay, and then we exit from here, and then here, that's our cuboid. We can just simply call it base thin. Okay, I like to call it like that, so it's then we have the pure geometry and the non-pure geometry with the same name, but the underscore din or dynamic, okay, from dynamic, okay. And this one I like to include it or move it to the hidden layer here, and also in general all the geometries or the objects we're going to create will be dynamic and respondable. But this one, because it's the base of the robot, will be static, okay? And also I like to, in this case, I prefer to uncheck this local respondable mask, because we don't want all the parts of the robot, once we have the hierarchy of the robot with all parts and everything, they will be locally related due to the hierarchy. And if we uncheck this local respondable mask, then the robot parts won't collide, okay? At least for the moment, it's a good idea. Okay, and so if you want, I can just simply try to show you how to create also, let's say, these parts here for corresponding to the link one. For instance, if we go here, we invert the selection, we create a cuboid. There it is. Because the link one, it's composed of a lot of parts, then we have to group them, okay? And we're going to create separately the dynamic parts first, and then once we're done, we are going to group them. Okay, there it is. And also, for instance, we can create actually that one too. Sorry, shape, no, cuboid. We will need to remove the shape afterwards. Okay. Actually, this shape, this is, yeah. And now this one here, there it is. And now that one, it's a geometry, as you can see. Let me just simply show you. If we hide this, if we check this, you have a clear view exactly what I mean. The part here for the bottom part of the link one, it's narrower here and slightly wider here. For now, we don't care, okay? But if you want to do it properly, then what you would have to do is to select part of the triangles here to create a cuboid, then select the triangles here to create a different cuboid and group them together, okay? Because by default, always it has the convex hull of the full geometry, and it will actually, this bounding box you see here, this will be the size of the cuboid if we select all of them. And that's what I'm going to do right now, okay? It's not that relevant to have the proper shape, but it's up to you if you want to do it, okay? So now what we have is a set of cuboids here I have created, and now what I'm going to do is to group them. So we have to right click here, enter in edit mode, group merging, group, selected shapes, and all these will be actually now the same pure geometry, and then we can call this link one underscore dynamic. The YN, okay? We have to do the same for all the parts here. The rest of the parts are not so complex. Just beside the only thing is here in the gripper, all these parts can be grouped together as a cuboid or whatever you want to do, create here. You can even create part of this shape here, okay? And the process is quite tedious and it requires some time, okay? But just be patient and try to do the best as you can. The only mention or important thing that I would like to mention is here in the gripper, if we want to interact with objects, then maybe it's a good idea to generate a shape which will be composed, let's say, let me just simply subdivide this into more triangles like that, yeah. Create a shape, let's say like something like that for the tip. Let's see if it works. Yeah, no, it only. it needs to select more triangles here. Yeah, that's it. Cuboid. Okay, that's our tip of our finger. Yeah. Let's say we are happy with that. And now we need to select those triangles, but in particular these ones might cause problems, so let me just do it like that. Let's select this one, and let me select these ones here. Oh no, I have selected. Okay, let me do it again. Clear selection. That's it. Not responding. No. Sorry. It's not responding. Now. Okay. So let's say select these triangles here. Let's see if they are selected. Okay, and now let's select only these ones. Let's see if it works. It needs to add more triangles here. No. Let's start again. Okay, maybe I shouldn't select those ones, but that's okay. You get the idea, okay? And then you can create a cuboid from those, okay? Maybe I shouldn't select those ones, so I should select only from here. So it is that you can create purely approximately the shape of the finger. That would be better if you want then to manipulate objects, okay? So this is something I leave for you, okay? So now your task is to complete and create all the dynamics and pure geometries that you have in this robot related with each of the links, okay? Thank you very much. Okay, and here you can see the geometries, the pure objects that I have created once I have completed the previous step. As you can see here, I was able to get a proper shape for the finger. It doesn't need to be exact, but more or less approximately this shape here and this shape here, so we can figure out and interact with objects in the environment. Okay, I also created two circles here, but they are grouped and they are part of the same right now object. Okay, I also created the correct names for everything, and also, for instance, here this one, as you can see, also I was able to manage to have it in two separate objects, and then I group everything together to be part of the link one and so on. Okay, so now your task is to do a group operation with the actual non-pure shape objects that we have in the scene, because right now we have a lot of objects and we would like to have just one single object, let's say for the base of the robot. Right now we have the base, but we have also the spacers here, and we have all these screws and the servo. All these belong to the same link. So the idea is that we have to select all of them like that and so on, and then in the end click right here, sorry, right click, come on, it's not very responsive now, and group merging everything once we have selected everything. Okay, those corresponding for the base, those corresponding for link one, which are all these parts here, the servo motors, the batteries, the Arduino, these servo motors here, also everything, all these parts are part of the link one. And also, if you see a screw like that, you can decide whether to be part of this link here or be part of this link. It's up to you. It's not that relevant. But if it's a screw like that, and in this particular screw, it will be actually screwed to this part. So it will be fixed to this part. So then in that case, I would say it's part of link 1. And for instance, here again, this screw here will be screwed from here and then will be fixed to this part here. This one will be free. And then this screw should be part of this one. But that's not that relevant, okay? Like that one here, this should be free and will be fixed to this part here, okay? This one here will be fixed to these parts here. Okay, so that's a suggestion, but it's not that relevant, okay? Whether they belong to one or the other one, because you won't notice probably the difference. Okay, so please complete this step and I will explain you what to do next. Okay, so I have completed the previous steps. They were very tedious steps, but they were necessary steps in order to have a proper robot simulation. And now in this step, we're going to move the actual robot, at least the first joint, okay? And well, before I forget to mention, remember that the joints 1, 2, 3, and 4 are joints corresponding to the servos, and servos by default, they will be in the position 90 degrees. And the current position you can see here corresponds actually to this 90 degrees. So I have already set these 90 degrees here for joints 1, 2, 3, and 4. This is not necessary for the rest of the joints, but these have to be in the 90 degree position. So please don't forget to set this value before you proceed. Okay, so now what I want you to create is the actual hierarchy of the robot. That will actually allow us to move the robot properly. So we will start by considering that the base dynamic object, or well, in this case is a static object, will be the base object of everything. And we just simply need to drag the non-pure shape base with all the elements. And then we have to make child the joint 1. Has to be child of base dynamic, okay? And joint 1 will be in charge of moving the dynamic link 1 or link 1 dynamic object here. So it will be child of joint 1, okay? And once we have this here, also every non-pure shape object will be child of its corresponding dynamic object. So that object now, if we move joint 1, then this shape will move, and you can see easily. If we move right now this to 0, this will rotate. If we move this to 90, this will rotate again to the home position. Okay. So now what you have, or what I suggest you to do, is to drag just simply all the elements, just temporary at least, but all the elements to inside the link 1 dynamic object. So they are child of this object here. I'll let you to do that. Okay. So whenever you move the joint 1, all the robot will move at least. Okay. That's just simply to apparently be working, but it's not, still there's a lot of steps to complete. Okay. So another thing to do is to create a script, a non-threaded script that will be associated to the robot base, which is base dynamic. There is. And the idea with this script is that we're going to generate or to create user function interface in order to move the servos manually with a slider. Okay, and I have prepared a code containing what we need at least for this step. Basically, what I'm doing is just simply getting the object handle joint 1. This is the variable joint 1 here, and I'm setting the position of the joint to be at 90 degrees. This with this set joint target position. This instruction here requires the value in radians, so that's why I convert the number 90 into radians using this structure here. Okay, and also remember that because the joints are in torque force mode and position control mode, then we can use this set joint target position in order to set the reference point, the set point of where we want to move the servo. And that's a reference point, which means that internally there's a dynamics and with the PID and everything that will move the actual servo to the current, to the target position. Okay, so there will be a slight difference between the concept of servo position or joint position and joint reference. There's a different concept. Okay, then what we are doing here is to create a user interface. Basically, we have a couple of labels, or 3 labels actually, with the joint one. But the important thing is that we have a slider that it's the values, the extreme values of, or the end values of the slider are minus 90 degrees and 90 degrees. And every time we move or we change the position of the slider, we will call the onQ1 change function, which is that one here. And by default, the slider position will be at 0, okay, which corresponds to the actual 90 degrees converted to radians, and will be this variable Q1 ref will be updated whenever we change the slider position. And in the end will vary between 0, because minus 90 plus 90 will be 0, to 180 degrees, which is the range of the servo. And then once we change this, every time in the syscall actuation function, we will just simply update the target position for the joint one using the variable Q1 ref. Okay, so I copy this code here into here, and then let's see how it works. Okay, now it will partially work because I haven't put all the elements inside the link dynamic element, but you will see how it works. That's it. It's slightly slow, but yeah, let me see. That's probably because, let me see, motor properties is not enabled. That's it. Let me make sure it's not enabled. There it is. Now will be much faster. That's it. That's the actual expected behavior. Yeah. Okay. So please follow the instructions and put all the elements inside this link one dynamic. Thank you. Okay, so now the idea is to move the second servo of the robot, this servo here, with the joint 2 axis will be actually that one there. Okay, and the idea is to move or to have a proper simulation for this closed loop structure that you can see here. Okay, as you know, CoppeliaSim only it's through this hierarchy relation, it's only able to simulate, in this case, open kinematic chains. But here we have a closed chain. So in order to implement this closed chain in CoppeliaSim, we need to use a dummy, which is an object that will be in charge of imposing a constraint between the elements, and then the chain will be closed. Okay, and that's actually what we are going to explain right now. Okay, so the idea is the following one. Okay, so we have this closed chain here, but we can see it as 2 open chains, one from this side and the other one from this side in opposite direction. Okay, so how to proceed is very simple. We have to follow just the change. So let's say link 2 needs, join 2 needs to move this link 2 dynamic object, and this link 2 will be actually child of the dynamic one. And then we have a link here. Is that one? Yes. So this link will be child of the dynamic object. And then we have the triangle the dynamic object of the triangle, which will be child of the joint 5. Okay, exactly. And then we have another joint here, will be 6. Okay, and then and you need to move the triangle also here. Yeah, and then you have the joint 6. And in theory, if we continue with the chain, we could in the end complete the chain, but it will be an open chain. So now what we are going to do is to implement the chain in the other way around. So from link 1, what we have is a joint here. Let me see that one, joint 7. So from link 1, we have joint 7, and then we have this link here, which is actually that one. Yeah. So that will be child of joint 7, and also this will be child of that one. Yeah. Okay, so what I mean is that we have one open chain here, one kinematic chain here, and then we have the reverse change from this side, and we have to join them together in this point. So we will create a dummy. Let's call it link 1, for instance. And then let's call it target. And the idea is that we need to move these dummies. They need to be moved to this position there. So they will be there. One of them will be there, and the other one will be also in the same position. So now we have 2 dummies here. Okay, and let me just simply change the size of the dummy. So we have a reduced size, and let's move it to the other, to the bottom layer. So we have a reduced size, and let's move it to the bottom layer. Okay, so we have the 2 dummies, and now how to implement this will be, okay, one of the dummies will be child of the joint 6. So the joint 6, remember, was the one that was dragged by the triangle, and now we have a dummy here. And now the other one will be child of beam 4, that one. Okay, so we need to set a link between these 2 dummies by double clicking here and selecting the other dummy. So now they are linked. Okay, and now we have to select the link type, and in this case we're going to select the dynamics overlap constraint that will make that the following behavior, or it will behave as we have a chain from here, and then we have this joint here, and then this link here will be directly connected here. So this joint will be actually moving as well this element here, and then we'll move this element here that will be attached together with this original link 1 dynamic object. Okay, so it's setting a constraint here, and as you can see, it's quite easy to understand that this joint here, remember, that was in torque force mode, but the dummy is not actually any object which is static or dynamic. It has no dynamic or static properties. This joint here, due to the dummy, is actually moving, as I said, this bar here too. So it's creating the constraint. Okay, so that's the way we can see that. Okay, so now if we just simply create another function for YouTube, we create another, we get the handle for joint 2. We set the reference initial value to 90, exactly the same, and we copy paste and change the numbers, and also these 2 I'm going to paste them and modify the name with this and this. So this one will be pointing there, and that one will be pointing there. Okay, and now also here. Okay, that's it. Okay, so I have created another slider for the second joint. So now, if we move this, as you can see, it's moving properly, this closed kinematic chain that we have configured, okay? And obviously, it's still working the first one, okay? That's not affecting at all, okay? So that's it. Okay, so now we have, or we want to do exactly the same thing, but for this 4-bar mechanism we have here as well, okay? Corresponding to the link 3, sorry, to the join 3. So what we have is, again, we have the join 3, that one, and then we have an open, or we will implement one chain in that direction until this point, and another chain in that direction until this point. So let me just first complete the first part of the chain. Join 3 will be actually moving this servo crank, yeah, that one, servo 3 crank element. So that will be child of join 3. Where is it? Here it is. And also the corresponding non-pure object also will be moved. And then we have an axis here, a joint. There will be a joint, that one, that will be child of the crank. That's it. And then we have this, which is beam 3, so that one will be a child of joint 15. Yeah, that's it. And then we have another axis here, that one, so that will be child of this one. And the beam 3 will be child of the dynamic object. That's it. Okay. And now, just to summarize, we have the link 1, which will be, or it has a child which is joint 3 that has the crank, and then it has this beam here, and then it finishes here with this joint. This joint actually will be moving this part here, but it will be done in a separate chain, okay? So what we have to do is to start from, again, from link 1, and in order to get to this point here, we need to start start with the join 2, dynamic link 2, exactly, and this will be moving, and then we have an axis here. Let me see, which is that one. That will be child of link 2 dynamic. So whenever the link 2 moves, this joint will be moving again, okay? And then this will drag this dynamic link 3 dynamic object. So, and also the that one. Yeah, that's it. So now we have all the elements. Now I need to create the dummies. Okay, let me just simply create the dummies from the ones I have already. So we keep the properties and the size properties and everything. Let's call it link 3. Let's call it link 2 3. Target and yeah, that's it. So now we need to place or to position these dummies in the correct place. So they need to be in this position there. That's it. So we move them there, one and the other one to exactly the same position. And now we just simply create, we move the dummy there, and we move this dummy to the link 3 dynamic object, that one. Okay, and now we have to create the link between the dummies. So this will be linked with the link 2 3 tip with the dynamics overlap constraint. That's it. Okay, so now just to recap, we have link 1, we have join 3, the servo crank, join 15, the beam 3, join 13 that will be linked to with these dummies to link 3 dynamic, and then we have backwards, we have join 12, link 2 dynamic, join 2, and then back again to link 1. So we are closing the chain. Okay, that's correct. Okay, so now we need to include another part of the code in order to control the third servo. So we simply copy paste what we have here. Join 3 will be join 3. This variable will be called q3ref, and that will be 3 and 3, and these two lines will be copied and modified. Sorry, this will be a 3 and that will be a 3. Okay, so that it will point to this function here. And finally, we just simply copy this and change the names. Okay, that's it. So now, if we play, sorry, that's because probably this is because join 3 is not actuated. Join 3, for whatever reason, I did not enable that. Yeah, that's it. That's fine. Okay, so we have the first one, the second one, that's correct. Okay, let me show it to you. Yeah, and the third one. It's working fine. Okay, thank you very much. Okay, so now in this step we're going to close the parallelogram change that we have in this robot in order to properly move the gripper base. So we have actually two chains. One related with this chain here, as you can see, and another one related with this chain here. So we're going to implement actually two different chains. So let's start with that one. Okay, so indeed that one will be link 3 exactly. So this will actually have, this is link 2, yeah. So now we are going to have remember I mentioned that we have another joint here in order to move this link here. So we have the joint 8, that's it. That will be moved correspondingly with the link 2 dynamic object. And then this bottom, right bottom part will be actually moved by the joint 8. So as long as joint 8 it moves, we'll move that one too. So this will be child of the dynamic object. And then we have here another link. So let's try to find it, 11. So this will be moved by this joint there, and then we have the servo base, which is that one. Yeah, that's an important one because a lot of objects will depend on it too. So the joint 11, that's it. Okay, so now we have the gripper base, and this is one of the directions of the chain, and the other direction of the chain is that one. So it's from link 2 will be close here. Okay, so we actually have link 3 there, so we only need to add a joint. There should be a joint, that one. There should be a joint that needs to be added to, not here, sorry, not the beam 3, the link dynamic 3, that one. That's it. So and now we need to create a dummy. Let's call it whatever. Okay, and target. Okay, and the position for these joints will be indeed that one. Sorry, these joints, these dummies. The position for these dummies will be that one and that one will be exactly, sorry, that one will be exactly in the same position. So now they need to be linked with the constraint, dynamics overlap constraint, yes. And then this one will be part of the joint 14, yeah. And the other one will be part of the gripper base, which is gripper base, that one. That's it. Okay, this is one of the chains, and the other one will be this chain here. So we will have, we have this chain here and this chain here that will be close there, for instance. Okay, so what we have is from the triangle, yes, we need to find this axis here. That one, joint 10. So we have from the triangle, we have joint 10, and then we have to find also another axis. Sorry, it was already here. Yeah, the 8th one. Yeah, exactly. So we have joint 10. Let me see where it is. There it is. And needs to move the right top dynamic object. That's it. And then that one will move again another joint, that one, yeah, the 9, joint 9. That's it. That will be connected to the gripper base. From here to here, yeah, exactly, there and there. Okay, so now we need dummies, one for, let's call it link right up, and let's call it this way, and let's link them together with the dynamics overlap constraint. Okay, so this one, for instance, will be moved to here, for instance, yes, and the other one will be moved to joint 9. That's it. Okay. Let me just simply recap. Okay, yeah, let me just simply rename this. I prefer to have link 3. It's just a name. Okay. So, okay, so now if we run the simulation, we will see that now, sorry, it's because it's just the gripper base. We forgot to put it inside the gripper base. That's it. The rest of things are gripper servo crack. Yeah, it was just simply, that's it. And as you can see right now, it's moving properly, and the gripper base is horizontal, and actually you can see it here. It's also working fine. Okay, so now in this last step, the idea is to generate, configure the simulation to properly open and close the gripper. So what we have is, it's again the same, it's a closed chain. Whenever we move the servo crank or the servo gripper crank, we need to drag this left finger, and due to the gears, there's a dependency relation between a joint here and a joint here. So whenever this joint rotates, this one has to rotate in the opposite direction. So whenever the left finger will move to this position here, the right finger will move on the other way. Okay, so in order to do that, it's again the same. So we have joint 4 is the actual joint we are interested in, and this has to be part of or child of the gripper base dynamic. Okay, and then we have one chain which will be that one up to here to the end of the coupler, and then we have another chain which will be the finger itself. Okay, and then we are going to link them together again with the constraints. So this thing here will move the servo crank, the dynamic object. And this has to be child of the dynamic one. Okay, that's it. And then we have an axis, that one will be child of, of the gripper servo crank. And then we have the coupler. That's it. And then we have the final joint, that one. And also the non-pure shape of the coupler. That's it. And then we have joint 17 that will be child of the gripper base. That will be here, and then we will have also the left finger dynamic object will be child of this joint. Okay, and then we just simply need the dummies to connect all together. Let's copy this and let's rename it like left or finger left. And let's copy this again and let's put here tip. And we have to position them to the correct position, should be that one. So we move them there, one, then we move the other one, that's it. And then we just simply to link them together, finger target, that's it, with the dynamics overlap constraint. And then we just simply move one of them to the end of the joint and the other one to the finger. So it has to be moved to finger left in up, and also I need to move this shape here. Finger left, where's finger left? Here is. Okay, and they are linked together. Okay, and now in order to implement this, how to implement the gear for the fingers, we have this joint here. This has to be, right now, is a joint that is in torque force mode, but we have to put it in dependent mode. And we have to enable the hybrid operation because it's dragging, or it's going to drag, actually, let's put it here, it's going to drag a dynamic object. So that's why the joint needs to be in hybrid operation. So once we have the dependent mode, we can select here the joint we were trying to replicate was number, I think that one, yeah, 17. Okay, which means that this joint here will be number 17 and -1. Okay, let's try. Maybe it's the opposite direction, but it's okay. So, and now also this joint needs to be moved to the servo base. So the gripper base, which is that one. Okay, and with that, we only need to update our code in order to implement a function with a button to open and close the gripper. So I have already prepared some code in which just simply there's a variable which is called gripper open that will set the position to 90, or gripper, when it's false, it will set the position to 60 degrees, will be the actual open position, and then it will set, okay, it's open, but if it's open, then we'll set to the closed position, and then we say, okay, it's closed. Okay, so we have to copy this function here somewhere else, let's say here, and also this part here is just simply to create a button called the onGripper function. So this will be the last line. Oops, sorry. That one. Okay, and then this needs joined for, which means that we need the handle. And by default, let's say we want to be closed, so we just simply set the position to 90 degrees, which it's closed position, it's the actual position right now. Okay, and if it's everything it's okay, let me just check, make sure the joint for is enabled. Yeah, so if everything's fine, it's opening, closing the gripper, moving the parts properly. Okay, and that's it. Okay, thank you very much. Hello, in this video we're going to explain how to generate trajectories for controlling the joints of a robot arm in CoppeliaSim VREP. The aims of the presentation are, on the one hand, to explain how to configure joints of a robot arm to perform the precision control, and also to set the joint limits, among other parameters. The main goal is to explain how to generate a polynomial trajectory for robot joints with time specifications, and also to control them by means of evaluating the reference trajectory point at every time instant. On the other hand, CoppeliaSim implements joint control through the RLL library, Reflexes Motion Library, that allows you to easily specify a target configuration, controlling aspects such as the speed and maximum acceleration. We will learn how to use the API for a specific function of this library to generate trajectories with a trapezoidal velocity profile. The robot arm we're going to use is the MiArm robot. In the video description, I have included a link with a file to download that will be used in this video. This robot has 3 motorized joints with ranges as indicated here. In the home configuration, all joints are positioned at 90 degrees. So, the first thing you must do is to properly set the joints. By default, joints are in torque force mode, which is the mode that we are going to use in this video. However, in order to control them, we must set their dynamic properties and enable the joint motor, and also enable the position control loop through a PID. In the figure on the left, I have highlighted 3 joints, or the 3 joints on which we must set the configuration, in particular joint 1, joint 2, and joint 3. The remainder of joints, please leave them exactly as they are. In the figure in the middle, I have set the minimum position for the specific joint and also the range, while in the figure on the right, I have set the PID parameters. I have tuned these parameters to have a small integral and derivative action. That will make easier for tracking the reference with a zero position error. In order to show the time plot of the position of the joints, we need to add a graph to our scene as shown. In this case, we must add 3 data streams to visualize the position of the first 3 joints. Make sure that you have activated the checkbox to show the time plots. And also you have set a proper buffer size, as well as the corresponding or the desired color you want for a specific curve for each of the joints. You can also create a second graph, in this case to show the joint velocities by adding in the data stream not the joint position but the joint velocity. A polynomial trajectory is defined by a set of parameters. In this case, we are interested in generating cubic trajectories because they provide a smooth velocity profile. They can be defined with just 4 parameters and they can be easily computed with some boundary conditions. Such as, for instance, the initial and target configuration and also the initial and target velocity, which in this case I set to 0. These parameters will be different for each joint and must be recalculated every time we want to reach a new configuration. In the formulas, Q0 is the initial configuration and Qt is the target configuration, while T is the overall time of the trajectory. In order to implement these trajectories, we first need to create a script associated to the robot base. On this occasion, we will use a threaded script, since the RML library we are about to use needs to be executed in this type of scripts. So please define the function compute cubic trajectory in order to compute the parameters of cubic trajectories. The input arguments provided to this function are the initial and target configurations as well as the overall time of the trajectory, t. Robot configuration are vectors with the values of the 3 motorized joint positions. The function must return 4 vectors with the trajectory parameters for each joint. Now you must also implement a function named here eval cubic trajectory. This function accepts the trajectory parameters vectors we created before, as well as the time in the variable t, and provides as an output argument the position of the joints in the vector variable qtray. Please fill the elements of the qtray variable with the cubic expression as indicated. Now you're ready to implement the moveupsj function provided here, intended to perform the joint control. This function emulates the well-known instruction under the same name in the rapid language used in ABB industrial robots. Your goal is to complete the missing code in this function as well as the missing code in the compute cubic trajectory and eval cubic trajectory functions. If you are interested in implementing this code in a non-threaded script, then the evaluation of the trajectory as well as setting the joint target position should be done within the syscall actuation function. In that case, we are responsible to be in charge of providing the correct time value, which must be 0 every time we are evaluating a new trajectory. On the other hand, many industrial robots implement a trapezoidal velocity profile. In this case, the maximum velocity as well as the maximum accelerations need to be provided for each joint. Therefore, we can implement a trajectory as shown, where the overall time for the trajectory will depend on the difference between the target and the initial configurations and obviously the maximum velocity and acceleration. This trapezoidal velocity profile is usually smoothed with an S-shaped profile, where the jerk of the trajectory is non-infinite. But the RML library we are about to use does not allow to use these S-shaped trajectories, at least for now. So, to replicate this behavior in CoppeliaSim, we need to use the RML move to joint positions function that allows to move the robot joints from the current configuration to a target configuration. The first input argument of the function is a vector with joint handles to be moved. The second argument is just a flag that by default we will leave to -1 to indicate that all joints movements are coordinated and synchronized. The next 2 arguments are 2 vectors with the initial velocities and accelerations of the joints, while the next 3 arguments are the maximum values for the velocities, the accelerations and the jerks of each joint. As I said, the jerk is the derivative of the acceleration, and limiting the jet will provide the S-shaped trajectory, which is smoother than the trapezoidal trajectory. However, as I said, CoppeliaSim doesn't support this because it's using the version 2 of the RML library. So for X vectors, we just simply need to provide a large value. The last two arguments of the function are actually the target position and the target velocity we want. Usually we will create motions with a zero initial and target velocities, but it is also possible to create, in this case, join the paths with non-zero velocities. The RML move to join position function is a blocking function, which means that the next instruction will not be executed until the movement has been completed. This implies that the code must be necessarily be implemented in a threaded script, as I said before. The function returns the reach position, as well as the current joint velocities and accelerations that can be used or passed as input arguments the next time we use the same instruction. So now you are in the position to implement the moveUpCA function to control the joints with time specifications, as I explained before, and also you can implement or use the RML move to join positions to reproduce the demo that I'm showing here. Please observe. Right now it's generating the set of instructions with the moveUpCA function, because as you can see the trajectory profile of the velocity is quadratic, but now it's actually generating the same it's trying to reach the same target configurations, but in this case using the function provided by the RML library. Please take a look to the trajectory profile of the velocities to see the difference. In this video, I have explained how to generate cubic trajectories for controlling the joints of a robot, as well as how to use the RML library to control these joints. Thanks a lot.
Hello. In this video, I will explain how to control the me-arm robot using CoppeliaSim with coordinated axis movement with an underlying cubic trajectory over the time. Okay, let me first explain or briefly explain what we have here. We have the me-arm robot with which is or has been configured in a kinematic mode, in which all joints here are purely kinematics, and all the links you can see here, they have no dynamics at all. Okay, just for simplicity. Okay, and then we have three joints to control, which are the first joint, it's a vertical joint. The second joint is this robot arm here, and then the third joint will move actually this bar here. Okay. We also have a graph in which I'm depicting the trace that the robot will do at the end effector here, the end effector trajectory. I'm just simply tracking a gripper object, which is an object that has been placed here just on the tip of the robot with its X, Y, and Z coordinate, as well as the, in this case, the joint angles Q1, Q2, and Q3 corresponding to the first three joints, as I said. The X, Y, Z coordinates actually are being displayed here as a 3D curve. The other ones will be displayed as a temporal or time plot actually. Okay. Let me just explain what we have in the code and what do you need to do. Okay. Well, let me just first move here to the syscall init function. I'm defining four configurations. The first one is the configuration where the robot is, Q0, and then I'm defining three more configurations with different angles for each of the joints. Okay. Then I get the handles of each of the joints and set the joints to the initial configuration position. Okay. Then I compute a function which I called compute trajectory, in which I just provide the initial configuration as a separate argument, and then a list of configurations that I would like to reach, and the time intervals that I need for each of these these trajectories I want to generate. Okay, that will produce a variable or a list with all trajectory configurations that I need to follow in order to perform this sequence that I want here. Okay, this, or the number of points in this trajectory, it's stored here in this variable here, and then I have here just a counter that I initialize to 1, so that in the syscall actuation, I just simply set the joint position as long as I have points in that trajectory I have computed, so that I do the for loop for each of the joints from 1 to 3, okay, and it's equal actually to the dimensions of Q0, which is 3. So I do this for loop here for each of the joints, and once I set the joints, then I increase the counter, okay, and then I move to the next simulation step, and then I will move to the next trajectory point. Okay, so let's see what we have here, or what I have implemented in compute trajectory. Okay, this compute trajectory function is actually calling another function that I call move fj, which is actually trying to emulate the rapid instruction for ABB robots that accepts an initial configuration, a final configuration, and a time that I want to generate or the trajectory from that initial configuration and the final configuration. Okay, that will generate or produce a set of points in the joint space, in the configuration space, that I will merge here. So with the sequence of all configurations that I want to reach, I will merge them all so that I follow that trajectory. Okay, this is just an auxiliary function to actually merge all trajectories, but the important one is the move fj function. Okay, this function here, it's computing. First thing it does is computing a number of points that I need for that specific trajectory, and that depends on the time interval that I want to spend to generate that trajectory, divided by the simulation time step. Okay, that gives me the amount of points that I want to generate from Q0 to Qt, that trajectory. Okay, then I compute a cubic trajectory, the parameters of a cubic trajectory. This is explained actually in a document which is included in the description of the video, that I explain how to compute these cubic trajectory parameters. Okay, but that will return 4 parameters, so that I then later can evaluate those parameters for a given time. And that's what I'm doing here in this for loop. I'm just simply iterating from 1 to n, so that I start with time 0, and then I evaluate all trajectory points I want and generate those trajectories here and store them here in QTrack. Okay, and then increase the time with delta t. Okay, so these get cubic trajectory params and eval trajectory params are 2 functions that I have here. As I said, I need 4 parameters per each of the joints, so that I have an initial value, whatever it is, a final value and the initial value, and then I have some maths which are very simple, that this cubic trajectory ensures that it starts exactly where I want, in the initial value, it finishes at the initial value, and the velocity of that trajectory at the initial and final time are equal to 0. Okay, as a result, I have these 4 parameters here that I return, and I use those parameters here in the eval trajectory, and here's where you can see the cubic actually. I have a times, in this case, t to the power 3, b times t to the power of 2, then c times t, and then I have d. Okay, that defines the actual cubic trajectory that will be evaluated for a given time. Okay, well, let's see how it works, this simulation. Here I have the actual time plot of the trajectory. So, and as you can see here, this is what I referred to as a cubic trajectory. Okay, up to 5 seconds. Then I move during 15 seconds from 5 to 20 with another trajectory, and then again 10 more seconds with another trajectory. Okay? And you can see here that the trajectory is not a straight line because I'm moving in the configuration space. Okay? For generating linear trajectories, we have a specific video for that. Thank you very much. Hello. In this video, I'm about to explain how to generate a point-to-point movement so that I can specify the points where I want to go in the Cartesian space, but the underlying trajectory is still a cubic trajectory, as we saw in a previous video. And this movement here is still being done in the configuration space. We will see that. Okay. But for that we need some to compute the inverse kinematics of the robot in order to translate a point in the Cartesian space into the configuration space. Okay, so there's a document included in the video description in which I provide all the maths behind the inverse kinematics. So please, I suggest you to take a look to that document to fully understand this video. Okay, well, let's start by analyzing what we have in this code that I have prepared here. Let's start with the syscall init function. In this case, I have access to the handles of the joints that the robot has, and I get the position of some specific points in order to compute actually the length of or the distance of some parameters that I need for the inverse kinematics or the geometry of my robot. This could be done by hand. You can just simply introduce the numbers here if you know the dimensions, but I prefer to do that so that it's supposed to be more exact. But this, I mean, don't really pay too much attention to that. It's not that important if you put the correct number in the end here. Okay. Well, right now here what I want to do is from my initial configuration I would like to go to different points. In this case is point 1, point 2, point 3, and point 4 actually is the point of my initial configuration. Okay. And as I did before, I get the joint handles in order to control them, and I set the joints positions to the initial configuration, which is Q0. It's exactly the same as we had before. And the difference here is that I call compute trajectory point. Okay. The difference here is that I require an initial configuration, then I have a sequence of points that I would like to go with a sequence of time intervals that I would like to spend on each of the trajectories. Okay. And I need to provide the parameters, the geometric parameters of the robot in order to compute the inverse kinematic, as we will see. But in the end, we generate again a trajectory which has a set of trajectory points, and again we have the same code we had here before in the syscall actuation, because I'm just simply moving the robot to specific joint positions depending on the trajectories that I have computed here. Okay, so let's move to the compute trajectory point function. Here is this one here. It's just simply, this function here is actually calling the moveJ function. Okay, this function is in charge of reproducing or emulating the moveJ instruction in Rapid that we use in ABB robots, that requires in this case initial configuration, a final or destiny position in Cartesian space, the time we want to spend on that or to generate for that trajectory, and the kinematic parameters. Okay, we will see this function here. This compute trajectory point is just simply merging all the trajectories that I generate with the moveJ instruction. Okay. The only thing I need to explain here is that for the next trajectory I would like to merge, because this is a sequence of trajectories, the last point I reach, which is pi minus 1, I use the inverse kinematics in order to compute the initial configuration I want for, or I need for the moveJ function. Okay. we will explain actually the inverse kinematics and the moveJ function right now, okay? So the moveJ function is very simple because it accepts, as I said, an initial configuration, a final Cartesian point, and a time. So what I do here is I use the inverse kinematic to translate the final Cartesian point into a final configuration. So these are the angles that I want at the end of the movement to reach that specific point, okay? And then I call the move upsj function that I explained in the previous video, okay? This function was already explained there, and it's exactly the same. That will return a cubic trajectory between q0 and qt in the configuration space, okay? That's the task for moveJ, and then anyway we need to explain the inverse kinematic. The inverse kinematic is based on some math or trigonometric relations that I'm not about to explain in detail here. I just simply would like you to take a look to the document, as I said, that is included in the video description, and the purpose of this function here is to compute the angles of the first joint, the second joint, and the third joint given a specific position, which x, y, and z coordinates, okay? And all the math behind here are just simply trigonometric relations for this specific robot in order to compute that relation, that inverse kinematic relation, okay? Okay, so let's try to run this example and see how it works. Well, as you can see here, we are moving to specific points. So the input is a point in the Cartesian space, but still the trajectory is not linear because we are moving, or the actual movement is performed in the configuration space using the move upsj function, remember, okay? So we just simply need to compute the inverse kinematic and then compute the actual trajectory in the configuration space, as you can see here, okay? So again, I have a time plot here with all the values for each of the joints that these trajectories have generated. Okay, thank you very much. Hello, in this video I'm going to explain how to generate a linear Cartesian movement. The end effector describes a linear movement to reach from one point to another point, okay? The trajectory behind that linear movement is still a cubic trajectory in terms of the displacement of how much we progress over this linear trajectory, okay? I will give details about that, okay? In the video description you have a document with all the maths that are behind this particular code, because we need to compute the inverse kinematics that we explained in a previous video, but also we need to compute the forward kinematics, okay? So following the ideas of the previous videos, we have already described some of the functions that we need for this particular example, so I'm not going to explain them, okay? But I will explain the new ones. So let's take a look to the code and let's move to the syscall init function, okay? Here at the beginning, this part here hasn't changed too much. Remember that we are here just simply getting the handles of some specific joints so we can compute the geometric relations here, distances between joints and some geometric parameters of this robot. But we could do that by hand, okay, if we know the displacements, okay? I just simply prefer to do it like that, so it's supposed to be more exact. Here the difference is that I will provide 4 points. In this case, these 3 points I indicated with a given numbers in the Cartesian space I would like to reach, and the last one I would like to return to the original position, which is q0. It's actually this q0 here, it's the same as before, but now I use the forward kinematic function that will give me the actual position of the end effector for a given configuration. Okay, we will explain this function later, okay? But anyway, here the difference is that now I compute, or I call the compute trajectory line function. It accepts initial configuration it accepts a sequence of points I would like to move, and again the time intervals that I want to spend on each of these trajectories, as well as the kinematic parameters of this robot, the geometry basically. Okay, and again I have a number of points, and then I execute or evaluate these trajectories I generate here, just here in the syscall actuation function, by setting the joints to the corresponding position. Okay, so let's take a look to the compute trajectory line function, which is somewhere here. Yep. And this function, it's merging, or it's joining a set of trajectories that I use, in this case, the move L instruction. Okay, this instruction, it's reproducing or emulating the rapid instruction that we use for ABB robots, that requires initial, in this case, configuration where the robot is, and requires a final point I would like to reach. But the difference with respect to the move J instruction is that the displacement in the Cartesian space of the end effector will be totally linear. Okay, we will see that. Okay, as before, we need to use the inverse kinematic here, so that for the next movements we know the last configuration we had from the previous point of that trajectory. So that's why we use this inverse kinematic inside here. Okay, so let's take a look to the move L instruction. Sorry. This move L instruction, it's, as I said before, accepting initial configuration, a final point, and a time to spend or to generate that trajectory. It's using the forward kinematics in order to compute from Q0, compute the initial point in the Cartesian space. So this is actually a point in the Cartesian space. And the difference compared to what we have before in the move J instruction is that now the cubic trajectory, it's done in the Cartesian space, so that I generate a cubic trajectory to move from P0 to PT. And that gives me a set of parameters for that specific trajectory in the Cartesian space. And that's what I'm doing here later, is just simply evaluating this trajectory. So for every time instant I want, I have a point in the Cartesian space. Okay, so it's exactly the same function. Actually, it doesn't matter if we evaluate a cubic trajectory in the configuration space or the Cartesian space. It's still a cubic trajectory on that specific space. Okay, so here, as I said, I have a set of points in the Cartesian space that I translate into the configuration space, which is the actual thing that we need for a robot, using the inverse kinematics. So every point in that trajectory we are using, for every point in the trajectory we are using the inverse kinematic function, so we know the actual angles that we want. Okay, so this forward kinematic function, the rest of the functions are exactly as we have seen before, but this forward kinematic function here is just simply computing the required math, so that for a given configuration I know how, or the position of X, Y, and Z of the end effector, the tip of the gripper, and these maths are being explained in the document that I include in the video description. Okay, so once we have seen everything here, let me just simply run the simulation and see how it works. Okay, as you can see, the trajectory is completely linear in the Cartesian space, but because we're using the inverse kinematic, then the joint, or the configuration space here, the trajectory of the joints, they don't have to be linear. Okay, and actually if you take a look here, it starts slowly, here moves faster, and then here decelerates a little bit due to this cubic trajectory during the displacement of the linear trajectory. Okay, I hope you could see it properly. Okay, thank you very much. Hello, in this video I'm going to explain how to generate a circular movement in the Cartesian space using the MIARM robot and CoppeliaSim. And for this we are following or we are based in the videos that we have seen before in order to describe coordinate axis movement, point-to-point movement and also linear movement. But now we are interested in reproducing the move-C instruction that we have in Rapid for ABB robots. For that instruction, we need 3 points at least in order to generate a circle or an arc segment actually. The first point is the actual robot position, and then the second point is the intermediate position of that trajectory, and the last point will be the actual end point that we want for that trajectory. Okay? In this example I'm going to explain we have two trajectories. One which is moving in the XY plane here of the global reference frame, is that one here, and then I have another trajectory here moving in the XZ plane of this global frame here, as you can see. But the maths I'm about to explain actually are valid for generating points in the 3D space of the Cartesian space, but with the only condition that at least the circle is not degenerated. Let's say, for instance, that the 3 points are aligned. In that case, the radius will be infinite, and then we cannot compute that circle. Okay, but apart from that, let's say singular cases, the code I'm about to explain will be valid for any circle or arc segment contained in a plane in the Cartesian space. Okay, so first thing I would like to also mention is that we are going to, as I said, generate two trajectories. For each of the trajectories, in order to compute that circle, I will need to compute a transformation matrix or reference frame that will be associated to the first point of each trajectory. In that case, the first trajectory will have a reference point here, a reference frame here, and then the second trajectory, since its initial point is that one, then it will have another reference frame associated to that plane that the points are contained. Okay, so let's take a look to the code we have here. It's quite a lot of code, but you will see that with the maths, all the maths that I have explained in the document that is included in the video description, then you will be able to follow this video. Okay, well, first thing is exactly the same as before. We have some in this case some we're getting the handles of some of the joints in order to get the dimensions of the robot and everything like that. We again set 4 specific positions I would like to go. In that case, these first 2 points together with initial configuration perform the first circle trajectory, and these 3 points here actually are the one that will perform the second circular trajectory. Okay? In that case, I have implemented a compute trajectory circle that I need an initial configuration and then the sequence of points that I would like to generate. But this is taken by pairs, so that this one here, it's taken by pairs with these two, and then the last configuration that will be associated to this position here will be combined with these other two positions here, so that we have these two trajectories as I was mentioned. And here we have the time that I spent on each of these two trajectories. Okay, so let's see how. Yeah, here is wait a moment. Yeah, there it is. Okay, so for this this computes trajectory circle, what I have is I call another function which is called move-C. As I said before, this is emulating the move-C instruction in the Rapid language that requires initial configuration and 2 points, the intermediate point and the final point, and the time I want to spend to generate that trajectory. Okay, as I said, I take that in pairs, so I need 2 points here, and then in order to combine more circular trajectories, then I need to generate or to compute the inverse kinematic using the last or the previous point in order to compute the initial configuration, and then I use the pi and pi plus 1 points in order to generate that sequence of trajectories. Okay, take a look, or just take into consideration that here the for loop increases by 2. Okay, so that's why the I increases by 2. Okay, Well, let's take a look to the move C instruction here. It's somewhere here. Here it is. Okay. Well, this instruction here, basically, it's just computing the actual trajectory that we need to move from our initial configuration to reach the final position that we want. But for that we need an intermediate position. Okay. In that case, what I need to do is first I need to compute the position in Cartesian coordinates of my actual initial configuration. Okay, so that's PT0. And then with these 3 points, I fit a circle in the 3D space. Okay, this is a function that has a math behind. I will explain it, briefly explain it here. Okay, but as I said, it's explained in the document, including the video description, that provides a transformation matrix that it's associated to the first point, so that the other 2 points are contained in the XY plane of this transformation matrix. Okay, because they are contained in the XY plane, then they can be seen as a circle in the 2D dimension, in a 2D dimension, with respect to that transformation frame. Okay, that's the key point here, and that actually is the center of the circle in that relative frame, and the radius, as well as the initial angle and the final angle, in order to go from the initial configuration to the final point in this case. Okay, there are 2 possible solutions, so we discard, we always choose or try to choose the shortest one. Okay, because that's why we, using the PT1, we know one which is the correct solution in this case. Okay. Okay, so let's say, or let's assume that we have the parameters for that circle. Okay, and then the cubic trajectory here, it's being performed in the angular coordinate in which I move or I describe or I sweep this circle here, so that I have a cubic trajectory from the initial angle to the final angle with respect to, as I said, this arc segment. Okay, and that will provide some trajectory parameters that I evaluate here in this for loop. Okay, this will give me the actual angle as time it's moving and passing through, so that on every time I compute, as you can see here, this part here, I just simply compute the equation of a circle in which I have the radius, the cosinus of the angle, and I add the x coordinate in this case, the y coordinate in this case, and the z coordinate is 0 because it's contained, this point here is relative to the transformation frame I was mentioned, and for that reason I use this transformation frame so that I convert this point into the Cartesian space with respect to the wall frame. Okay, that's a point with respect to the wall frame. So once we have the point A with respect to the wall frame, then we can use the inverse kinematics to compute the actual angles of the first 3 joints of the robot, so that we can move from the initial configuration, pass by the intermediate point, and then reach the final point. Okay. Well, let me just briefly explain how this fit circle function works. This function here is basically computing 2 vectors with respect to PT0. So the vector PT1 minus PT0 and PT2 minus PT0, and it's computing in this case x, y and z axis of a reference frame, so that the first axis, the x-axis, points towards PT1. Okay, the second one, it's the cross product between PT01 and PT02, and then the y-axis is just simply the cross product because it's a dexter rotary reference frame, and then once we have the z and the x, we can compute the y. Okay, with that we build a transformation matrix. This is a function. These are some auxiliary functions that I explained just before here, but we built a transformation matrix, and with that we do some math in order to compute. Now the points can be projected over the xy plane of this reference frame, and then we can compute the standard maths for the circle radius and the initial angle and final angle for this circle contained in the 2D plane of the XY reference frame here. Okay. Well, these actually functions I mentioned here, they are just right here, just to compute the vector difference, the norm of a vector, the unitary vector from a generic vector, the cross product, the dot product, or to build a transformation matrix. Okay, and these are some auxiliary functions that I need in order to succeed for this example. Okay, well, let's see how it works. It's hard to appreciate, but at the beginning, since it still is a qubit trajectory, it will start with a slow displacement here, then we'll speed up a little bit and then slow down here. Okay, here this is how it works. Now the speed is increasing and then the speed is decreasing, and then it's moving in the in the XZ plane, as you can see there. Okay, I hope you could see it. Thank you very much. Hello. In this video, I'm going to explain how to work with matrices and vectors in Lua within CoppeliaSim. Lua has several classes to represent matrices and vectors. It has two generic classes, matrix and vector, that will allow us to represent any matrix or vector respectively. In addition to this, it includes specific classes that will be used to represent a rotation matrix or a homogeneous transformation matrix, or the position of a 3D point. The objective of this presentation is to focus on two generic classes, while specific classes for working with 3D geometry will be seen in another video. First, given a Lua table represented here by a set of t values, t1, t2 and so on, we can assign table values in a matrix or vector format as shown here. Therefore, a matrix and a vector are nothing more than a table stored storing numerical data on which we can perform some mathematical operations, so it contains specific methods. Now we will see a set of examples that will help us to understand how to work with these classes. Here specifically we see three examples to create matrices. The first example creates a matrix filled with random numbers. In the second example, we create a matrix filled with a Lua table. And in the third example, we create an identity matrix. If we call the matrix constructor and pass only these two arguments, it will create by default a matrix filled of zeros of the appropriate dimensions. There are other methods that can be used, for instance the method ones, that will obviously fill the matrix with all ones in all its elements. We can multiply two matrices by using the star operator or multiplication operator. We can also add and subtract matrices using just the plus and minus sign, or we could even perform arithmetic operations with a scalar that will affect to all the elements of the matrix. We can individually access the elements of an array using the square bracket operators. If we do not indicate the second coordinate, then it will return the corresponding row of the matrix. So it's the first, if we use the square brackets but only with one coordinate, then it will return a row matrix. Then if we access to an element that is outside the matrix range, then we do, as we do in the second example, then it will return a nil value. You can see here that we are trying to access to element 1, 4, but this is a 2 times 2 matrix, then this is why it returns a nil value. But if we try to access to a row that doesn't exist, then it will return an empty array. Then to set, for instance, also a specific element of a matrix, we can also use the square bracket operators. We can concatenate vertically or horizontally matrices, as you can see. Obviously, the dimensions of the matrices must be consistent, otherwise it will throw an error. We can access to a submatrix using the slice method. In this case, we must pass the coordinates of the first element of the submatrix and the last element of the submatrix. Here in this example, the first coordinate is the element 2, 1, and the last element is the element 2, 3. In the same way, we could assign a submatrix to an existing matrix using, in this case, the assign method. We can also delete rows and columns of matrices using the methods drop col or drop row, or we can assign rows or columns using the methods set row or set col. The transpose of a matrix is obtained using the T method from transpose, while we can calculate the inverse of a square matrix using the Gauss-Jordan method using the inv function. The matrix library does not include the computations for computing the pseudo-inverse of a matrix. However, this is convenient in many robotics applications, since it is rather quite useful to try to invert the Jacobian of a matrix, and this Jacobian is not necessarily a square matrix. Therefore, we can use that the inverse of this matrix should be done with the pseudo-inverse operator. Okay. Then in here, what I have included here is a script that will help us to compute this pseudo-inverse. And also you can see here a simple code to help you how you can use it. Okay. Like matrices, we can also create vectors. They are nothing more than matrices, but in a column form. So we can create them, we can assign them in a very similar way that we did before, because indeed they are matrices. And the majority of the operators and functions that we have previously seen can be applied to vectors too. For example, we can multiply a matrix with a vector because basically it's the same as multiplying two matrices with the appropriate dimensions. There are functions or specific functions for filling a vector with a linear spacing using the linspace method, but also there are other methods to fill the spacing with a logarithmic or geometric spacing. In this presentation, I have introduced the use of matrices and vectors in Lua using CoppeliaSim. Thanks a lot. Hello. In this video, I'm going to explain how to work with homogeneous transformation matrices, rotation matrices, and translation vectors in Lua using CoppeliaSim. Just to recap, Lua has two generic classes to represent matrices and vectors that we have already explained in a previous video. The aim of this video is to specifically talk about matrix 3x3 and matrix 4x4 classes that specifically represent rotation and homogeneous transformation matrices, respectively. On the other hand, we will also talk about vector 3 and vector 4 classes that will allow us to specify a Cartesian or homogeneous position. To learn how to use this type of classes, we are going to see some examples and a simple exercise. Keep in mind that CoppeliaSim API includes functions that allow us to access the position or orientation of an object, its transformation matrix, etc. In addition to this, it also includes a plugin, K, which allows us to compute the inverse kinematics of a robot and to compute its Jacobian. Thus, the logical question is, why do we need the matrix library and the classes associated with transformations, vectors, etc. that I have previously commented. So, first of all, CoppeliaSim API is used for objects that belong to the sim, which forces us to create them and position them in the right place. The matrix calculus of homogeneous transformation is of academic interest, and this is in fact our main motivation. We might be also interested in extending CoppeliaSim's functionality by using the matrix library, as we did, for instance, for the case of the pseudo-inverse function. Here I show a couple of examples to define a rotation matrix with the rotset function, although we could also use rotx or roty functions. Both of them are also defined in the matrix 3x3 class. To define a position from a Lua table, we can use the vector3 class as shown. To create a homogeneous transformation matrix, we can use the class matrix 4x4, in which we can specify the 16 elements of the transformation matrix from a Lua table. Once created, we can access its rotation matrix as shown. The Euler angles that this rotation matrix represents, or its equivalent representation in quaternions, in both cases they return a Lua table with the requested values. We can also access to the position vector and also to the pose, which is just a combination of the position and the orientation expressed in quaternions. In that case also, these two last functions also return a Lua table, as you can see. Here I show another example in which I create a transformation matrix from a rotation matrix and a translation vector using the fromRT function. So to set the pose of a reference frame with respect to another, we can access the elements of the matrix A1 by using the data method. As you can see, we have used these ideas to set the reference frame O1 with respect to O0 in the given code. Here I show another example that actually performs just the opposite. Starting from an existing object in CoppeliaSim, we use the getObjectMatrix function to obtain a table with 12 values corresponding to the first 3 rows of the homogeneous transformation matrix. Then we make a vertical concatenation with a vector containing 3 zeros and a 1 to fill the last row of the transformation matrix. So we can build and create the matrix A1. We can extract information about a given axis of a transformation matrix by using the axis method, which returns a vector with 3 elements with the values of the indicated axis. We can use this vector to perform a rotation around the z-axis with a certain angle by using the fromAxis angle method. Finally, I show here an example in which the inverse of the transformation matrix can be performed. Here we have 2 options, since if we fill the information as if it were a matrix of type matrix 4x4 and then we call the inv method, then it takes into consideration that the inverse of a transformation matrix can be computed with a specific formula as indicated. This is more efficient than computing the inverse using the Gauss-Jordan method, which would be the case if we had computed this inverse by using the generic matrix class. But in any case, both of them return the same result. Well, in the description of the video, I have included a CoppeliaSim file that includes a piece or a part with the dimensions that I show here. The aim of this exercise is to place the reference systems O0, O1, etc. at the indicated positions and orientations. Indeed, all reference frames are by default in the file that I provide at the bottom left corner, just right where O frame is. So we must compute first relative transformations between the reference frames by using the specified parameters A, B, C, D, and E. That is, we must first compute transformations between O1 and O0, O2 and O1, O3 and O2, and so on. To make the exercise easier, I show here the necessary code that you must include in the dummy script. Well, actually it's included in the dummy script to set the position and orientation of reference frame 01 with respect to 00. So your task is now to do the same thing, but with the remainder of reference frames. Once you do that, the expected result is the one as you can see in the figure here on the right. In this presentation, I have introduced the use of homogeneous transformation matrix, rotation matrices using Lua and CoppeliaSim. Thanks a lot. Hello, in this video I will explain how to compute forward kinematics of serial robot manipulators using CoppeliaSim. The aims of the presentation are, on the one hand, to define a set of functions to compute forward kinematics. These functions will help us to make calculations that we typically need in many robot arms, such as, for instance, the robot Jacobian, as we will see in another video. In addition to this, I will explain in this video how to automatically extract Denovid-Hardeman parameters from a serial manipulator and how to automatically set the position and orientation of reference frames associated with each link based on joint positions. I have included in the video description a file that includes a robot with 7 degrees of freedom and 8 reference frames associated with each of the robot links. Reference frames are objects named 00, 01, etc. And they are all positioned at the base of the robot, at the ground level. And they are obviously aligned with the first joint to comply with the Denovid-Hardeman method. We must find out the height of the first joint, that is the set coordinate with respect to the frame 00. We also need to find out the separation distance of the tip of the end effector with respect to the position of the last joint. That's the distance along the z-axis of the last joint. We will see why. CoppeliaSim includes an add-on that allows to extract the Denovid-Hardeman parameters. So once we activate this add-on, we need to select the first joint and then a window will appear displaying information of Denovid-Hardeman parameters related to the transformation of the joints, and this is what I show here in this table, in which I have included all the Denovid-Hardeman parameters that are related with this robot, and in particular parameter L0 and L7 correspond to the height of the first joint and the separation distance of the last joint with respect to the tip. Now we must create a script and associate it with the base of the robot. In the syscall init function, we need to add the following code that will allow us to access joint handles and reference frame handles. This will be stored in the joints variable and also in the O variable. Also, we will create a Lua table with the Denovid-Hardeman parameters that we get in our previous step. This table contains 7 elements, with each of them with another table of 4 elements related with the Denovid-Hardeman parameters of each joint. Then we will create a function with the name dh that accepts the handle of a joint in a Lua table with the 4 Denovid-Hardeman parameters associated with that joint. As you can see, this function first obtains the joint value position using the getJointPosition function, and also the joint type using the getJointType function, which allow us to discriminate between revolute and prismatic joints. Then it computes the Denovid-Hardeman transformation matrix and returns this matrix as an output argument. Now we will implement an auxiliary function that allows us to obtain a Lua table with all the transformation matrices associated with joints. As it can be seen, the function stores in a table AI the transformation matrices that the dh function returns. In each iteration of the loop, joint handle and the corresponding row of the full table of database parameters need to be provided. Finally, we have created another function to set the position of reference frame. To do this, we will set reference frames based on the relative position of specific transformation matrix, and using this data we will set the reference frames using the setObjectMatrix function. Well, in this video I have explained how to compute forward kinematics of serial robot manipulators in CoppeliaSim. Thank you very much. Hello, in this video I will explain how to solve the inverse kinematic problem of serial robot manipulators using CoppeliaSim and specifically the SimIK plugin. In this first video I am going to explain how to configure an inverse kinematic environment from scene objects. In the next video I will explain how to manually create all these elements and to solve the inverse kinematic problem as well, but using advanced functions. The aims of the presentation are to explain how to use the SimIK plugin to solve the inverse kinematic problem. I will explain how to create an environment with all the elements that the plugin needs from scene objects. We will see a couple of algorithms to solve the inverse kinematics and what kind of constraints we can include on it. Finally, we will see how to solve the inverse kinematic problem and how to apply the calculated values to joint positions to actually achieve a pose. To end this presentation, I will show some examples. The SimIK plugin can solve the inverse kinematic of multiple serial robot manipulators. So in this regard, it has its own environment that works independently of CoppeliaSim scene objects. This means that we need to replicate the robot configuration we have in a scene to be able to control a specific robot. And we can also solve the inverse kinematic problem without affecting objects in the scene, but this is something, as I said, we will see in the next video. We can create several environments to be able to have multiple computations running independently. This is like having several open sessions in the plugin where we can perform independent computations. On each of the environments we can create inverse kinematic groups consisting of a set of elements, and these elements must have a hierarchy like a serial robot manipulator. In particular, we need a dummy at the robot base, a set of joints representing the robot and a dummy of the tip of the robot that will be linked to another dummy that represents the target position to be reached. It is therefore important to remark that IK elements of the plugin are different from scene objects of CoppeliaSim. So, in this video, as I said before, I will focus on how to solve the inverse kinematic problem from objects that we have in the scene. So in this case, I have created a dummy at the tip of the robot, another one at the tip of, at the base of the robot, with the hierarchy or the hierarchical relationship as shown in the figure on the left. And in addition to this, we need to create also a target dummy that will be used to determine the position and orientation that we intend to reach. The dummies you can see here are actually based on the previous example that we saw in a previous video about forward kinematics. The base dummy it's named 00, the tip dummy it's named 07, and the target dummy it's named target. This is a new dummy, okay? And all these dummies are actually objects in the CoppeliaSim scene. To work with the CoppeliaSim IK plugin, we need to create a number of objects starting with the IK environment. As I said, it's some kind of internal session that will allow us to configure all the remaining elements that we need to solve the problem. In the code I show here, I have created 3 variables, 2 of them to define the base and the tip of the robot from the reference frame dummies that we have in our scene, and a third variable to define the target dummy. These variables correspond to actual objects, as I said, in CoppeliaSim scene. Next, we create the IK environment using the SimIK create environment function, and store the result in the IKEnv variable that will be used in all plugin function calls, as we will see later. Then we need to add a series of groups to the environment. A group includes calculation parameters that are used to solve the inverse kinematic problem. There are actually two different algorithms implemented in the plugin: the pseudo-inverse of the robot Jacobian or the damped least squares method, or DLS. Both algorithms are iterative algorithms, and specifically the DLS algorithm also needs to provide a damping factor as a parameter to smooth the progression of the algorithm. I have indicated here each of the parameters, what I mean. Well, I have created in particular here two IK groups to solve the problem with both algorithms, and this is, as we will see, just in case one of them fails, we can always try to solve it with the other algorithm. We need to add the elements to each of IK groups, and for that we use the SimIK add AK elements from scene. This is a function that will include all the scene objects from the base to the tip as part of the elements of the AK environment. It also needs the target dummy and what kind of constraint we impose to our problem. In particular here I have used a pose constraint, but we will see that there might be several options to solve the problem, and that will imply some kind of relaxation. So actually here we see three different examples to solve the inverse kinematic problem with different constraint requirements. So the SimIK constraint pose imposes constraints on both position and orientation. In other words, it's a 6-dimensional task in which the plugin must try to find a solution so that the point reaches, or the tip reaches the target, satisfying those 6 variables. We could solve the problem only considering, for instance, position variables. In this case, the task would have a 3-dimensional space, which means that the problem has been somehow relaxed, and thus additional solutions are valid now. We can also require constraints, for instance, on the alpha, beta, or even the gamma angle. As you can see from these 3 examples, the position of the tip and the target, all of them they match, but depending on the additional constraints we impose, the orientation that the tip of the robot reaches, it's different. In particular, for instance, if we impose position, then the orientation doesn't mean any orientation would be a valid solution. And if we impose, for instance, in this case, the alpha beta constraint, that implies that our z-axis must be aligned. Yeah, and this is something, for instance, could be relevant, for instance, for a drilling operation where the orientation of the z-axis is not important, but the direction, it is important. So once we have created all elements in the AK environment, we can solve the inverse kinematic problem by using the SimIK apply AK environment to a scene function. This function allows to directly move the robot if a solution is found. It is well known that finding a feasible solution is not always guaranteed. Imagine the case where we request to reach a position that is outside the robot workspace. Sometimes the pseudo-inverse algorithm finds more difficult to find the solution, but is faster to compute, and for that reason we try to solve first the problem with using this pseudo-inverse approach, and then in case it fails, then we try to solve it with the DLS algorithm. And just in case both fail, then in that case we show a dialog to the user indicating that the inverse kinematic is failing. Well, now let's see some examples to see how the plugin solves the problem. I have prepared actually a set of examples where I have fixed the target dummy to a given position and orientation, and we have generated a smooth trajectory from the tip to the target using an interpolation between the positions and orientations. At each of the trajectory points, we solve the inverse kinematic problem and move the robot to the requested pose. In this first video, we will see how we can successfully solve the problem by moving the robot with a smooth trajectory from the start position to the target position. As you can see, the robot, it's moving and it's reaching exactly the target position that we requested. Now, in the second video, we're going to see how the robot manages to solve the problem at the same pose, but during the interpolated movement, there are poses that the robot cannot reach. You will see how it stretches trying to reach the target with the proper orientation, and then at the end of the trajectory, it does manage to reach the position and orientation again, because the actual pose we are demanding, it's within the workspace of the robot. As you can see, somehow the robot is trying to reach a position, an orientation that it's outside the scope of, or outside the workspace of the robot, and the plugin it's not able to solve it. But then later we can recover the inverse kinematic. And in the third video, we will see how the solution found represents a non-physically possible movement. The reason is because when generating this video, joints were not limited on purpose, and thus the plugin considers joint angles that should not be valid indeed. If we want to avoid these kind of problems, we need to properly set the joint limits using the joint properties. Obviously, this will reduce the set of possible solutions, but at least the ones you find will be feasible solutions. So let's see how it works, or how it fails actually. You can see that the robot is moving and it's flipping this link here, providing an impossible movement. We could solve this by limiting or specifying or proper configuring these values here, the minimum position and the range of the link. Well, in this presentation I have explained how to solve the inverse kinematic of serial robot manipulators using SimIK plugin in CoppeliaSim. Thank you very much. Hello, in this video I will explain how to solve the inverse kinematic problem of serial robot manipulators using SimIK plugin in CoppeliaSim. This video is indeed a continuation of a previous video in which I explained how to solve this problem from scene objects. In this video, I will explain how to manually create all required elements to solve this inverse kinematic problem. This will give us more possibilities to control the kind of solutions we obtained before and actually how we can apply them. The aims of the presentation are on the one hand to continue learning how to use this CoppeliaSim's SimIK plugin. I will remark again the difference between the scene objects and plugin objects. We will see how to use forward kinematics to compute the position of an orientation of a robot tip, and how to prepare all the necessary elements to the IK environment that the plugin needs in order to be able to compute the inverse kinematics. Finally, we will see how to compute trajectories to move from the current configuration to a desired final pose. We're going to distinguish between scene objects and objects belonging to the IK plugin's environment. So the first thing we need to do is to create an IK environment. Then we will create a set of elements, the base, the end effector or tip, and the target dummies. Also, we need to create IK joints. All these objects are created inside the IK environment. The key concept here is that we can do this without duplicating objects that we have in CoppeliaSim scene. In fact, here we only need, the only scene objects we need actually are the links and the joints that actually confront the robot. We have created a target. Here in the figure on the right you see that there's a scene object named target, but this is for convenience, so we can visualize the pose to which the road must converge. The base dummy at the AK environment will be positioned for convenience at the position 0, 0, 0, and the tip dummy will be positioned using the forward kinematics. We will set the position of all AK joints considering actually the same position of the scene object, so we will ask CoppeliaSim about these positions and orientations and create the AK joints properly in the AK environment. Well, the DH function I have included here allows to obtain a homogeneous transformation matrix using the Navier-Hartenberg parameters. This is something that we already saw in a previous video related with the forward kinematics, remember. Here I have just added a function that allows us to obtain the transformation matrix of the end effector by just post-multiplying all the Navier-Hartenberg parameters by calling the DH function. We will use this matrix, which is the AN matrix, to position and to set the position and orientation of the tip of the dummy. A0, it's for convenience, it's just simply an identity matrix representing the position and orientation of the robot base. Actually, we start now preparing all the elements to solve the inverse kinematics. We start by creating the AK environment and the 3 AK dummies, the base, the tip, and the target. We will position the base and the tip according to the transformations A0 and AN as I have already mentioned. And in addition to this, we need to establish a link between the tip and the target so that the plugin can identify which elements are the tip and the target and they must be somehow related. And in this case, we use the SimAK settling dummy function. Well, later we will create a set of joints inside the AK environment. In the code I'm showing here, this code allows us to create and configure the joints from actual robot joints in the scene. So the joints variable is a table with the scene joints handles, while the IK joints variable it's the corresponding table related with the IK joint handles. As you can see, I have created IK joints considering the type of joint, revolute or prismatic, and also considering the limits, its position and orientation and so on. Once we have created all necessary elements, we can establish a hierarchy relationship between them. The base dummy is the parent of all AK elements, and then we can add joints. Each one is child of the previous one. And to complete the hierarchy, the tip must be the child of the last joint. In addition to this, we must create an AK group, as we saw in the previous video. Here, just simply, I'm showing the code for the pseudo-inverse method, and in this case, I have specified a constraint or to constrain the pose. Okay, but remember that there might be different options to select the calculation method algorithm and also which constraints to apply. Now we are finally in a position to solve the inverse kinematic problem. So in the code I'm showing here, the first part of the code actually I manually set a target position and orientation. Actually what I'm setting is the position and orientation of the scene target object, which is this CoppeliaSim scene object, but I do the same or the corresponding thing for the AK target object, which is the same object but in the AK environment. Then the SimAK get config for tpose function allows to solve the inverse kinematic problem. This function returns, in case of finding a solution, a list with the values of the joints. One of the most important parameters to tune is the accuracy of the solution to be found. Internally, the plugin tries multiple configurations until it finds one that satisfies the imposed constraints. In the code, I have set this parameter to 0.1. It should be interpreted as meters, but actually it considers not only meters for precision, but it's a mixture between meters and orientation. So this is an advanced feature that I prefer not to mention. Okay. So you can also set the maximum calculation time, returning the best or the best solution found so far if the time is due. In the code, I have set this time to 0.5 seconds. As you know, the solution of the inverse kinematic is not unique. And in fact, here I'm showing 3 different examples in which the robot is able to reach exactly the same pose. All of them are correct and they were returned by the previous function. And the reason is, as I mentioned before, we try to find a solution and the plugin internally tries to find multiple solutions until decides that has found a correct one. But this is some kind of random procedure. So in this redundant robot, we were able to find multiple solutions to solve the same problem. The plugin also allows to generate trajectories from the current position to the target dummy. In this case, we must use the SimIK generate path function, which requires to specify the AK environment, the AK group, the list with all the AK joints, and also the robot tip. We must also indicate in the last argument the number of trajectory points we want, in this case 100. The returned value is a table with all joint values along the path. We can just simply reorganize this information in a matrix form using the matrix library. And once the trajectory is computed, then we can apply it to each of the trajectory points to the sim joints, and we can do this, for instance, inside the syscall actuation function by just calling the sim set joint position until all point trajectories has been applied. In this video, we will see how this trajectory generator works. As you can see, there's a smooth transition between the initial position and the final configuration or position that we required. Let's see it again. Here it is. Okay. Well, in this presentation, I have explained how to solve the inverse kinematics of serial robot manipulators using the SimIK plugin in CoppeliaSim. Thank you very much. Hello, in this video I'm going to explain how to compute the robot Jacobian matrix using SimIK plugin in CoppeliaSim. This plugin returns information with elements of the Jacobian matrix, but its elements need to be reordered in order to obtain a matrix whose rows are the constraints of the task and columns represent the joints, ordered from the first to the last joint. If you implement the functions that I propose in this video, you will see how the obtained matrix looks as expected, and in the end I hope you save hours of struggling trying to understand what the obtained numbers means, because this part of the software is, to be honest, not well documented, or not documented in detail at least. The aims of the video are to explain how the robot Jacobian matrix can be obtained using the SimIK plugin, and I will explain how we need to reorder, or how we should reorder the elements of the matrix in order to obtain the expected results based on the conventional definition of the Jacobian matrix. In order to get proper calculations, we need also to know the orientation of the end effector, and for that reason I'm going to quickly review how to obtain forward kinematics and also how to set up all the elements that the plugin requires in order to compute the Jacobian. To finish the presentation, I will show some numerical examples of the Jacobian matrix computation for a 7 degrees of freedom robot in 2 specific configurations. We will also see an example in which we will visualize the direction of the instantaneous linear velocity vector at the end effector as a consequence of applying a velocity to the joints. So by now, you know that we will use the SimIK plugin, which was used in our previous presentation to solve the inverse kinematics problem. Therefore, I recommend you to watch the video before continuing with this presentation. Here I'm just going to review which are the steps we need in order to properly configure the plugin and give some quick details about the code. But if you want to find more details, please watch my previous video about the inverse kinematics. Remember that you must create an AK environment, also create a set of dummies for the base, tip and target, as well as a set of AK joints according to the position and orientation of robot joints in the CoppeliaSim scene. Furthermore, we must establish the appropriate hierarchical relationship between all AK elements. And in addition to this, we must configure the AK group with the appropriate parameterization to solve the problem. That is the type of algorithm, number of iterations, and above all, the type of constraints we impose to our problem. Here, I will assume that we solve the full problem, that is the one that establishes 3 position and 3 angle constraints to reach a specific pose. In this code, I create an AK environment, 3 dummies for the base, tip and target, and set the AK joints or create the AK joints. In particular, AK joints take in actual position values of robot joints, and it's important to remark the difference between the variable AK joints and joints. The first one contains handles of AK elements, while the later contains handles of CoppeliaSim scene objects. At the end of this code, I call the function getAn. That returns a transformation matrix of the end effector by computing the forward kinematics. This transformation is used to set the position and orientation of the tip and target. Details about this function will be shown later. Once AK dummies and AK joints have been created, we need to set a proper hierarchical relationship between the AK elements and create an AK group to indicate the type of task we want to solve. A 6-dimensional pose task, let's say. It is important to remark that robot Jacobian will depend actually on the type of constraints we use here. In this particular example, I'm using the SimAK constraint pose, as you can see in the last line of code, in order to obtain the full robot Jacobian matrix. The AKDH function that I include here allows to obtain the homogeneous transformation matrix using the Navier-Harden parameters. This is actually very similar to what we saw in a previous video regarding with the forward kinematics, but in this case I'm using AK joints position values, which means that we can set multiple configurations and compute the Jacobian matrix without actually moving the robot in CoppeliaSim scene. The getAn function allows to obtain the transformation matrix of the end effector with respect to the robot base. Once the plugin is configured and all previous functions implemented, then we can compute the robot Jacobian. First, we call the function SimAK compute Jacobian, and in case of returning a true value, then we call the function SimAK get Jacobian. This second function returns 2 values. The first one is a table with all elements of robot Jacobian, and the second one is another table with the dimension of the Jacobian. Specifically, the number of elements in the Jacobian or in the table regarding with the Jacobian, it's equal to the number of joints multiplied by the number of constraints in X, Y, Z, etc. The order in which these elements are ordered, it is indicated here in the slide. And as you can see, we need to provide the Jacobian matrix form, or we should provide the Jacobian in a matrix form if we want to use it for further computations. Actually, the function getJacob implemented in the code I'm showing here allows to obtain the Jacobian in matrix form. The result is a matrix which has as many columns as robot joints and as many rows as constraints imposed by the task. The first column corresponds to the first of robot joints, while the last column corresponds to the last robot joint. For a pose problem, as the one that we configured before, the first 3 rows correspond to the position constraints, while the last 3 rows correspond to the angle constraints. It is important to mention that the Jacobian matrix returned by CoppeliaSim, it is actually unconventional matrix, to say the least. I have been analyzing the values that it returns, and the conclusion I get is that the position constraints are just as we expect. They are referred actually to with respect to the robot base, but the angle constraints somehow they are referred to the end effector frame. And for that reason, we must perform a rotation of the last 3 rows using the forward kinematics. This transformation is implemented in the lines of this code I'm showing here, just before returning the J variable. Now we're going to check the numerical values obtained for a robot with 7 degrees of freedom at a specific configuration. So in the figure on the left, we can see the robot and the z-axis of the reference frames associated to joint positions. These are the blue arrows that you can see in the figure. At the base of the robot, you can see the x and z-axis of the robot base. The first row of the Jacobi matrix represents the x-axis constraint of the end effector with respect to the robot base. It is indicating that variations of joints of the second joint, fourth joint and sixth joint can generate a linear speed in the x direction. Due to the direction of rotation of the joints, a positive rotation speed would imply a negative linear velocity in the end effector. On the other hand, joints 1, 3 and 5 affect the linear movement in the y direction. And also you can see that the rotation of the joint or the fifth joint implies a rotation in the x-axis, while a velocity in the seventh joint affects to a rotation or an angular velocity in the z-axis. Here we can see another example with the robot in a different configuration. In this case, I have modified the position of the sixth joint, and it can be seen now that joints 5 and 7 are the ones that allow a rotation in the x-axis, while now only joints 1 and 3 allow the rotation or a rotation in the z-axis. Coefficients that appear in the y row are now somehow larger than before, because the robot arm is extended, and thus the distances to the rotation axis are greater, and that's why the coefficients are also greater. Finally, we are trying to visualize the instantaneous linear velocity vector that we would have at the end effector for a specific configuration. So the configuration doesn't move, but what we're going to do is to modify the velocities of the joints with these sliders. So when we move to the left to the slider, we are actually applying a negative velocity in this case. So let's play the video. And as you can see here, I'm applying a negative velocity on the first joint, and it appears as a negative velocity in the y-axis. This is a negative velocity of the second joint, and you can see it's normal to the in this case to the radius that it's created with the joint and the end effector. That was the third joint, and now we're going to move the fourth joint, which is similar to the second one, okay, as you can see, and then the fifth one, which will imply another rotation in the velocity, in this case in the y-axis again, and this is the sixth joint. This will imply a velocity in the x-axis, and the last joint will not have any kind of effect on the linear velocity because of the orientation it has. Okay. Well, in this video I have explained how to compute the robot Jacobi matrix in CoppeliaSim using the SimAK plugin. Thank you very much. Hello, in this video I am going to explain how to implement a kinematic control to follow trajectories using serial robot manipulator in CoppeliaSim and the SimAK plugin. The aims of this presentation are the implementation of a kinematic controller so that the end effector of the robot follows a given trajectory. To do this, we first review some theoretical concepts associated with the robot kinematic control. Later, we will see how to create a trajectory from a path, which will allow us to obtain the position and orientation of a reference frame to follow. Then we will see some auxiliary functions for calculating the error between the reference orientation and the end effector orientation. We will also briefly review some functions and variables that we need in order to compute the forward kinematics and differential kinematics using the SimAK plugin. Finally, we will see how to implement the kinematic controller once all previous steps have been completed and show a demo or a couple of examples. As a review, to implement a kinematic control, we must compute several terms that require calculations that we have been studying and mentioning them in several previous videos. We need to implement a trajectory generator, and in this case, I'm going to use CoppeliaSim path and get a path point at each time instant. This generator will return a position and orientation, or a reference position and orientation, as well as their velocities. We will compute the error between the reference position and orientation and the end effector position and orientation, obtained from the forward kinematic function. This error will be multiplied by a gain and added to a feed-forward term to compute the end effector speed. This speed will be translated into joint command speeds using the pseudo-inverse of the robot Jacobian. Finally, the integration over time of joint velocities will allow us to compute joint positions that will be applied in the end to the robot. In order to implement kinematic control, we need a reference to follow. Here, I propose to create a path using the utilities offered by CoppeliaSim. In the Add menu, then you can select Path and then choose a path type, for example, a closed path. Once the path has been created, we must properly position it so that all its points are reachable by the robot. Here, I have checked the options X-axis points down or points down the path, and the X-axis points up the path parameter dialog. X-axis points along the path. Okay. Obviously, the path checkpoints can be modified if so wished. Inside the syscall_init function, we will create a dummy that will represent the target to follow, and that this dummy will be positioned at a point of the trajectory. To obtain a position of the path, we must make use of a set of CoppeliaSim API functions that will allow us to obtain a table with all positions and orientations of the path, as well as its partial lengths. The variables velocity and pose along path will allow us to determine which point of the path we want to evaluate and the speed of the point along the path. I have created an auxiliary function that will allow us to obtain a posture from the trajectory. The function obtains an interpolated position and orientation of the path according to the value of pose along path variable, which must be always defined between 0 and 1. Then it sets the pose of the target dummy object according to the obtained position and orientation, and builds the vector of positions and orientations to be used as a reference. That will be actually our return output argument. This is a vector with 7 elements, 3 corresponding to the position and 4 corresponding to the orientation expressed in quaternions. On the other hand, it also obtains the linear and angular velocities of the target dummy by calling the function getObjectVel. This is a function that I'm going to explain right now. This function returns a vector with the linear and angular velocities. Actually, it returns the variation of the Euler angle velocities over time for a given object handle. This function is useful for computing the feed-forward term of the kinematic controller. It obtains the linear velocity, linear vel, and the angular velocity, angvel. Specifically, the angular velocity is defined with respect to the rotation axis of the object, and by means of a simple transformation we can obtain the velocity of the Euler angles. The code I'm showing here combines in a vector of 6 elements, 3 of them corresponding to the linear speed and 3 of them corresponding to the speed of Euler angles. And this is what it returns. On the other hand, to compute an error, we must subtract 2 signals, one with position and orientation references and another one with position and orientations of the end effector. Subtracting positions is not a problem because they are defined in R3, but subtracting orientation is tricky due to Euler discontinuities. In this sense, the correct way to compute a 3D angular difference is by using quaternions. The difference between quaternions is a well-known operation that it is obtained from the multiplication of the first quaternion with the conjugate of the second quaternion. The result of this operation represents a vector and an angle that we must rotate to reach Q2 from Q1. To express the orientation error between the reference and the end effector back in Euler angles, we must use the previous function and then convert the result into Euler angles. For this purpose, I have also implemented another auxiliary function, quad2eul function, which returns a vector with the Euler angles from a given quaternion. Here I have assumed that the Euler angles I use are the x, y, z representation used in CoppeliaSim. Actually, they are Taylorian angles. If beta angle is close to half pi, then a log gimbal situation occurs, which implies that the alpha and gamma angles can be combined and they represent a single rotation because they are basically pointing to the same axis. Here I just simply assume that in this case alpha is 0 and the actual rotation is returned as a computation of the angle gamma. In order to compute forward kinematics and differential kinematics, we must properly configure the CoppeliaSim sim. This is something that we have already seen in previous videos using the SimAK plugin. Here I will simply review the name of the variables that I have defined as a result of each of the stages that we need to complete before continuing. For example, variable IKM contains the handle of the IK environment, while variables IKBase, IKTip, and IKTarget are the handles of the IK dummies that we need to define the base, the tip, and the target of the kinematic problem. The variable IK joints contains a table with handles of IK joints, which are generated from a table of regular joint handles stored in the variable joints. The variable IK group undamped define a task of type pose, and this is something we need in order to compute the forward and specifically differential kinematics. Also, we have implemented, or I assume that we have implemented, a set of functions like IKDH, which allows to compute the inverse kinematics, forward kinematics, while the function getAn allows to compute, in this case, the end effector transformation. Also, the function getJacob will allow us to compute the differential kinematics. All these functions were described in a previous video. The kinematic controller requires to compute the pseudo-inverse of the Jacobian matrix. In the code I show here, I include an auxiliary code to compute such matrix. I explained a similar code when introducing the matrix library, but here I made small modifications to make computations less sensitive to the tolerance parameter. In return, it computes the regularized method it needs several iterations to automatically adjust the value of the regularization parameter. In this case is lambda. In the code of you can see on the right, in the new version. So you can try both of them and you can choose whatever you prefer. The oldest version, which is slightly faster, or the new version, which is let's say less sensitive to the tolerance parameter but slightly slower. Now we are ready to, or we have all necessary elements to implement a kinematic controller. The code I show here must be implemented inside the syscall actuation function, since in each step of the simulation we call the getPathPose function that will return a different posture to follow. depending on the simulation time. From the position and orientation of the end effector, we obtain an error or a vector between the reference and the end effector. This error will be calculated using the quantitative function to compute the angular difference in 3D using the quaternion representation. If you try to do this directly with Euler angles, you will face some discontinuity problems. Once the error has been calculated, we must compute the robot Jacobian and obtain a submatrix corresponding to the task. In this sense, the variable task dim takes the value 6 for posture tracking tasks, but also it could take the value 5 or 3 if we want to solve a kinematic problem but with fewer constraints. At the end of the code, it computes the speed of joints and increments the position or its position accordingly. The computed position must be updated in joints position SIM objects, but also in the objects created in the SIM AK join or plugin, so that all computations, forwarding and differential kinematics are consistent. It is important to note that K is the gain of the controller, and this can be a scalar that affects to all tasks in the same way, but it could be also some diagonal matrix. In my case, I usually use values around 0.5, but the higher gain could also have been used, and in that case would imply a faster convergence to the trajectory. Here I show two demonstrative examples of how the kinematic control works. Using a robot with 7 degrees of freedom. The goal of the first video is to track a posture or pose in which both the position and orientation of the end effector must follow a specific reference. In the second video, I show an example for position tracking with free orientation. Okay, so let's see the first video. Well, as you can see, the controller takes the error to 0, bringing the tip to the end of the end effector closest to the trajectory. And as we can see, the orientation of the end effector adapts the orientation of the trajectory, which changes the angle gamma because, and remember that I checked the option where the x-axis follows the path. Well, in this second example, we see how the end effector approaches the trajectory, but its orientation is totally free. In this case, we would have more degrees of freedom to find a solution for the kinematic problem, which will allow us, for example, to implement policies in the null space of the task. Well, in this video, I have explained how to implement the kinematic control with a serial robot manipulator in CoppeliaSim. Thank you very much. Hello, in this video I will explain how to detect objects using a vision sensor in CoppeliaSim. This will be useful to implement robot visual servoing method, as we will see in the next video. The aims of the presentation is to explain how vision sensors work in CoppeliaSim and more specifically the Sim Vision plugin. We will create a camera from an existing model and configure it to work as a 3D camera in order to detect objects. I will explain the code that the sensor must include in its own script so that it can detect objects, and also I will explain the meaning of the data provided by the object detection algorithm. I will also explain how to get the intrinsic parameters of the camera from the sensor properties, since we will use these parameters to get the 3D position of the objects. The ultimate objective of this presentation is to obtain the values detected for what we consider we known as the reference image, with the purpose of using this reference image within a visual servoing control scheme. Vision sensors must implement a callback function that will be called each time a new image is acquired. This function provides sensor data as input argument in a variable inData, and it must return a table with the compressed or packed output information. By default, CoppeliaSim returns a set of 15 values with information regarding the minimum, maximum and average values detected in the image. But we can return any other additional information if we properly pack this information. Furthermore, CoppeliaSim uses two plugins that will allow us to process images. Specifically, the Sim Vision plugin includes a set of simple operations and functionalities for image processing, such as add or blob detection, among others. The SimIM plugin includes additional processing functions. This is an OpenCV wrapper with some limited functionalities, but in general sufficient for many problems. In this video we will focus on the Sim Vision plugin. The Sim Vision plugin includes a set of functionalities to be able to detect objects in images. Although it is quite limited, it is useful to detect edges, blobs, segment by color, among other few features. Here I show you some of the functions that I consider more relevant for you in many of the standard applications. The way the plugin works, it's through three types of image buffers. On the one hand, we have the original image, which can be overwritten if so wish. Let's say you want to show the processed image instead of the original one, so then you can write this information on the image sensor. Then on the other hand, the plugin uses the working image. This is the buffer on which all the functions that I mentioned before, they do the processing indeed. And in addition to this, there are a couple of auxiliary buffers that allow us to temporarily store a result of a working image to be able to perform some operations, for instance, as abstraction. We're going to configure a vision sensor as a 3D camera that will provide us with the X, Y and Z coordinates of the objects. CoppeliaSim includes in its model library a 3D camera named Blob2 3D Position TTM. The idea is that you can drag this object into your scene, and we will modify the perspective angle of the camera to 45 degrees, as you can see here in the vision sensor properties. You can leave the rest of the parameters by default, except the packet one is black option. If you want, you can mark this option if you want to speed the calculations, but I think you won't really notice a real difference. We're also going to create a plane of dimension 100 by 100 square centimeters and 4 color circles of size 4 times 4 square centimeters, separated by the distance of 5 centimeters with respect to the center of the plane. Then we're going to make the blob to 3D position sensor object child of the blob to 3D position body object. And this will also be a child of the last link of the robot. Note that the original 3D camera model includes also a dynamic object that is part of the camera. We must remove this object because our simulation is a pure kinematic simulation, so we don't use dynamic objects. To properly position the camera and also the orientation, I've included here the positions and orientations of each of the objects so you can obtain the same results I obtained at the end of the presentation. In addition to this, in the code that I show here, in the code that includes the sensor, we are actually going to modify the default code that is included in the syscall vision function that will allow us to implement the actual blob detection. In the code I show here, you can see that I'm calling the blob detection on work-in function that allows detecting the objects or blobs. It has several parameters. One of the most important one is the threshold value, since it will determine the sensitivity of the sensor to detect certain type of objects based on the contrast. Another important parameter in our case is the last argument that we have set to false, so that the return image remains exactly as the original one, so it retains the original colors, since we are going to distinguish each of the blobs according to their color. The parameter that we have set to 0 indicates that the minimum indicates the minimum size of the object that we want to detect, and setting this value to 0 means that there's no filter used in this case. The blob detection on work image function returns information with a very specific structure that is documented in the function help. Every time we read from the vision sensor, we will get this information, and specifically it returns a table with the number of blobs it has detected, as well as the blob size in terms of the number of fields that each blob contains, and also this will help us to properly separate and distinguish between all blobs because they are returned in a single table. The table size actually should be the blob size, which is 6 in this case, multiplied by the number of detected blobs plus 2. Each blob contains information about the relative size, the orientation, X and Y position, and width and height. The X and Y position are normalized to the blob center coordinates. Now let's see how to access all this information. So we need to create, in this case, a script that will be associated to the robot base if you don't have already this script created. And in the syscall init function, we must access to the parameter or the camera handle and obtain information about its intrinsic parameters, such as the horizontal and vertical resolution, perspective angle, near and far clipping distances, and horizontal and vertical scaling parameters. All this data is relevant in order to translate pixels into 3D points. Then we can create a function for detecting 3D objects. So the purpose of this function is to call SimReadVision sensor function that will return the information about the objects detected in the aux2 variable. Remember that CoppeliaSim returns by default a buffer with 15 elements. In this case, this information is returned in the aux1 variable, and it's generic information regarding the properties of the image, such as the average gray values, and among other information. We're not interested in that information, but we will use the actual return value that we have, or the information that we have in a return variable aux2. As you can see in the for loop, I extract all the information that the camera returns and store it in a variable s that contains the coordinates x, y, and z of the detected objects. Note that the variable depth has been obtained because the camera includes a depth buffer, which returns the depth of each of the pixels normalized between the values near clip and far clip, while the coordinates x and y are obtained from coordinates of the objects in the image, and since they are also normalized, we must multiply the pixel value by its z coordinate and divide it by the scale factor. Also inside the for loop, I get the color of the object, the RGB color that, or particularly of the pixel in which we have the x and y coordinate, and we store this in the colors variable. In summary, the blob's 3D points function returns a list of coordinates with each of the features, and it has also a list with all the colors. If you call blob 3D points function inside the syscall sensing function and print the values of the variables sref and colorsref, they should have approximately the values that I show here in these tables. These values will be considered as reference values when implemented a robot visual servoing. If everything is correct, you should also see that the camera projects 4 spheres right in the position where the circles are. Well, in this presentation I have explained how to implement object detection that will help us to implement visual feedback control, as I will explain in the next video. Thank you very much. Hello, in this video I will explain how to implement visual feedback servoing in CoppeliaSim. Specifically, I will focus on the implementation aspects of the kinematic controller using an image-based method, while in the previous video we saw how to implement all those aspects related with the object detection. As you can see, this presentation has many objectives to achieve. First, I will review the conceptual framework of robot visual servoing using a control diagram. Later, I will explain how to obtain features and make correspondence with those obtained with a reference image in order to compute an error to be minimized. Then I will explain how to compute the interaction matrix and how to obtain the transformation between the camera and the end effector. And we will also see a brief overview about the variables and functions that I use in order to compute the robot kinematics. And some rotational in the end, I will explain how to implement the robot visual servoing, and we will see some rotational and translational examples. This diagram represents the required robot visual servoing control structure. We need a reference image. This is a set of reference features as ref and a list of features colors, information about the reference features. On the other hand, an image processing method will provide us a list with the detected characteristics with their corresponding colors on actual images. With all this information, we need to compute an error between the features. In this case, I use color data to make the correspondence. This error is defined in the image plane, and for this reason, we use differential kinematics as well as the transformation between the final end effector and the camera and the interaction matrix, so we can relate velocities in the image plane with joint velocities. A proportional controller is responsible for determining the actual joint velocities so that the error converges to zero using the zero inverse of the Jacobian. Since it is a kinematic simulation, these velocities will be integrated over time to determine the new joint positions that will ultimately move the end effector to a new position from where we can take a new image. In this presentation, I will assume that you already have completed all necessary steps to detect objects and images. In the previous video, I explained how to implement this process using a vision sensor in CoppeliaSim, and as a result, we will be able to get a list of features and their colors that will be used as reference values. Using this image processing algorithm, we will be able to detect features from actual images, so the idea is to use them, or to use the function blob 3D points on every simulation step, and this is a function that I explained in the previous video that will return in the end a list of features and a list of colors of the features. In order to compute the error between the detected features and the reference features, we must establish a prior correspondence between them. For this reason, when detecting objects, we also detect the colors in addition to the features position. For the correspondence is done using the color data using one of the simplest possible methods, a nearest neighbor approach. Obviously, there are other other methods more robust in computer vision, but since this is not a part of our problem statement, I prefer to keep it simple here. However, in a real-life application, this might be a key step. Thus, correspondence is implemented by determining the closest point in the RGB color space. As I said, I'm aware that this is not the most appropriate approach, but this is one of the simplest ones, and it's robust enough to work for the problem that I'm trying to solve here. The error in the feature is a vector with twice as many elements as the number of features we have detected, since the error vector includes errors in x and y coordinates of each feature in a column form. For the example shown, the vector or the error vector is a vector with 8 elements. So in order to compute the elements of this vector, we must subtract the elements of the list of detected features and subtract them with the elements of the list of the reference features, indexed accordingly with to the correspondence list. This is what I have coded here, and in the examples at the end of the video you will see that the norm of this error tends to 0. The interaction matrix relates the velocities of the features in the image plane to linear and angular velocities of the camera reference frame. This matrix therefore has as many rows as twice of detected features and 6 columns, corresponding to the 3 linear velocities and the 3 angular velocities in a 3D space. The matrix is computed from the detected features, but as we saw in a previous or a specific video about robot visual servoing technique, IVS, it is also convenient to use the reference features of in order to compute the interaction matrix. So this, in the end, we take the average of both matrices and return this as an output argument of the function. As input argument of this function, I include here the list of measure features, the reference features, and also the list of the correspondence. The camera is attached to the last link of the robot. However, the reference system of the camera and the end effector, they do not have to be coincident. In this case, even they are close, it is convenient to compute the transformation between them so that we can compute the relation between the linear and angular velocities using classic maths for 3D motion. In particular, we need to compute, as you can see here, or we use the 3D motion maths that translate linear and angular velocities from one reference frame into another reference frame. In order to compute forward and differential kinematics, we must properly set up CoppeliaSim scene and the SimAK plugin. This is something, again, that we have already seen in a previous video, where I have explained how to configure the SimAK plugin so we can use it for computed robot kinematics. We also implement for tracking trajectories and so on. Here I include the names of the variables. You should be already familiar by now with those names, and these are associated with the specific implementation of the robot kinematics. I also have included here the names of the functions that allow us to compute such kinematics that will be obviously used in the image-based kinematic controller, such as the getAN, getJacob, and AKDH functions. Kinematic control with visual feedback would consist of suitably combine all these elements that we have previously seen. We must obtain a set of features and compare them with reference ones and compute the error between them. Before that, we should have established a correspondence between them. We must also compute the robot Jacobian, but please bear in mind that the Jacobian returned by CoppeliaSim is the Jacobian with respect to the robot base, but we need the Jacobian with respect to the end effector. We just need to perform a simple linear transformation so that the Jacobian is multiplied with a blockwise diagonal matrix with the rotation matrix between the end effector and the robot base. On the other hand, we must have computed as well, or we should compute as well the transformation between the end effector and the camera. This transformation is constant and can be done in the initialization of your script, and therefore it can be just simply computed once. The interaction matrix, it's computed from features, from measurement features and reference features. The result of all these calculations is a Jacobian matrix JC that represents the variation of the position of features in the image planes as a consequence of variations of the joints. A proportional control based on the pseudo-inverse of the Jacobian matrix will allow us to obtain joint speeds that would make the error to converge to zero. Due to non-linearities, this is not always true, but as we will see in the examples, we will see that the control is quite robust, particularly if we are able to solve the correspondence problem. In the syscall actuation function, we can implement the integrator that will allow us to determine the new positions of the joints that the robot must have on their velocities. But remember that we have to set the position of the joints in the CoppeliaSim scene objects, but as well in the SimAK objects. In this first example, we're going to see a case in which the robot must perform a rotation of the last joint. This is a 125 rotation with respect to the reference configuration, which is quite a lot. As it can be seen, the robot is capable of solving the problem posed. The configuration reached doesn't have to coincide with reference 1, since this is a redundant robot with 7 degrees of freedom, but as it can be seen, the logarithm of the error decreases practically linear to a point where the error magnitude is due to quantization errors. In this second example, I have positioned the robot so that the camera is translated, but the orientation of the camera is the correct one. Let's see how it works. Once again, it is observed that how the robot is capable of solving the problem. In this case, it moves the camera, but also has a small rotation and inclination that it's being corrected until we reach the error close to the noise level. And in this third example, I have moved the robot so that the axis must perform a simultaneous translation and rotation. Specifically, the image is rotated 90 degrees, but it also has some displacement, so we detect the blobs or the objects at the left bottom left corner of the image. So let's see how it works. Again, it can be seen that despite of the difficulty of the problem, the IBBS algorithm is capable of solving this situation, moving the camera to a configuration where the error is very, very small. Well, in this presentation I have explained how to implement the kinematic controller for robot visual servoing in CoppeliaSim. Thank you very much.
Hello, I am Leopoldo Armesto. You probably know about me because I have developed a set of video tutorials about CoppeliaSim. And this video is about what happens when Coppelia Robotics releases a new version of CoppeliaSim, and without notice the old version stops working. Actually, let me show you exactly what happens. If you try to run the software, I'm working right now with the version 4.2.0, and the 4.3 version it's released. Now it says here leaving, and without any kind of warning, error or something like that, it stops working. Okay, you might have to understand that as an academic, this is a very inappropriate behavior of the software, because when you're running the software in a computer lab and you try to expect to use it for, let's say, lab sessions, then this behavior is totally undesirable. Okay, Coppelia Robotics actually is trying to force us to update to the new version by doing this, but actually updating to the new version has to be done with caution, because the API that was working for previous versions is not always compatible with the new version. So you have to be careful about that. Okay, so what to do in that case? What you have to do is you have to go to program files. Okay, this is in Spanish, but in English is program files. Okay, and inside program files you will find the folder Coppelia Robotics, and then CoppeliaSim Edu, and then inside this folder there's a system folder. Okay, and a file which is user set txt. You have to open this file here, and this line here, you see the first line, it's not included by default when you have installed the software. But if you Google on the Coppelia Robot and CoppeliaSim forum, then you can find that the maintainers they mentioned that you have to include this line in this file. So actually, I'm going to uncomment this line, save it, and now if I run the software, you will see that everything works as expected. The problem is that this line here, the port that you're trying to access, depends on the version. Okay, The one you've seen before, it's only valid for the version 4.2.0. Okay, and if you have, let's say, next year, you have already installed the 4.3.0 and you have to update, probably this number has to be is different and you have to Google for it. Okay, thank you very much.